All right, welcome back to machine learning. I'm really excited to be able to share some amazing stuff that University of San Francisco students have built during the week or written about during the week. And quite a few of the things I'm going to show you have already spread around the internet quite a bit. Lots of tweets and posts and all kinds of stuff happening. One of the first to be widely shared was this one by Tyler, who did something really interesting. He started out by saying, like, what if I create this synthetic data set where the independent variables is like the X and the Y, and the dependent variable is like color, right? And interestingly, he showed me an earlier version of this where he wasn't using color. He was just like putting the actual numbers in here. And this thing kind of wasn't really working at all. And as soon as he started using color, it started working really well. And so I wanted to mention that one of the things that unfortunately we don't teach you at USF is theory of human perception. Perhaps we should. Because actually when it comes to visualization, it's kind of the most important thing to know is what is the human eye, or what's the human brain good at perceiving. There's a whole area of academic study on this. And one of the things that we're best at perceiving is differences in color. Right? So that's why as soon as we look at this picture of this synthetic data he created, you can immediately see, oh, there's kind of 4 areas of, lighter red color. So what he did was he said, okay, what if we tried to create a machine learning model of this synthetic data set? So specifically, he created a tree. And the cool thing is that you can actually draw the tree, right? So after he created the tree, he did this all in Matplotlib. Matplotlib is very flexible, right? He actually drew the tree boundaries. So that's already a pretty neat trick, is to be actually able to draw the tree. But then he did something even cleverer, which is he said, okay, so what predictions does the tree make? Well, it's the average of each of these areas, and so to do that we can actually draw the average color, right? Which is actually kind of pretty. Here is the predictions that the tree makes. Now, here's where it gets really interesting, is you can, as you know, randomly generate trees through resampling, and so here are 4 trees generated through resampling. They're all pretty similar, but a little bit different. And so now we can actually visualize bagging. And to visualize bagging, we literally take the average of the 4 pictures, right? That's what bagging is. And there it is, right? And so here is the fuzzy decision boundaries of a random forest. And I think this is kind of amazing, right? Because it's like I wish I had this actually when I started teaching you all random forests, because I could have skipped a couple of classes. It's just okay, that's what we do. We create the decision boundaries, we average each area, and then we do it a few times and average all of them. Okay, so that's what a random forest does. And I think this is just such a great example of making the complex easy through pictures. So congrats to Tyler for that. It actually turns out that he has actually reinvented something that somebody else has already done. A guy called Christian Innie, who went on to be one of the world's foremost machine learning researchers, actually included almost exactly this technique in a book he wrote about decision forests. So it's actually kind of cool that Tyler ended up reinventing something that one of the world's foremost authorities on decision forests actually has created. So I thought that was neat. And it's nice because when we posted this on Twitter, it got a lot of attention, and finally somebody was able to say oh, you know what, this actually already exists. So Tyler's gone away and started reading that book. Something else which is super cool is Jason Carpenter created a whole new library called Parfit. And Parfit is a parallelized fitting of multiple models for the purpose of selecting hyperparameters. And there's a lot I really like about this. He's shown a clear example of how to use it, right? And the API looks very similar to other grid search-based approaches, but it uses the validation techniques that Rachel wrote about and that we learned about a couple of weeks ago of using a good validation set. And what he's done here is in his blog post that introduces it, he's gone right back and said like, well, what are hyperparameters? Why do we have to train them? And he's kind of explained every step. And then the module itself is like, it's very polished. He's added documentation to it. He's added a nice README to it. And it's kind of interesting when you actually look at the code, you realize, it's very simple, which is, it's definitely not a bad thing. That's a good thing, is to make things simple. But by kind of writing this little bit of code and then packaging it up so nicely, he's made it really easy for other people to use this technique, which is great. And so one of the things I've been really thrilled to see is then Vinay went along and combined two things from our class. One was to take Parfit, and then the other was to take the kind of accelerated SGD approach to classification we learned about in the last lesson, and combine the two to say like, okay, well, let's now use Parfit to help us find the parameters of a SGD logistic regression. So I think that's really a really great idea. Something else which I thought was terrific is Prince actually basically went through and summarized pretty much all the stuff we learned in the random forest interpretation class. And he went even further than that as he described each of the different approaches to random forest interpretation. He described how it's done. So here, for example, is feature importance through variable permutation. A little picture of each one. And then super cool, here is the code to implement it from scratch. So I think this is like really nice post, describing something that not many people understand and showing, exactly how it works, both with pictures and with code that implements it from scratch. So I think that's really, really great. One of the things I really like here is that for like the tree interpreter part, he actually showed how you can take the tree interpreter output and feed it into the new waterfall chart package that Chris, our USF student, built to show how you can actually visualize the contributions of the tree interpreter in a waterfall chart. So again, kind of a nice combination of multiple pieces of technology we've both learnt about and built as a group. I also really thought this kernel, there's been a few interesting kernels shared, and I'll share some more next week. Devesh wrote this really nice kernel showing there's this quite challenging Kaggle competition on detecting icebergs versus ships. And it's a kind of a weird two-channel satellite data, which is very hard to visualize. And he actually went through and basically described kind of the formulas for how these like radar scattering things actually work, and then actually managed to come up with a code that allowed him to recreate, the actual 3D icebergs or ships. And I have not seen that done before. Like it's quite challenging to know how to visualize this data. And then he went on to show how to build a neural net to try to interpret this. So that was pretty fantastic as well. So yeah, congratulations for all of you. I know for a lot of you, you're posting stuff out there to the rest of the world for the first time, and it's kind of intimidating. You're used to writing stuff that you kind of hand in to a teacher and they're the only ones who see it, and it's kind of scary the first time you do it, but then the first time somebody, upvotes your Kaggle kernel or adds a clap to your Medium post, you suddenly realize, oh, I've written something that people like. That's pretty great. So if you haven't tried yourself yet, I again invite you to try writing something. And if you're not sure, you could write a summary of a lesson. You could write a summary of like, if there's something you found hard, like maybe you found it hard to fire up a GPU-based AWS instance, you eventually figured it out, you could write down, just describe how you solved that problem. Or if one of your classmates didn't understand something and you explained it to them, then you could like write down something saying like, oh, there's this concept that some people have trouble understanding, here's a good way I think of explaining it. There's all kinds of stuff you could do. Okay, so let's go back to SGD. And so we're going back through this notebook which Rachel put together, basically taking us through kind of SGD from scratch for the purpose of digit recognition. And actually quite a lot of the stuff we look at today is going to be closely following part of the computational linear algebra course, which you can both find the MOOCs on FastAI or at USF. It'll be an elective next year, right? So if you find some of this this stuff interesting, and I hope you do, then please consider signing up for the elective or checking out the video online. So we're building neural networks. And we're starting with an assumption that we've downloaded the MNIST data, we've normalized it by subtracting the mean and divided by the standard deviation. Okay, so the data is, it's slightly unusual in that although they represent images, they were downloaded as, each image was a 784 long rank 1 tensor. So it's been flattened out. Okay, and so for the purpose of drawing pictures of it, we had to resize it to 28 by 28. But the actual data we've got is not 28 by 28. It's 784 long, flattened out. Okay. The basic steps we're going to take here is to start out with training the world's simplest neural network. It's basically a logistic regression, right? So no hidden layers. And we're going to train it using a library, FastAI, and we're going to build the network using a library, PyTorch, right? And then we're going to gradually get rid of all the libraries, right? So first of all, we'll get rid of the NN neural net library in PyTorch and write that ourselves. Then we'll get rid of the FastAI fit function and write that ourselves. And then we'll get rid of the PyTorch optimizer and write that ourselves. And so by the end of this notebook, we'll have written all the pieces ourselves. The only thing that we'll end up relying on is the two key things that PyTorch gives us, which is A, the ability to write Python code and have it run on the GPU, and B, the ability to write Python code and have it automatically differentiated for us. Okay? So they're the two things we're not going to attempt to write ourselves because it's boring and pointless, but everything else we'll try and write ourselves on top of those two things. Okay? So our starting point is like not doing anything ourselves. It's basically having it all done for us. And so PyTorch has an NN library, which is where the neural net stuff lives. You can create a multi-layer neural network by using the sequential function and then passing in a list of the layers that you want. And we asked for a linear layer followed by a softmax layer, and that defines our logistic regression. Okay? The input to our linear layer is 28 by 28, as we just discussed. The output is 10, because we want a probability for each of the numbers 0 through 9, for each of our images. Okay? CUDA sticks it on the GPU. And then fits a model. Okay, so we start out with a random set of weights, and then fit uses gradient descent to make it better. We had to tell the fit function what criterion to use. In other words, what counts as better, and we told it to use negative log likelihood. We'll learn about that in the next lesson, what that is exactly. We had to tell it what optimizer to use, and we said please use optim.atom. The details of that we won't cover in this course. We're going to build something simpler called SGD. If you're interested in atom, we just covered that in the deep learning course. And what metrics do you want to print out? We decided to print out accuracy. Okay, so that was that. And so if we do that, okay. So after we fit it, we get an accuracy of generally somewhere around 91, 92%. So what we're going to do from here is we're going to repeat this exact same thing. So we're going to rebuild this model 4 or 5 times, building it and fitting it with less and less libraries. Okay, so the second thing that we did last time was to try to start to define the module ourselves, right? So instead of saying the network is a sequential bunch of these layers, let's not use that library at all and try and define it ourselves from scratch. Okay. So to do that, we have to use OO, because that's how we build everything in PyTorch. And we have to create a class which inherits from nn.module. So nn.module is a PyTorch class that takes our class and turns it into a neural network module, which basically means anything that you inherit from nn.module like this, you can pretty much insert into a neural network as a layer, or you can treat it as a neural network. It's going to get all the stuff that it needs automatically to work as a part of or a full neural network. And we'll talk about exactly what that means today and the next lesson. Right? So we need to construct the object. So that means we need to define the constructor, dunder init. And then importantly, this is a Python thing, is if you inherit from some other object, then you have to create the thing you inherit from first. So when you say super.dunder init, that says construct the nn.module piece of that first, right? If you don't do that, then the nn.module stuff never gets a chance to actually get constructed. Right? So this is just like a standard Python OO subclass constructor. Okay? And if any of that's unclear to you, then this is where you definitely want to just grab a Python intro to OO, because this is the standard approach. All right. So inside our constructor, we want to do the equivalent of nn.linear. All right. So what nn.linear is doing is it's taking our 28 by 28 vector, so 768 long vector, and that's going to be the input to a matrix multiplication. So we now need to create something with 768 rows, and that's 768, and 10 columns. Okay, so because the input to this is going to be a mini batch of size, actually let's move this into a new window. (768) by 10, and the input to this is going to be a mini batch of size 64 by 768. Right? So we're going to do this matrix product. Okay? So when we say in PyTorch nn.linear, it's going to construct this matrix for us. Right? So since we're not using that, we're doing things from scratch, we need to make it ourselves. So to make it ourselves, we can say generate normal random numbers with this dimensionality, which we passed in here, 768 by 10. Okay, so that gives us our randomly initialized matrix. Okay. Then we want to add on to this, we don't just want y equals ax, we want y equals ax plus b. Right, so we need to add on what we call in neural nets a bias vector. So we create here a bias vector of length 10. Okay, again, randomly initialized. And so now here are our two randomly initialized weight tensors. So that's our constructor. Okay. Now we need to define forward. Why do we need to define forward? This is a PyTorch specific thing. What's going to happen is this is when you create a module in PyTorch, the object that you get back behaves as if it's a function. You can call it with parentheses, which we'll do that in a moment. And so you need to somehow define what happens when you call it as if it's a function. And the answer is PyTorch calls a method called forward. Okay, that's the PyTorch kind of approach that they picked, right? So when it calls forward, we need to do our actual calculation of the output of this module or layer. Okay, so here is the thing that actually gets calculated in our logistic regression. So basically, we take our input x, which gets passed to forward. That's basically how forward works. It gets passed the mini batch, and we matrix multiply it by the layer 1 weights, which we defined up here. And then we add on the layer 1 bias, which we defined up here. Okay. And actually, nowadays, we can define this a little bit more elegantly using the Python 3 matrix multiplication operator, which is the @ sign. Okay. And when you use that, I think you kind of end up with something that looks closer to what the mathematical notation looked like, and so I find that nicer. Okay. All right, so that's our linear layer in our logistic regression, in our zero hidden layer neural net. So then the next thing we do to that is softmax. Okay, so we get the output of this matrix multiply. Okay, who wants to tell me what the dimensionality of my output of this matrix multiply is? Sorry? 64 by 10. Thank you, Karen. And I should mention, for those of you that weren't at Deep Learning class yesterday, we actually looked at a really cool post from Kerem who described how to do structured data analysis with neural nets, which has been like super popular. And a whole bunch of people have kind of said that they've read it and found it super interesting. So that was really exciting. So we get this matrix of outputs, and we put this through a softmax. And why do we put it through a softmax? We put it through a softmax because in the end, we want for every image, we want a probability that it's a 0 or a 1 or a 2 or a 3 or 4, right? So we want a bunch of probabilities that add up to 1, and where each of those probabilities is between 0 and 1. So a softmax does exactly that for us. So for example, if we weren't picking out numbers from 0 to 10, but instead we're picking out cat, dog, plane, fish, or building, the output of that matrix multiply for one particular image might look like that. These are just some random numbers. And to turn that into a softmax, I first go e to the power of each of those numbers. I sum up those e to the power ofs, and then I take each of those e to the power ofs and divide it by the sum. And that's softmax. That's the definition of softmax. So because it was e to the power of, it means it's always positive. Because it was divided by the sum, it means that it's always between 0 and 1. And it also means, because it's divided by the sum, that they always add up to 1. So by applying this softmax activation function, so anytime we have a layer of outputs, which we call activations, and then we apply some function, some nonlinear function to that maps one scalar to one scalar, like softmax does. We call that an activation function. Okay? So the softmax activation function takes our outputs and turns it into something which behaves like a probability. Right? We don't, strictly speaking, need it. We could still try and train something where the output directly is the probabilities, right? But by using this function that automatically makes them always behave like probabilities, it means there's less for the network to learn, so it's going to learn better, right? So generally speaking, whenever we design an architecture, we try to design it in a way where it's as easy as possible for it to create something of the form that we want. So that's why we use softmax. Right, so that's the basic steps, right? We have our input, which is a bunch of images, right, which is here. It gets multiplied by a weight matrix. We actually also add on a bias, right, to get a output of the linear function. we put it through a nonlinear activation function, in this case softmax, and that gives us our probabilities. So there that all is. PyTorch also tends to use the log of softmax for reasons that don't particularly need bother us now. It's basically a numerical stability convenience. Okay, so to make this the same as our version up here that uses log softmax, I'm going to use log here as well. Okay, so we can now instantiate this class, that is, create an object of this class.
So I have a question back for the probabilities where we were before.
Mm-hmm.
So if we were to have a photo with a cat and a dog together, would that change the way that that works? Or does it work in the same basic
Yeah,
manner?
so that's a great question. So if you had a photo with a cat and a dog together and you wanted it to spit out both cat and dog, this would be a very poor choice. So softmax is specifically the activation function we use for categorical predictions where we only ever want to predict one of those things, right? And so part of the reason why is that, as you can see, because we're using e to the, right, e to the slightly bigger numbers creates much bigger numbers, as a result of which we generally have just one or two things large and everything else is pretty small, right? So if I like recalculate these random numbers a few times, you'll see like it tends to be a bunch of zeros and one or two high numbers, right? So it's really designed to try to kind of make it easy to predict like this one thing is the thing I want. If you're doing multi-label prediction, so I want to find all the things in this image, rather than using softmax, we would instead use sigmoid, right? So sigmoid would cause each of these to be between 0 and 1, but they would no longer add to 1. Good question. And like a lot of these details about like best practices are things that we cover in the deep learning course, and we won't cover heaps of them here in the machine learning course. We're more interested in the mechanics, I guess. But we'll try and do them if they're quick. All right. So now that we've got that, we can instantiate an object of that class. And of course, we want to copy it over to the GPU, so we can do computations over there. Again, we need an optimizer. We'll be talking about what this is shortly. But you'll see here, we've called a function on our class called parameters, but we never defined a method called parameters. And the reason that is going to work is because it actually was defined for us inside nn.module. And so nn.module actually automatically goes through the attributes we've created and finds anything that basically we said, this is a parameter. So the way you say something is a parameter is you wrap it in nn.parameter. So this is just the way that you tell PyTorch, this is something that I want to optimize. Okay? So when we created the weight matrix, we just wrapped it with nn.parameter. It's exactly the same as a regular PyTorch variable, which we'll learn about shortly. It's just a little flag to say, hey, you should optimize this. And so when you call net2.parameters on our net2 object we created, it goes through everything that we created in the constructor, checks to see if any of them are of type parameter, and if so, it sets all of those as being things that we want to train with the optimizer. And we'll be implementing the optimizer from scratch later. Okay, so having done that, we can fit. And we should get basically the same answer as before, 91-ish. So that looks good. All right. So what have we actually built here? Well, what we've actually built, as I said, is something that can behave like a regular function, right? So I want to show you how we can actually call this as a function. So to be able to call it as a function, we need to be able to pass data to it. To be able to pass data to it, I'm going to need to grab a mini batch of MNIST images. Okay, so we used, for convenience, the image classifier data from arrays method from FastAI. And what that does is it creates a PyTorch data loader for us. A PyTorch data loader is something that grabs a few images and sticks them into a mini batch and makes them available. And you can basically say, give me another mini batch, give me another mini batch, give me another mini batch. And so in Python, we call these things generators. Generators are things where you can basically say, I want another, I want another, I want another, right? There's this kind of very close connection between iterators and generators. I'm not going to worry about the difference between them right now, but you'll see basically to turn, to actually get hold of something which we can say, please give me another of, in order to grab something that we can use to generate mini batches, we have to take our data loader, and so you can ask for the training data loader from our model data object. You'll see there's a bunch of different data loaders you can ask for. You can ask for the test data loader, the train data loader, the validation loader, augmented images data loader, and so forth. So we're going to grab the training data loader that was created for us. This is a standard PyTorch data loader, well, slightly optimized by us, but same idea. And you can then say, this is a standard Python thing. We can say, turn that into an iterator. Turn that into something where we can grab another one at a time from. And so once you've done that, we've now got something that we can iterate through. You can use the standard Python next function to grab one more thing from that generator. Okay. So that's returning the x's from our mini batch and the y's from our mini batch. The other way that you can use generators and iterators in Python is with a for loop. I could also have said like for, x mini batch, comma, y mini batch in data loader, and then like do something, right? So when you do that, it's actually behind the scenes. It's basically syntactic sugar for calling next lots of times, okay? So this is all standard Python stuff. So that returns a tensor of size 64 by 784, as we would expect, right? The FastAI library we used defaults to a mini batch size of 64. That's why it's that long. These are all of the background 0 pixels, but they're not actually 0. In this case, why aren't they 0? Yeah, they're normalized, exactly, right? So we subtracted the mean divided by the standard deviation, right? So there it is. So now what we want to do is we want to pass that into our logistic regression. So what we might do is we'll go variable xmb equals variable. Okay, I can take my x mini batch. I can move it onto the GPU, because remember my net2 object is on the GPU, so our data for it also has to be on the GPU. And then the second thing I do is I have to wrap it in variable. So what does variable do? This is how we get for free automatic differentiation. PyTorch can automatically differentiate pretty much anything, right? Any tensor. But to do so takes memory and time. So it's not going to always keep track, like to do automatic differentiation, it has to keep track of exactly how something was calculated. We added these things together, we multiplied it by that, we then took the sign, blah, 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 right? You have to know all of the steps, because then to do the automatic differentiation, it has to take the derivative of each step using the chain rule, multiply them all together, right? So that's slow and memory intensive. So we have to opt in to saying like, okay, this particular thing we're going to be taking the derivative of later, so please keep track of all of those operations for us. And so the way we opt in is by wrapping a tensor in a variable, right? So that's how we do it. And you'll see that it looks almost exactly like a tensor, but it now says variable containing this tensor, right? So in PyTorch, a variable has exactly identical API to a tensor, or actually more specifically a superset of the API of a tensor. Anything we can do to a tensor, we can do to a variable. But it's going to keep track of exactly what we did, so we can later on take the derivative. Okay, so we can now pass that into our net2 object. And remember I said you can treat this as if it's a function, right? So notice we're not calling dot forward. We're just treating it as a function. And then remember we took the log, so to undo that I'm taking the exp, and that will give me my probabilities. Okay, so there's my probabilities. And it's got return something of size 64 by 10. So for each image in the mini batch, we've got 10 probabilities. And you'll see most probabilities are pretty close to 0, right? And a few of them are quite a bit bigger, which is exactly what we would hope, right? Is that it's like, okay, it's not a 0, it's not a 1, it's not a 2, it is a 3, it's not a 4, it's not a 5, and so forth. So maybe this would be a bit easier to read if we just grab like the first 3 of them. Okay, so it's like 10 to the negative 3, 10 to the negative 8, 2, 5, 5, 4. Okay, and then suddenly here's 1, which is 10 to the negative 1, right? So you can kind of see what it's trying to do here. I mean, we could call like net2 dot forward, and it'll do exactly the same thing, right? But that's not how all of the PyTorch mechanics actually work. It's actually, they actually call it as if it's a function, right? And so this is actually a really important idea, like, because it means that when we define our own architectures or whatever, anywhere that you would put in a function, you could put in a layer. Anywhere you put in a layer, you can put in a neural net. Anywhere you put in a neural net, you can put in a function. Because as far as PyTorch is concerned, they're all just things that it's going to call, just like as if they're functions. So they're all like interchangeable. And this is really important because that's how we create really good neural nets, is by mixing and matching lots of pieces and putting them all together. Right? Let me give you an example. Here is my logistic regression, which got 91 and a bit % accuracy. I'm now going to turn it into a neural network with one hidden layer. Right? And the way I'm going to do that is I'm going to create one more layer. I'm going to change this so it spits out 100 rather than 10, which means this one input is going to be 100 rather than 10. Now this as it is can't possibly make things any better at all yet. Why is this definitely not going to be better than what I had before? Yeah, can somebody pass the... Yeah.
Because you've got a combination of 2 linear layers, which is just the same as 1 linear layer with different parameters.
Exactly. Right. So we've got 2 linear layers, which is just a linear layer. Right. So to make things interesting, I'm going to replace all of the negatives from the first layer with zeros, because that's a nonlinear transformation. And so that nonlinear transformation is called a rectified linear unit. Okay. So nn.sequential simply is going to call each of these layers in turn for each mini batch. Right. So do a linear layer, replace all of the negatives with 0, do another linear layer, and do a softmax. This is now a neural network with one hidden layer. And so let's try training that instead. Okay, our accuracy's now gone up to 96%. Okay, so this is the idea, is that the basic techniques we're learning in this lesson like become powerful at the point where you start stacking them together. Okay, can somebody pass the green box there and then there? Yes, Daniel.
Why did you pick 100?
No reason. It was like easier to type an extra 0. Like this question of like how many activations should I have in a neural network layer is kind of part of the skill of a deep learning practitioner. We cover it in the deep learning course, not in this course.
When adding that additional, I guess, transformation,
additional layer.
Additional layer.
This one here is called a nonlinear layer or an activation function.
You said activation layer?
Activation function or activation layer.
Okay, activation function.
Mm-hmm.
Does it matter that, like, if you would have done, for example, like 2 softmaxes, or is that something you cannot do? Like when
no, you can absolutely use a softmax there, but it's probably not going to give you what you want. And the reason why is that a softmax tends to push most of its activations to 0. Right? And an activation, just to be clear, like I've had a lot of questions in the deep learning course about like what's an activation? An activation is the value that is calculated in a layer, right? So this is an activation, right? It's not a weight. A weight is not an activation. It's the value that you calculate from a layer. So softmax will tend to make most of its activations pretty close to zero, and that's the opposite of what you want. You generally want your activations to be kind of as rich and diverse and used as possible. So nothing to stop you doing it, but it probably won't work very well. Basically, pretty much all of your layers will be followed by non-linear activation functions that will nearly always be ReLU, except for the last layer.
To ask the question in a different way, could you, when doing multiple layers, so let's say like going 2 or 3,
could you lift things?
Just going 2 or 3 layers deep, do you want to switch up these activation layers,
No.
or is it okay just to keep them consistent?
No, that's a great question. So if I wanted to go deeper, I would just do that. Okay, that's a now 2 hidden layer network.
So I think I'd heard you said that there are a couple of different activation functions, like that rectified linear unit. What are some examples, and why would you use each?
Yeah, great question. So basically, like, as you add like more linear layers, you kind of got your input comes in, and you put it through a linear layer, and then a non-linear layer, linear layer, non-linear layer. Linear layer, and then the final non-linear layer. The final non-linear layer, as we've discussed, if it's a multi-category classification, but you only ever pick one of them, you would use softmax. If it's a binary classification or a multi-label classification where you're predicting multiple things, you would use sigmoid. If it's a regression, you would often have nothing at all, right? Although we learned in last night's DL course where sometimes you can use sigmoid there as well. So they're basically the options, main options for the final layer. For the hidden layers, you pretty much always use ReLU. Right? But there is another one you can pick, which is kind of interesting, which is called leaky ReLU, and it looks like this. And basically, if it's above 0, it's y equals x, and if it's below 0, it's like y equals 0.1x. Okay, so it's very similar to ReLU, but it's rather than being equal to 0 under x, it's like something close to that. So they're the main two, ReLU and leaky ReLU. There are various others, but they're kind of like things that just look very close to that. So for example, there's something called ELU, which is quite popular, but like, the details don't matter too much, honestly. Like like ELU is something that looks like this, but it's slightly more curvy in the middle. And it's kind of like, it's not generally something that you so much pick based on the data set. It's more like, over time, we just find better activation functions. So 2 or 3 years ago, everybody used ReLU. A year ago, pretty much everybody used leaky ReLU. Today, I guess probably most people are starting to move towards ELU. But honestly, the choice of activation function doesn't matter terribly much, actually. And people have actually showed that you can use like pretty arbitrary nonlinear activation functions, like even a sine wave, and it still works. Okay. So although what we're going to do today is showing how to create this network with no hidden layers, to turn it into that network, which is 96%-ish accurate, it will be trivial, right? And in fact, it's something you should probably try and do during the week, right, is to create that version. Okay, so now that we've got something where we can take our network, pass in our variable, and get back some predictions, that's basically all that happened when we called fit. So we're going to see how that approach can be used to create this stochastic gradient descent. One thing to note is that to turn the predicted probabilities into a predicted, like which digit is it, we would need to use argmax. Unfortunately, PyTorch doesn't call it argmax. Instead, PyTorch just calls it max, and max returns two things. It returns the actual max across this axis, so this is across the columns, right? And the second thing it returns is the index of that maximum, right? So the equivalent of argmax is to call max and then get the first indexed thing. Okay, so there's our predictions. Right? If this was in NumPy, we would instead use np.argmax. Okay. All right. So here are the predictions from our hand-created logistic regression, and in this case, looks like we got all but one correct. So the next thing we're going to try and get rid of in terms of using libraries is we'll try to avoid using the matrix multiplication operator, and instead we're going to try and write that by hand. So this next part, we're going to learn about something which kind of seems it's going to seem like a minor little kind of programming idea. But actually it's going to turn out that, at least in my opinion, it's the most important programming concept that we'll teach in this course, and it's possibly the most important programming kind of concept in all the things you need to build machine learning algorithms. And it's the idea of broadcasting. And the idea I will show by example. If we create an array of 10, 6, neg 4 and an array of 2, 8, 7, and then add the two together, it adds each of the components of those two arrays in turn. We call that element-wise. So in other words, we didn't have to write a loop, right? Back in the old days, we would have to have looped through each one and added them and then concatenated them together. We don't have to do that today. It happens for us automatically. So in NumPy, we automatically get element-wise operations. We can do the same thing with PyTorch. So in FastAI, we just add a little capital T to turn something into a PyTorch tensor, right? And if we add those together, exactly the same thing, right? So element-wise operations are pretty standard in these kinds of libraries. It's interesting not just because we don't have to write the for loop, right? But it's actually much more interesting because of the performance things that are happening here. The first is, if we were doing a for loop, right? If we were doing a for loop, that would happen in Python, right? Even when you use PyTorch, it still does the for loop in Python. It has no way of like optimizing a for loop. And so a for loop in Python is something like 10,000 times slower than in C. So that's your first problem. I can't remember, it's like 1,000 or 10,000. The second problem then is that you don't just want it to be optimized in C, but you want C to take advantage of the thing that all of your CPUs do, which is something called SIMD, Single Instruction Multiple Data, which is your CPU is capable of taking 8 things at a time, right, in a vector, and adding them up to another vector with 8 things in a single CPU instruction. Right? So if you can take advantage of SIMD, you're immediately 8 times faster. It depends on how big the data type is. It might be 4, might be 8. The other thing that you've got in your computer is you've got multiple processors, multiple cores. So you've probably got, like if this is happening on one core, you've probably got about 4 of those. Okay, so if you're using SIMD, you're 8 times faster. If you can use multiple cores, then you're 32 times faster. And then if you're doing that in C, you might be something like 1,000 times faster, right? And so the nice thing is that when we do that, it's taking advantage of all of these things, okay? Better still, if you do it in PyTorch and your data was created with .CUDA, to stick it on the GPU, then your GPU can do about 10,000 things at a time, right? So that'll be another 100 times faster than C, right? So this is critical to getting good performance, is you have to learn how to write loopless code by taking advantage of these element-wise operations. And like it's a lot more than just plus. I could also use less than, right? And that's going to return 0, 1, 1. Or if we go back to NumPy, false, true, true. And so you can kind of use this to do all kinds of things without looping. So for example, I could now multiply that by A, and here are all of the values of A as long as they're less than B. Or we could take the mean. This is the percentage of values in A that are less than B. Right? So like there's a lot of stuff you can do with this simple idea. But to take it further, right, to take it further than just this element-wise operation, we're going to have to go the next step to something called broadcasting. So let's take a 5-minute break, come back at 2:17, and we'll talk about broadcasting. So, broadcasting. This is the definition from the NumPy documentation of broadcasting. And I'm going to come back to it in a moment rather than reading it now. But let's start by looking at an example of broadcasting. So A is an array with one dimension, also known as a rank 1 tensor, also known as a vector. Okay. We can say A greater than 0. So here we have a rank 1 tensor, right, and a rank 0 tensor. Right? A rank 0 tensor is also called a scalar. A rank 1 tensor is also called a vector. And we've got an operation between the two. Right? Now you've probably done it 1,000 times without even noticing that's kind of weird, right? That you've got these things of different ranks and different sizes. So what is it actually doing, right? Well, what it's actually doing is it's taking that scalar and copying it here, 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 right? And then it's actually going element-wise. 10 is greater than 0, 6 is greater than 0, minus 4 is greater than 0, and giving us back the 3 answers, right? And that's called broadcasting. Broadcasting means copying one or more axes of my tensor to allow it to be the same shape as the other tensor. It doesn't really copy it though. What it actually does is it stores this kind of internal indicator that says pretend that this is a vector of 3 zeros, but it actually just like, rather than kind of going to the next row or going to the next scalar, it goes back to where it came from. If you're interested in learning about this specifically, they set the stride on that axis to be 0. That's a minor advanced concept for those who are curious. So we could do a plus 1, right? It's going to broadcast the scalar 1 to be 1, 1, 1, and then do element-wise addition. We could do the same with a matrix, right? Here's our matrix. 2 times the matrix is going to broadcast 2 to be 2, 2, 2, 2, 2, 2, 2, 2, 2, and then do element-wise multiplication. All right? So that's our kind of most simple version of broadcasting. So here's a slightly more complex version of broadcasting. Here's an array called C, right? So this is a rank 1 tensor. And here's our matrix M from before, our rank 2 tensor. We can add M plus C. Right? So what's going on here? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's M, right? And then C, 10, 20, 30. You can see that what it's done is to add that to each row, right? 11, 22, 33, 14, 25, 36. And so we can kind of figure it seems to have done the same kind of idea as broadcasting a scalar. It's like made copies of it. And then it treats those as if it's a rank 2 matrix. And now we can do element-wise addition. Does that make sense? Right. Now that's, yes, can you pass that, Devon, over there? Thank you.
So, as it's like, by looking at this example, it like copies it down, making new rows. So how would we want to do it if we wanted to get new columns?
I'm so glad you asked. So, instead, we would do this. 10, 20, 30. Right? And then copy that. 10, 20, 30. 10, 20, 30. And now treat that as our matrix. So to get NumPy to do that, we need to not pass in a vector, but to pass in a matrix with one column, right? A rank 2 tensor. Right? So basically, it turns out that NumPy is going to think of a rank 1 tensor for these purposes as if it was a rank 2 tensor which represents a row. Right? So in other words, that it is 1 by 3. Right? So we want to create a tensor which is 3 by 1. There's a couple of ways to do that. One is to use np.expandIms. And if you then pass in this argument, it says, please insert a length 1 axis here, please. So in our case, we want to turn it into a 3 by 1. So if we said expandim c, 1, okay, so if we say expandim c, 1, it changes the shape to 3, 1. So if we look at what that looks like a column. Okay, so if we now go that plus m, you can see it's doing exactly what we hoped it would do, right? Which is to add 10, 20, 30 to the column. 10, 20, 30 to the column, 10, 20, 30 to the column. Okay? Now, because the location of a unit axis turns out to be so important, it's really helpful to kind of experiment with creating these extra unit axes and know how to do it easily. And np.expandims isn't, in my opinion, the easiest way to do this. The easiest way is to index into the tensor with a special index none. And what none does is it creates a new axis in that location of length 1. right? So this is going to add a new axis at the start of length 1. This is going to add a new axis at the end of length 1. Or why not do both? Right? So if you think about it, like a tensor which has like 3 things in it could be of any rank you like, right? You can just add unit axes all over the place. And so that way we can kind of decide how we want our broadcasting to work. So there's a pretty convenient thing in NumPy called broadcast2. And what that does is it takes our vector and broadcasts it to that shape and shows us what that would look like, right? So if you're ever like unsure of what's going on in some broadcasting operation, you can say broadcast2. And so for example here we could say, like rather than 3,3, we could say m.shape, right? And see exactly what's going to happen. And so that's what's going to happen before we add it to m, right? So if we said turn it into a column, that's what that looks like. Make sense? Yeah. So that's kind of like the intuitive definition of broadcasting. And so now hopefully we can go back to that NumPy documentation and understand what it means, right? Broadcasting describes how NumPy is going to treat arrays of different shapes when we do some operation, right? The smaller array is broadcast across the larger array. By smaller array, they mean lower rank tensor, basically. Broadcast across the higher rank tensor, so they have compatible shapes. It vectorizes array operations. So vectorizing generally means like using SIMD and stuff like that so that multiple things happen at the same time. All the looping occurs in C, but it doesn't actually make needless copies of data. It kind of just acts as if it had. Right? So there's our definition. Now in deep learning you very often deal with tensors of rank 4 or more, and you very often combine them with tensors of rank 1 or 2, and trying to just rely on intuition to do that correctly is nearly impossible. So you really need to know the rules. So here are the rules. Okay, here's m.shape, here's c.shape. So the rule are that we're going to compare the shapes of our two tensors element-wise. We're going to look at one at a time. And we're going to start at the end. Right? So look at the trailing dimensions. And then go towards the front. Okay? And so 2 dimensions are going to be compatible when one of these 2 things is true. Right? So let's check, right? We've got our M and C compatible. M is 3, 3. C is 3. Right? So we're going to start at the end, trailing dimensions first, and check. Are they compatible? They're compatible if the dimensions are equal. Okay, so these ones are equal, so they're compatible. Right. All right, let's go to the next one. Uh-oh, we're missing. Right? C is missing something. So what happens if something is missing is we insert a 1. Okay, that's the rule. Right? And so let's now check. Are these compatible? One of them is 1. Yes, they're compatible. Okay? So now you can see why it is that NumPy treats the one-dimensional array as if it is a rank 2 tensor, which is representing a row. It's because we're basically inserting a 1 at the front. Okay? So that's the rule. So for example, this is something that you very commonly have to do, which is you start with like an image of like 256 pixels by 256 pixels by 3 channels, and you want to subtract the mean of each channel. Right? So you've got 256 by 256 by 3, and you want to subtract something of length 3. Right? So yeah, you can do that, absolutely, because 3 and 3 are compatible because they're the same. Right? 256 and empty is compatible because it's going to insert a 1. 256 and empty is compatible because it's going to insert a 1. Right? So you're going to end up with, this is going to be broadcast over all of this axis, and then that whole thing will be broadcast over this axis, and so we'll end up with a 256 by 256 by 3 effective tensor here. Right? So interestingly, like, very few people in the data science or machine learning communities understand broadcasting, and the vast majority of the time, for example, when I see people doing pre-processing for computer vision, like subtracting the mean, they always write loops over the channels, right? And I kind of think like, it's like so handy to not have to do that, and it's often so much faster to not have to do that. So if you get good at broadcasting, you'll have this like super useful skill that very, very few people have. And like it's an ancient skill, you know. It goes all the way back to the days of APL. So APL was from the late 50s. Stands for Programming Language. And Kenneth Iverson wrote this paper called Notation as a Tool for Thought, in which he proposed a new math notation. And he proposed that if we use this new math notation, it gives us new tools for thought and allows us to think things we couldn't before. And one of his ideas was broadcasting, not as a computer programming tool, but as a piece of math notation. And so he ended up implementing this notation as a tool for thought as a programming language called APL. And his son has gone on to further develop that into a piece of software called J, which is basically what you get when you put 60 years of very smart people working on this idea. And with this programming language, you can express very complex mathematical ideas, often just with a line of code or two. And so, I mean, it's great that we have J, but it's even greater that these ideas have found their ways into the languages we all use, like in Python, the NumPy and PyTorch libraries. Right? These are not just little kind of niche ideas. These are like fundamental ways to think about math and to do programming. Like, let me give an example of like this kind of notation as a tool for thought. Let's look. Here we've got C, right? Here we've got C none, right? Notice this is now got 2 square brackets, right? So this is kind of like a one row rank 2 tensor. Here it is as a column. So what is didn't mean to do round ones. Okay, what's that going to do? Have a think about it. Does anybody want to have a go? Can you even talk through your thinking? Okay, can we pass the Jake just over there? Thank you.
Kind of outer product?
Yes, absolutely. So take us through your thinking. How's that going to work?
The diagonal elements can be directly visualized from the squares. 10 cross 10, 20 cross 20, and 30 cross 30. And if we multiply the first row with this column, we can get the first row of the matrix. So finally we'll get a 3 cross 3 matrix.
Yeah. And so to think of this in terms of like those broadcasting rules, we're basically taking this column, right, which is of rank 3, 1, right, and this kind of row, sorry, that's dimension 3, 1, and this row which is of dimension 1, 3, right? And so to make these compatible with our broadcasting rules, right, this one here has to be duplicated 3 times because it needs to match this. Okay, and now this one's going to have to be duplicated 3 times to match this. Okay, and so now I've got 2 matrices to do an element-wise product of. And so, as you say, there is our outer product. Right? Now, the interesting thing here is that suddenly, now that this is not a special mathematical case, but just a specific version of the general idea of broadcasting, we can do like an outer plus, or we can do an outer greater than, right? Or whatever, right? So it's suddenly we've kind of got this concept that we can use to build new ideas, and then we can start to experiment with those new ideas. And so, you know, interestingly, NumPy actually uses this sometimes. For example, if you want to create a grid, this is how NumPy does it, right? Actually, this is kind of the, sorry, let me show you this way. If you want to create a grid, this is how NumPy does it. It actually returns 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4. One as a column, one as a row. So we could say like, okay, that's X grid, comma, Y grid. And now you could do something like, well, I mean, we could obviously go like that, right? And so suddenly we've expanded that out into a grid, right? And so, yeah, it's kind of interesting how like some of these like simple little concepts kind of get built on and built on and built on. So if you lose something like APL or J, it's this whole environment of layers and layers and layers of this. We don't have such a deep environment in NumPy, but you know, you can certainly see these ideas of like broadcasting coming through in simple things like how do we create a grid in NumPy. So yeah, so that's broadcasting. And so what we can do with this now is use this to implement matrix multiplication ourselves. Okay. Now, why would we want to do that? Well, obviously we don't, right? Matrix multiplication has already been handled perfectly nicely for us by our libraries. But very often you'll find in all kinds of areas in machine learning, and particularly in deep learning, that there'll be particular types of linear function that you want to do that aren't quite done for you, right? So for example, there's like whole areas called like tensor regression and tensor decomposition, which are really being developed a lot at the moment, and they're kind of talking about like how do we take like higher rank tensors and kind of turn them into combinations of rows, columns, and faces. And it turns out that when you can kind of do this, you can basically like deal with really high dimensional data structures with not much memory and not much computation time. For example, there's a really terrific library called Tensorly, which does a whole lot of this kind of stuff for you. So it's a really, really important area. It covers like all of deep learning, lots of modern machine learning in general. And so even though you're not going to like define matrix multiplication, you're very likely to want to define some other slightly different tensor product, you know. So it's really useful to kind of understand how to do that. So let's go back and look at our matrix and our 2D array and 1D array, rank 2 tensor, rank 1 tensor. And remember, we can do a matrix multiplication using the @ sign or the old way, np.matmul. Okay. And so what that's actually doing when we do that is we're basically saying, okay, 1 times 10 plus 2 times 20 plus 3 times 30 is 140, right? And so we do that for each row, and we can go through and do the same thing for the next one and for the next one to get our result, right? You could do that in Torch as well. We could make this a little shorter. Okay, same thing. Okay, but that is not matrix multiplication. What's that? Sorry? Element-wise. Specifically, we've got a matrix and a vector, so broadcasting. Okay, good. So we've got, this is element-wise with broadcasting. But notice the numbers it's created, 10, 40, 90, are the exact three numbers that I needed to calculate when I did that first piece of my matrix multiplication. So in other words, if we sum this over the columns, which is axis equals 1, we get our matrix vector product. Okay? So we can kind of do this stuff without special help from our library. So now let's expand this out to a matrix-matrix product. So a matrix-matrix product looks like this. This is this great site called matrixmultiplication.xyz, and it shows us this is what happens when we multiply two matrices. Okay, that's what matrix multiplication is, operationally speaking. So in other words, what we just did there was we first of all took the first column with the first row to get this one, and then we took the second column with the first row to get that one. Right? So we're basically doing the thing we just did, the matrix vector product, we're just doing it twice. Right? Once with this column and once with this column, and then we concatenate the two together. Okay? So we can now go ahead and do that like so. M times the first column dot sum, M times the second column dot sum. And so there are the two columns of our matrix multiplication. Okay? So I didn't want to make our code too messy, so I'm not going to actually use that, but we have it there now if we want to. We don't need to use Torch or NumPy matrix multiplication anymore. We've got our own that we can use using nothing but element-wise operations, broadcasting, and sum. Okay. So this is our logistic regression from scratch class. Again, I just copied it here. Here's where we instantiate the object, copy it to the GPU. We create an optimizer, which we'll learn about in a moment, and we call fit. Okay, so the goal is to now repeat this without needing to call fit. So to do that, we're going to need a loop which grabs a mini batch of data at a time, and with each mini batch of data we need to pass it to the optimizer and say, please try to come up with a slightly better set of predictions for this mini batch. Right? So as we learnt, in order to grab a mini batch of the training set at a time, we have to ask the model data object for the training data loader. We have to wrap it in iter to create an iterator or a generator. And so that gives us our data loader. Okay, so PyTorch calls this a data loader. We actually wrote our own FastAI data loader, but it's basically the same idea. And so the next thing we do is we grab the x and the y tensor, the next one from our data loader, okay, wrap it in a variable to say I need to be able to take the derivative of the calculations using this, because if I can't take the derivative, then I can't get the gradients and I can't update the weights. Right? And I need to put it on the GPU because my module is on the GPU. And so we can now take that variable and pass it to the object that we instantiated, our logistic regression. Remember, our module, we can use it as if it's a function, because that's how PyTorch works. And that gives us a set of predictions, as we've seen before. Okay? So now we can check the loss, and the loss we defined as being a negative log likelihood loss object. Okay, and we're going to learn about how that's calculated in the next lesson. For now, think of it just like root mean squared error, but for classification problems. So we can call that also just like a function. So you can kind of see this very general idea in PyTorch that, you know, kind of treat everything ideally like it's a function. So in this case, we have a loss, negative log likelihood loss object. We treat it like a function. We pass in our predictions, and we pass in our actuals. Right? And again, the actuals need to be turned into a variable and put on the GPU because the loss is specifically the thing that we actually want to take the derivative of. Right? So that gives us our loss. And there it is. That's our loss, 2.43. Okay. So it's a variable. And because it's a variable, it knows how it was calculated. Right? It knows it was calculated with this loss function. It knows that the predictions were calculated with this network. It knows that this network consisted of these operations. And so we can get the gradient automatically. Right? So to get the gradient, we call L.backward. Remember, L is the thing that contains our loss. Right? So L.backward is something which is added to anything that's a variable you can call .backward, and that says, please calculate the gradients. Okay? And so that calculates the gradients and stores them inside basically for each of the weights that was used, each of the parameters that was used to calculate that, it's now stored a .grad. We'll see it later. It's basically stored the gradient, right? So we can then call optimizer.step, and we're going to do this step manually shortly, and that's the bit that says, please make the weights a little bit better, right? And so what optimizer.step is doing is it's saying like, okay, if you had like a really simple function like this, right? Then what the optimizer does is it says, okay, let's pick a random starting point, right? And let's calculate the value of the loss, right? So here's our parameter. Here's our loss, right? Let's take the derivative, right? The derivative tells us which way is down, so it tells us we need to go that direction, okay? And we take a small step. And then we take the derivative again, and we take a small step. Derivative again, take a small step. Derivative again, take a small step, until eventually we're taking such small steps that we stop. Okay, so that's what gradient descent does. Okay, how big a step is a small step? Well, we basically take the derivative here, so let's say derivative there is like 8, right? And we multiply it by a small number, like say 0.01, and that tells us what step size to take. This small number here is called the learning rate, and it's the most important hyperparameter to set. Right? If you pick too small a learning rate, then your steps down are going to be like tiny, and it's going to take you forever. Right? Too big a learning rate, and you'll jump too far. Right? And then you'll jump too far, and you'll diverge rather than converge. Okay? We're not going to talk about how to pick a learning rate in this class, but in the deep learning class we actually show you a specific technique that very reliably picks a very good learning rate. So that's basically what's happening, right? So we calculate the derivatives and we call the optimizer that does a step, in other words, update the weights based on the gradients and the learning rate. We should hopefully find that after doing that, we have a better loss than we did before. So I just reran this and got a loss here of 4.16. And after one step, it's now 4.03. Okay, so it worked the way we hoped it would based on this mini batch. It updated all of the weights in our network to be a little better than they were, as a result of which our loss went down. Okay, so let's turn that into a training loop. Right, we're going to go through 100 steps, grab one more mini batch of data from the data loader, calculate our predictions from our network, calculate our loss from the predictions and the actuals. Every 10 goes, we'll print out the accuracy, just take the mean of whether they're equal or not. One PyTorch specific thing, you have to zero the gradients. Basically, you can have networks where like you've got lots of different loss functions that you might want to add all of the gradients together, right? So you have to tell PyTorch like when to set the gradients back to 0, right? So this just says set all the gradients to 0, calculate the gradients, that's called backward, and then take one step of the optimizer, so update the weights using the gradients and the learning rate. And so once we run it, you can see the loss goes down and the accuracy goes up. Okay, so that's the basic approach. And so next lesson we'll see what that does. All right, we'll look at it in detail. We're not going to look inside here. As I say, we're going to basically take the calculation of the derivatives as a given. Right? But basically, what's happening there, in any kind of deep network, you have kind of like a function that's like, you know, a linear function, and then you pass the output of that into another function that might be like a ReLU, and you pass the output of that into another function that might be another linear layer, and you pass that into another function that might be another ReLU, and so forth. Right? So like these deep networks are just functions of functions of functions. So you could write them mathematically like that. Right? And so all backprop does is it says, let's just simplify this down to the 2 version, is we can say, okay, u equals f of x, right? And so therefore the derivative of g of f of x is we can calculate with the chain rule as being g dash u f dash x, right? And so you can see we can do the same thing for the functions of the functions of the functions. And so when you apply a function to a function of a function, you can take the derivative just by taking the product of the derivatives of each of those layers. Okay? And in neural networks, we call this backpropagation. Okay? So when you hear backpropagation, it just means use the chain rule to calculate the derivatives. And so when you see a neural network defined like here, right? Like if it's defined sequentially, literally all this means is apply this function to the input, apply this function to that, apply this function to that, apply this function to that. Right? So this is just defining a composition of a function to a function to a function to a function. Okay? And so, yeah, so although we're not going to bother with calculating the gradients ourselves, you can now see why it can do it, right? As long as it has internally, you know, it knows like what's the derivative of to the power of, what's the derivative of sine, what's the derivative of plus, and so forth, then our Python code in here is just combining those things together. So it just needs to know how to compose them together with the chain rule, and away it goes. Okay? Okay, so I think we can leave it there for now, and yeah, and in the next class we'll go and we'll see how to write our own optimizer, and then we'll have solved MNIST from scratch ourselves. See you then. Well, welcome back to machine learning. One of the most exciting things this week, almost certainly the most exciting thing this week, is that FastAI is now on pip. So you can pip install FastAI. And so thank you to Prince and to Karem for making that happen. To USF students who had never published a pip package before, and this is one of the harder ones to publish because it's got a lot of dependencies. So it's, probably still easiest just to do the conda env update thing, but a couple of places that it would be handy instead to pip install FastAI would be, well, obviously if you're working outside of the repo and the notebooks, then this gives you access to FastAI everywhere. Also, I believe they submitted a pull request to Kaggle to try and get it added to the Kaggle kernels, so hopefully you'll be able to use it on Kaggle kernels soon. Yeah, you can use it at your work or whatever else. So that's exciting. I mean, I'm not going to say it's like officially released yet. It's still very early, obviously, and you're helping add documentation and all that kind of stuff. But it's great that that's now there. Couple of cool kernels from USF students this week. Thought I'd highlight two that were both from the text normalization competition, which was about trying to take text which was written out, just standard English text. They also had one for Russian, and you're trying to kind of identify things that could be like first, second, third, and say like that's a cardinal number, or this is a phone number, or whatever. And I did a quick little bit of searching, and I saw that there had been some attempts in academia to use deep learning for this, but they hadn't managed to make much progress. And I actually noticed, so Alvira's kernel here, which gets 0.992 on the leaderboard, which I think is like top 20, it's kind of entirely heuristic, and it's a great example of kind of feature engineering. In this case, the whole thing is basically entirely feature engineering. So it's basically looking through and using lots of regular expressions to figure out for each token, what is it, And I think she's done a great job here of kind of laying it all out clearly as to what all the different pieces are and how they all fit together. And she mentioned that she's maybe hoping to turn this into a library, which I think would be great, right? You could use this to grab a piece of text and pull out what are all the pieces in it. It's the kind of thing that the natural language processing community hopes to be able to do without like lots of handwritten code like this. But for now, it'll be interesting to see like what the winners turn out to have done. But I haven't seen machine learning being used really to do this particularly well. Perhaps the best approaches are ones which combine this kind of feature engineering along with some machine learning. But I think this is a great example of effective feature engineering. And this is another USF student who has done much the same thing, got a similar kind of score, but used her own different set of rules. Again, this would get you a good leaderboard position with these as well. So I thought that was interesting to see examples of some of our students entering a competition and getting kind of top 20-ish results by, basically just handwritten heuristics. And this is where, for example, computer vision was 6 years ago still. Basically all the best approaches was a whole lot of like carefully handwritten heuristics, often combined with some simple machine learning. And so I think over time, the field is kind of definitely trying to move towards automating much more of this. And actually, interestingly, very interestingly, in the safe driver prediction competition, which just finished, one of the Netflix prize winners won this competition, and he invented a new algorithm for dealing with structured data, which basically doesn't require any feature engineering at all. So he came first place using nothing but 5 deep learning models and 1 gradient boosting machine. And his basic approach was very similar to what we've been learning in this class so far and what we'll be learning also tomorrow, which is using fully connected neural networks and one-hot encoding, and specifically embedding, which we'll learn about. But he had a very clever technique, which was there was a lot of data in this competition which was unlabeled. So in other words, where they didn't know whether that driver would go under claim or not, or whatever. So unlabeled data. So when you've got some labeled and some unlabeled data, we call that semi-supervised learning. And in real life, most learning is semi-supervised learning. Like in real life, normally you have some things that are labeled and some things that are unlabeled. So this is kind of the most practically useful kind of learning. And then structured data is the most common kind of data that companies deal with day to day. So the fact that this competition was a semi-supervised structured data competition made it incredibly practically useful. And so what his technique for winning this was to do data augmentation, which those of you doing the deep learning course have learned about, which is basically the idea, like if you had pictures, you would like flip them horizontally or rotate them a bit. Data augmentation means creating new data examples, which are kind of slightly different versions of ones you already have. And the way he did it was for each row in the data, he would at random replace 15% of the variables with a different row. So each row now would represent like a mix of like 80%, 85% of the original row, but 15% randomly selected from a different row. And so this was a way of like randomly changing the data a little bit. And then he used something called an autoencoder, which we probably won't study until part 2 of the deep learning course, but the basic idea of an autoencoder is your dependent variable is the same as your independent variable. So in other words, you try to predict your input, which obviously is trivial if you're allowed to the identity transform, for example, trivially predicts the input. But the trick with an autoencoder is to have less activations in at least one of your layers than your input, right? So if your input was like a 100-dimensional vector and you put it through a 100 by 10 matrix to create 10 activations, and then had to recreate the original 100-long vector from that, then you've basically you've had to have compressed it effectively. And so it turns out that that kind of neural network is forced to find correlations and features and interesting relationships in the data, even when it's not labeled. So he used that rather than he didn't do any hand engineering. He just used an autoencoder. So, these are some interesting kind of directions that if you keep going with your machine learning studies, particularly if you do part 2 of the deep learning course next year, you'll learn about. And you can kind of see how feature engineering is going away. And this was just an hour ago. So this is very recent news indeed. But this is one of the most important breakthroughs I've seen in a long time. Okay. So we were working through a simple logistic regression trained with SGD for MNIST. And here's the summary of where we got to. We have nearly built a module, and a training loop from scratch. And we were going to kind of try and finish that. And after we finish that, I'm then going to go through this entire notebook backwards, right? So having gone like top to bottom, we're then going to go back through bottom to top, okay? So, this was that little handwritten nn.module class we created. We defined our loss, we defined our learning rate, and we defined our optimizer. And this is the thing that we're going to try and write by hand in a moment. So that stuff, that we're dealing with from PyTorch, but that we've written ourselves, and this we've written ourselves. So the basic idea was we're going to go through some number of epochs. So let's go through one epoch, right? And we're going to keep track of how much for each mini batch, what was the loss, so that we can report it at the end. We're going to turn our training data loader into an iterator. so that we can loop through every mini batch. And so now we can go ahead and say for tensor in the length of the data loader, and then we can call next to grab the next independent variables and the dependent variables from our data loader, from that iterator. Okay? So then remember, we can then pass the X tensor into our model by calling the model as if it was a function. But first of all, we have to turn it into a variable. Last week, we were typing variable blah.CUDA to turn it into a variable. A shorthand for that is just the capital V. Right? So capital T for a tensor, capital V for a variable. That's just a shortcut in FastAI. Okay? So that returns our predictions. And so the next thing we needed was to calculate our loss, because we can't calculate the derivatives of the loss if we haven't calculated the loss. So the loss takes the predictions and the actuals. Okay, so the actuals again are the Y tensor, and again we have to turn that into a variable. Now, can anybody remind me what a variable is and why we would want to use a variable here?
I think once you turn it into a variable, then it tracks it, so then you can do it backward on it. So you can.
And what? Sorry, when you turn to variable, it
can track like its process of like as you add the function, as the functions start getting layered within each other, you can track it, and then when you do backward on it, it back propagates and does the gradient boosting.
Right. So gradient boosting. Right. So a variable keeps track of all of the steps to get computed. And so there's actually a fantastic tutorial on the PyTorch website. So on the PyTorch website, there's a tutorials section, and there's a tutorial there about AutoGrad. AutoGrad is the name of the automatic differentiation package that comes with PyTorch, and it's an implementation of automatic differentiation. And so the variable class is really the key class here, because that's the thing that turns a tensor into something where we can keep track of its gradients. So basically here they show how to create a variable, do an operation to a variable, and then you can go back and actually look at the grad function, which is the function that it's keeping track of, basically to calculate the gradient, right? So as we do more and more operations to this variable, and the variable's calculated from that variable, it keeps keeping track of it. So later on we can go dot backward and then print dot grad and find out the gradient, right? And so you'll notice we never defined the gradient, we just defined it as being x plus 2 squared times 3, whatever, and it can calculate the gradient. Okay, so that's why we need to turn that into a variable. So L is now a variable containing the loss. So it contains a single number for this mini batch, which is the loss for this mini batch. But it's not just a number. It's a number as a variable, so it's a number that knows how it was calculated. Right? So we're going to append that loss to our array just so we can get the average of it later, basically. And now we're going to calculate the gradient. So L dot backward is the thing that says calculate the gradient. So remember, when we call the network, it's actually calling our forward function. So that's like go through it forward, and then backward is like using the chain rule to calculate the gradients backwards. Okay, and then this is the thing we're about to write, which is update the weights based on the gradients and the learning rate. Okay. Zero grad we'll explain when we write this out by hand. Okay. And so then at the end, we can turn our validation data loader into an iterator, and we can then go through its length, grabbing each x and y out of that, and asking for the score, which we defined up here to be equal to which thing did you predict, which thing was actual, and so check whether they're equal, right? And then the mean of that is going to be our accuracy. Okay? Could you pass that over to Chenxi?
what's the advantage that you convert it into an iterator rather than like use normal, I don't know, Python loop or?
We're using a normal Python loop.
Yeah.
So it's still, this is a normal Python loop. So the question really is like, compared to what, right? So like, the alternative perhaps you're thinking of would be like, we could use like something like a list with an indexer. Okay.
Yeah.
So, the problem there is that we want, there's a few things. I mean, one key one is we want each time we grab a new mini batch, we want it to be random. We want a different shuffled thing. So this, you can actually kind of iterate from forever. You can loop through it as many times as you like. So there's this kind of idea, it's called different things in different languages, but a lot of languages will call it like stream processing. And it's this basic idea that rather than saying I want the third thing or the ninth thing, it's just like I want the next thing, right? It's great for like network programming. It's like grab the next thing from the network. It's great for UI programming. It's like grab the next event whether somebody clicked a button. It also turns out to be great for this kind of numeric programming. So it's like I just want the next batch of data. It means that the data like can be kind of arbitrarily long because we're just grabbing one piece at a time. Yeah, so, I mean, and also, I guess the short answer is, because it's how PyTorch works, PyTorch's data loaders are designed to be called in this way. And then, so Python has this concept of a generator, which is like an different type of generator. I wonder if this is going to be a snake generator or a computer generator. Okay. A generator is a way that you can create a function that, as it says, behaves like an iterator. So like Python has recognized that this stream processing approach to programming is like super handy and helpful and supports it everywhere. So basically anywhere that you use a for in loop, anywhere you use a list comprehension, those things can always be generators or iterators. So by programming this way, we just get a lot of flexibility, I guess. Does that sound about right, Terence? You're the programming language expert. Did you?
Yeah, I was going to say something.
Do you want to grab the box so we can hear? So Terence actually does programming languages for a living, so we should ask him.
Yeah, I mean, the short answer is what you said. You might say something about space, but in this case, that all that data has to be in memory anyway, because we've got...
No, it doesn't have to be in memory. So, in fact, most of the time...
we could pull a mini batch from something.
In fact, most of the time with PyTorch, the mini batch will be read from like separate images spread over your disk on demand. So most of the time it's not in memory.
But in general, you want to keep as little in memory as possible at a time. And so the idea of stream processing also is great because you can do compositions. You can pipe the data to a different machine. You can...
Yeah, the compositions are great. You can grab the next thing from here and then send it off to the next stream, which can then grab it and do something else. Yeah.
Which you guys all recognize, of course, from the command line pipes and redirection. Yes.
Okay. Thanks, Terence. It's the benefit of working with people that actually know what they're talking about. All right. So let's now take that and get rid of the optimizer. Okay. So the only thing that we're going to be left with is the negative log likelihood loss function, which we could also replace. Actually, we have a implementation of that from scratch that Yannette wrote in the notebooks. So it's only one line of code, as we learned earlier. You can do it with a single if statement. Okay. So I don't know why I was so lazy as to include this. So what we're going to do is we're going to, again, grab this module that we've written ourselves, the logistic regression module. We're going to have one epoch, again. We're going to loop through each thing in our iterator, again. We're going to grab our independent and dependent variable for the mini batch, again. Pass it into our network, again. Calculate the loss. So this is all the same as before. But now we're going to get rid of this optimizer.step. And we're going to do it by hand. So the basic trick is, as I mentioned, we're not going to do the calculus by hand. So we'll call l.backward to calculate the gradients automatically. And that's going to fill in our weight matrix. So do you remember when we created our, let's go back and look at the code for, here's that module we built. So the weight matrix for the linear layer weights we called L1W, and for the bias we called L1B. Right? So they were the attributes we created. I've just put them into things called W and B, just to save some typing, basically. So W is our weights, B is our biases. And so the weights, and remember the weights are a variable, and to get the tensor out of the variable, we have to use .data, right? So we want to update the actual tensor that's in this variable. So we say weights.data minus equals, so we want to go in the opposite direction to the gradient. The gradient tells us which way is up, we want to go down. Whatever is currently in the gradients times the learning rate. So that is the formula for gradient descent. Right? So as you can see, it's like as easy a thing as you can possibly imagine. It's like literally update the weights to be equal to whatever they are now minus the gradients times the learning rate, and do the same thing for the bias. Does anybody have any questions about that step in terms of like why we do it or how? Did you have a question? Do you want to grab that?
No, that step. But when we do the next of DL,
the next here?
Yes, yes. So when we reach the end of the loop, how do we grab the next element?
So this is going through each index in range of length. So this is going 0, 1, 2, 3. At the end of this loop, it's going to print out the mean of the validation set, go back to the start of the epoch, at which point it's going to recreate a new iterator. Okay, so basically behind the scenes in Python, when you call iter on this, it basically tells it to like reset its state to create a new iterator. And if you're interested in how that works, the code is all available for you to look at. So we could look at like md.train.dl is a fastai.dataset.model data loader. So we could like take a look at the code of that. So we could take a look at the code of that and see exactly how it's being built, right? And so you can see here, here's the next function, right? Which basically is keeping track of how many times it's been through in the self.i. And here's the iter function, which is the thing that gets called when you create a new iterator. And you can see it's basically passing it off to something else, which is of type data loader, and then you can check out data loader if you're interested to see how that's implemented as well. So the data loader that we wrote basically uses multi-threading to allow it to have multiple of these going on at the same time. It's actually it's really simple. It's only about a screen full of code. So if you're interested in simple multi-threaded programming, it's a good thing to look at. Okay, now, oh, yes.
Why have you wrapped this in a for epoch in range 1, since that'll only run once?
Because in real life, we would normally be running multiple epochs.
Okay.
So like in this case, because it's a linear model, it actually basically trains to as good as it's going to get in one epoch. So if I type 3 here, it actually won't really improve after the first epoch much at all, as you can see, right? But when we go back up to the top, we're going to look at some slightly deeper and more interesting versions, which will take more epochs. So, if I was turning this into a function, I'd be going like, def train model, and one of the things you would pass in is like number of epochs, kind of a thing. Okay, great. So one thing to remember is that when you're creating these neural network layers, and remember this is just, as far as PyTorch is concerned, this is just it's an nn.module. It could be we could be using it as a layer, we could be using it as a function, we could be using it as a neural net. PyTorch doesn't think of those as different things, right? So this could be a layer inside some other network, right? So how do gradients work? So if you've got a layer, which remember is just a bunch of, we can think of it basically as its activations, right? Or some activations that get computed through some either nonlinear activation function or through some linear function. And from that layer, it's very likely that we're then, like, let's say, putting it through a matrix product, right, to create some new layer. And so each one of these, so if we were to grab like one of these activations, right, is actually going to be used to calculate every one of these outputs, right? And so if you want to calculate the derivative, you have to know how this weight matrix impacts that output and that output and that output and that output, right? And then you have to add all of those together to find like the total impact of this, you know, across all of its outputs. And so that's why in PyTorch you have to tell it when to set the gradients to 0, right? Because the idea is that, you know, you could be like having lots of different loss functions or lots of different outputs in your next set of activations or whatever, all adding up, increasing or decreasing your gradients, right? So you basically have to say, okay, this is a new calculation, reset, okay? So here is where we do that, right? So before we do L.backward, we say reset, okay? So let's take our weights. Let's take the gradients, let's take the tensor that they point to, and then 0 underscore. Does anybody remember from last week what underscore does as a suffix in PyTorch? Yeah.
I forgot the language, but basically it changes it within the place right there.
The language is in place.
Oh.
Yeah, exactly. So it sounds like a minor technicality, but it's super useful to remember. Every function pretty much has an underscore version suffix, which does it in place. Yeah, so normally 0 returns a tensor of zeros of a particular size. So 0 underscore means replace the contents of this with a bunch of zeros. Okay. All right. So that's it, right? So that's like SGD from scratch, and if I get rid of my menu bar, we can officially say it fits within a screen. Okay. So of course we haven't got our definition of logistic regression here. That's another half a screen. But basically, there's not much to it. Yes, Vash.
So later on, if we have to do this more, the gradient, is it because you might find like a wrong minima, local minima? Is that why? So you have to kick it out, and that's why you have to do it multiple times when the surfaces get more complicated.
Why do you need multiple epochs? Is that your question? Well, I mean, a simple way to answer that would be, let's say our learning rate was tiny, right? Then it's just not going to get very far, right? There's nothing that says going through one epoch is enough to get you all the way there. So then it'd be like, okay, well, let's increase our learning rate. And it's like, yeah, sure, we'll increase our learning rate, but who's to say that the highest learning rate that learns stably is enough to learn this as well as it can be learned? And for most data sets, for most architectures, one epoch is very rarely enough to get you to the best result you can get to. You know, linear models are just, they're very nicely behaved, you know, so you can often use higher learning rates and learn them more quickly. Also, you can't like generally get as good at accuracy, so there's not as far to take them either. So yeah, doing one epoch is going to be the rarity. All right, so let's go backwards. So going backwards, we're basically going to say, all right, let's not write those 2 lines again and again and again. Let's not write those 3 lines again and again and again. Let's have somebody do that for us, right? So that's the only difference between that version and this version is rather than saying .0 ourselves, rather than saying minus gradient times LR ourselves, these are wrapped up for us, okay? There is another wrinkle here, which is this approach to updating the weights is actually pretty inefficient. It doesn't take advantage of momentum and curvature, and so in the DL course we learn about how to do momentum from scratch as well. Okay, so if we actually just use plain old SGD, then you'll see that this learns much slower. So now that I've typed just plain old SGD here, this is now literally doing exactly the same thing as our slow version, so I have to increase the learning rate. Okay, there we go. So this is now the same as the one we wrote by hand. So then, all right, let's do a little bit more stuff automatically. Let's not, given that every time we train something, we have to loop through epoch, loop through batch, do forward, get the loss, zero the gradient, do backward, do a step of the optimizer. Let's put all that in a function. Okay? And that function is called fit. All right, there it is. Okay, so let's take a look at fit. Fit, go through each epoch, go through each batch, do one step, keep track of the loss, and at the end calculate the validation. Right? And so then step So if you're interested in looking at this stuff's all inside fastai.model. And so here is step, right? Zero the gradients, calculate the loss. Remember, PyTorch tends to call it criterion rather than loss, right? Do backward. And then there's something else we haven't learned here, but we do learn the deep learning course, which is gradient clipping. So you can ignore that. Right? So you can see now, like, all the stuff that we've learnt when you look inside the actual frameworks. That's the code you see. Okay? So that's what fit does. And so then the next step would be like, okay, well, this idea of like having some weights and a bias and doing a matrix product and addition, let's put that in a function. This thing of doing the log softmax, let's put that in a function. And then the very idea of like first doing this and then doing that, this idea of like chaining functions together, let's put that into a function. And that finally gets us to that. Okay, so sequential simply means do this function, take the result, send it to this function, etc. Right? And linear means create the weight matrix, create the biases. Okay, so that's it, right? So we can then, as we started to talk about, like turn this into a deep neural network by saying, rather than sending this straight off into 10 activations, let's put it into say 100 activations. We could pick whatever number we like. Put it through a ReLU to make it nonlinear. Put it through another linear layer, another ReLU, and then our final output with our final activation function, right? And so this is now a deep network. So we could fit that. And this time now, because it's like deeper, I'm actually going to run a few more epochs, right? And you can see the accuracy increasing, right? So if you try and increase the learning rate here, it's like 0.1. Further, it actually starts to become unstable. Now I'll show you a trick. This is called learning rate annealing. The trick is this. When you're trying to fit to a function, right, you've been taking a few steps. Step, step, step. As you get close to the middle, like get close to the bottom, your steps probably want to become smaller, right? Otherwise, what tends to happen is you start finding you're doing this, right? And so you can actually see it here, right? It got 93, 94 and a bit, 94.6, 94.8, like it's kind of starting to flatten out, right? Now that could be because it's kind of done as well as it can, or it could be that it's going backwards and forwards. So what is a good idea is later on in training is to decrease your learning rate and to take smaller steps. Okay, that's called learning rate annealing. So there's a function in FastAI called set learning rates. You can pass in your optimizer and your new learning rate, and see if that helps, right? And very often it does. About an order of magnitude. In the deep learning course, we learn a much better technique than this to do this all automatically and at a more granular level. But if you're doing it by hand, like an order of magnitude at a time is what people generally do. So you'll see people in papers talk about learning rate schedules. This is like a learning rate schedule. So this schedule, just a moment, Erica, I'll just come to Ernest first, has got us to 97, right? And I tried kind of going further, and we don't seem to be able to get much better than that. So yeah, so here we've got something where we can get 97% accuracy. Yes, Erica?
So it seems like you changed the learning rate to something very small.
10 times smaller than we started with. So we had 0.1, now it's 0.01. Yep.
But that makes the whole model train really slow. So I was wondering if you can make it so that it changes dynamically as it approaches closer to the minima.
Yeah, pretty much. Yeah, so that's some of the stuff we learn in the deep learning course, is these more advanced approaches. Yeah. Divesh.
So how it is different from using Adam Optimizer or something?
That's the kind of stuff we can do. I mean, you still need annealing. As I say, we do this kind of stuff in the deep learning course. So for now, we're just going to stick to standard SGD.
I had a question about the data loading.
Yeah.
I know it's a FastAI function, but could you go into a little bit of detail of how it's creating batches, how it's loading data, and how it's making those decisions?
Sure. It'd be good to ask that on Monday night so we can talk about it in detail in the deep learning class. But let's do the quick version here. So basically, there's a really nice design in PyTorch where they basically say, let's create a thing called a data set, right? And a data set is basically something that looks like a list. It has a length, right? And so that's like how many images are in the data set. And it has the ability to index into it like a list, right? So if you had like D equals data set, you can do length D, and you can do D of some index, right? That's basically all a data set is, as far as PyTorch is concerned. And so you start with a data set, so it's like, okay, D3 gives you the third image, or whatever. And so then the idea is that you can take a data set and you can pass that into a constructor for a data loader. And that gives you something which is now iterable, right? So you can now say iter DL, and that's something that you can call next on. And what that now is going to do is, when you do this, you can choose to have shuffle on or shuffle off. Shuffle on means give me random mini batch. Shuffle off means go through it sequentially. And so what the data loader does now when you say next is it basically, assuming you said shuffle equals true, is it's going to grab, if you've got a batch size of 64 random integers between 0 and length, and call this 64 times to get 64 different items and jam them together. So FastAI uses the exact same terminology and the exact same API. We just do some of the details differently. So specifically, particularly with computer vision, you often want to do a lot of not so much pre-processing, data augmentation, like flipping, changing the colors a little bit, rotating. Those turn out to be really computationally expensive. Even just reading the JPEGs turns out to be computationally expensive. So PyTorch uses an approach where it fires off multiple processes to do that in parallel. Whereas the FastAI library instead does something called multi-threading, which is can be a much faster way of doing it. Yes, Yannette.
So
an epoch is a real epoch in the sense that all of the elements, so it's a shuffle at the beginning of the epoch, something like that?
Yeah, yeah. I mean, not all libraries work the same way. Some do sampling with replacement, some don't. We actually, the FastAI library hands off the shuffling off to the actual PyTorch version, and I believe the PyTorch version, yeah, actually shuffles and an epoch covers everything once, I believe. Okay, now the thing is, when you start to get these bigger networks, potentially you're getting quite a few parameters, right? So I want to ask you to calculate how many parameters there are, but let's remember here we've got 28 by 28 input into 100 output, and then 100 into 100, and then 100 into 10, right? And then for each of those, we've got weights and biases. So we can actually do this. Net.parameters returns a list where each element of the list is a matrix, or actually a tensor, of the parameters for that, not just for that layer, but if it's a layer with both weights and biases, that would be 2 parameters, right? So basically returns us a list of all of the tensors containing the parameters. Num elements in PyTorch tells you how big that is, right? So if I run this, here is the number of parameters in each layer. So I've got 784 inputs, and the first layer has 100 outputs, so therefore the first weight matrix is of size 78,400. Okay, and the first bias vector is of size 100. Okay, and then the next one is 100 by 100. Okay, and there's 100, and then the next one is 100 by 10, and then there's my bias. Okay, so there's the number of elements in each layer, and if I add them all up, it's nearly 100,000. Okay, and so I'm possibly at risk of overfitting here, right? So we might want to think about using regularization. So a really simple, common approach to regularization in all of machine learning is something called L2 regularization. And it's super important, super handy. You can use it with just about anything, right? And the basic idea, anyway, L2 regularization, the basic idea is this. Normally we'd say our loss is equal to, let's just do RMSE to keep things kind of simple. It's equal to our predictions minus our actuals, squared, and then we sum them up, take the average, take the square root. Okay? So what if we then want to say, you know what, like if I've got lots and lots of parameters, don't use them unless they're really helping enough, right? Like if you've got 1 million parameters and you only really needed 10 parameters to be useful, just use 10, right? So how could we like tell the loss function to do that? And so basically what we want to say is, hey, if a parameter is 0, that's no problem. It's like it doesn't exist at all. So let's penalize a parameter for not being 0. Right? So what would be a way we could measure that? How can we like calculate how un-zero our parameters are? Can you pass that to Chen Shi, please, Ernest?
You calculate the average of all the parameters. That's my first thought.
Can't quite be the average. Close.
Oh,
yes, Taylor.
Yeah.
Yes, you figured it out. Okay.
I think if we assuming all of our data has been normalized, standardized, however you want to call it, we want to check that they're significantly different from 0, right? Would that be
not
the
the
idea?
data, the parameters.
The parameters
weights.
rather would be significantly different.
And the
from
parameters
0.
don't have to be normalized or anything; they're just calculated.
Right.
Yes. So significantly different from 0.
Right. I just meant assuming that the data has been normalized so that we can compare them on the same scale.
Yeah, got it. Yeah, right.
And then those that are not significantly different from 0, we can probably just drop.
And I think Chen Shi's going to tell us how to do that. Yeah. You just figured it out, right?
The mean of the absolute value.
Could do that. That would be called L1, which is great. So L1 would be the absolute value of the weights average. Right. L2 is actually the sum.
Square root sum of squares.
Yeah, exactly. So we just take we don't even have to square root. So we just take the squares of the weights themselves. And then, like, we want to be able to say, like, okay, how much do we want to penalize not being 0, right? Because if we actually don't have that many parameters, we don't want to regularize much at all. If we've got heaps, we do want to regularize a lot, right? So then we put a parameter here, right? Except I have a rule in my classes, which is never to use Greek letters. So normally people use alpha. I'm going to use A, okay? So this is some number which you often see something around kind of 1e neg 6 to 1e neg 4-ish, right? Now, we actually don't care about the loss. When you think about it, we don't actually care about the loss, other than like maybe to print it out. What we actually care about is the gradient of the loss. Okay, so the gradient of that, right, is that, right? So there are two ways to do this. We can actually modify our loss function to add in this square penalty, or we could modify that thing where we said weights equals weights minus gradient times learning rate to subtract that as well, right? Well, actually, sorry, to add that as well. And these are kind of basically equivalent, but they have different names. This is called L2 regularization, right? This is called weight decay. So in the neural network literature, you know, that version kind of was how it was first posed in the neural network literature, whereas this other version is kind of how it was posed in the statistics literature. And yeah, you know, they're equivalent. As we talked about in the deep learning class, it turns out they're not exactly equivalent because when you have things like momentum and atom, it can behave differently. And 2 weeks ago, a researcher figured out a way to actually do proper weight decay in modern optimizers, and one of our FastAI students just implemented that in the FastAI library, so FastAI is now the first library to actually support this properly. So anyway, so for now, let's do the version which PyTorch calls weight decay, but actually it turns out, based on this paper 2 weeks ago, is actually L2 regularization. It's not quite correct, but it's close enough. So here we can say weight decay is 1e neg 3. So this is going to set our penalty multiplier A to 1e neg 3, and it's going to add that to the loss function. Okay? And so let's make a copy of these cells, just so we can compare. Hope this actually works. Okay, and we'll set this running. Okay, so this is now optimizing. Oh, except if you actually... So I've made a mistake here, which is I didn't rerun this cell. This is an important thing to kind of remember. Since I didn't rerun this cell, here when it created the optimizer and said net.parameters, it started with the parameters that I had already trained, right? So I actually hadn't recreated my network. Okay, so I actually need to go back and rerun this cell first to recreate the network, then go through and run this. Okay, there we go. So let's see what happens. So you might notice something kind of counterintuitive here, which is that that's our training error, right? Now you would expect our training error with regularization to be worse. Does that make sense, right? Because we're penalizing parameters that specifically can make it better. And yet, actually it started out better, not worse. So why could that be? So the reason that can happen is that if you have a function that looks like that, right, it takes potentially a really long time to train. Whereas if you have a function that kind of looks more like that, it's going to train a lot more quickly. And there are certain things that you can do which sometimes just like can take a function that's kind of horrible and make it less horrible. And sometimes weight decay can actually make your functions a little more nicely behaved. And that's actually happened here. So like I just mentioned that to say like don't let that confuse you, right? Like weight decay really does penalize the training set. And look, so strictly speaking, the final number we get to for the training set shouldn't end up being better, but it can train sometimes more quickly, right? Yes, can you pass it to Chenchi?
I don't get it.
Okay.
Why making it faster? Like the time matters? Like the training time matters?
No, this is after one epoch,
yeah.
Right? So after one epoch, and congratulations for saying, I don't get it. That's like the best thing anybody can say. You know, so helpful. This here was our training without weight decay. Okay. And this here is our training with weight decay. Okay. So this is not related to time. This is related to just an epoch. Right? After one epoch, my claim was that you would expect the training set, all other things being equal, to have a worse loss with weight decay because we're penalizing it. You know, this has no penalty, this has a penalty. So the thing with the penalty should be worse. And I'm saying, oh, it's not. That's weird, right? And so the reason it's not is because in a single epoch, it matters a lot as to whether you're trying to optimize something that's very bumpy or whether you're trying to optimize something that's kind of nice and smooth. If you're trying to optimize something that's really bumpy, like imagine in some high-dimensional space, right, you end up kind of rolling around through all these different tubes and tunnels and stuff, you know, whereas if it's just smooth, you just go boom. Right? It's like imagine a marble rolling down a hill where one of them you've got like what's it called? Lombard Street in San Francisco. It's like backwards, forwards, backwards, forwards. It takes a long time to drive down the road, right? Where else, you know, if you kind of took a motorbike and just went straight over the top, you just go boom, right? So whether, so kind of the shape of the loss function surface, you know, impacts or kind of defines how easy it is to optimize. And therefore, how far can it get in a single epoch? And based on these results, it would appear that weight decay here has made it this function easier to optimize.
So just to make sure, it's the penalizing is making the optimizer more than likely to reach the global minimum rather than...
No, I wouldn't say that. My claim actually is that at the end, it's probably going to be less good on the training set. And indeed, this does look to be the case. At the end, after 5 epochs, our training set is now worse with weight decay. Now that's what I would expect, right? I would expect, like, if you actually find, like, I never use the term global optimum because it's just not something we have any guarantees about. We don't really care about. We just care, like, where do we get to after a certain number of epochs? We hope that we found somewhere that's like a good solution. And so by the time we get to like a good solution, the training set with weight decay, the loss is worse because it's a penalty, right? But on the validation set, the loss is better, right? Because we penalized the training set in order to kind of try and create something that generalizes better. So we've got more parameters, you know, the parameters that are kind of pointless are now 0, and it generalizes better, right? So all we're saying is that it just got to a good point after one epoch, is really all we're saying.
So is it always true?
No. If by it you mean does weight decay always make the function surface smoother? No, it's not always true. But it's like, it's worth remembering that if you're having trouble training a function, adding a little bit of weight decay may help.
And so by regularizing the parameters, what it does is it smoothens out the loss functions.
I mean, it's not why we do it. You know, the reason why we do it is because we want to penalize things that aren't 0 to say, like, don't make this parameter a high number unless it's really helping the loss a lot, right? Set it to 0 if you can, because setting as many parameters to 0 as possible means that it's going to generalize better, right? It's like the same as having a smaller network, right? So that's why we do it. But it can change how it learns as well. So let's, okay, just one moment, Erica. So I just wanted to check how we actually went here. So after the second epoch, yeah. So you can see here, it really has helped, right? After the second epoch, before we got to 97% accuracy, now we're nearly up to about 98% accuracy, right? And you can see that the loss was 0.08 versus 0.13, right? So adding regularization has allowed us to find a, 3% versus 2%, so like a 50% better solution. Yes, Erica.
So there are two pieces to this, right? One is L2 regularization and the weight decay. Right?
No, so my claim was they're the same thing,
okay.
Right? So weight decay is the version if you just take the derivative of L2 regularization, you get weight decay. So you can implement it either by changing the loss function with a squared loss penalty, or you can implement it by adding the weights themselves as part of the gradient. Okay. Yeah, I was just going to finish the questions. Yes, can you pass that to Devesh?
Can we use regularization in convolution layer as well?
Absolutely. So a convolution layer just is weights. So, yep.
Jeremy, can you explain why you thought you needed weight decay in this particular problem?
Not easily. I mean, other than to say it's something that I would always try.
You're overfitting Thunder.
Well,
maybe
yeah. I mean, okay. So even if yeah, okay. That's a good point, Yannette. So if my training loss was higher than my validation loss, then I'm underfitting, right? So there's definitely no point regularizing, right? If like that would always be a bad thing. That would always mean you need like more parameters in your model. In this case, I'm overfitting. That doesn't necessarily mean regularization will help, but it's certainly worth trying. Thank you, Nat. That's a great point. There's one more question. Yep. Tyler, do you want to pass it over there?
So how do you choose the optimal number of epoch?
You do my deep learning course. That's a long story and lots of
Do you do it by heuristically, or is there any?
It's a bit of both.
Okay.
We just don't, as I say, we don't have time to cover best practices in this class. We're going to learn the kind of fundamentals. Yeah. Okay. So let's take a 6-minute break and come back at 11:10. All right. So something that we cover in great detail in the deep learning course, but is like really important to mention here, is that the secret, in my opinion, to kind of modern machine learning techniques is to massively over-parameterize the solution to your problem, right? Like as we've done here, we've got like 100,000 weights when we only had a small number of 28 by 28 images. And then use regularization. Okay, it's like the direct opposite of how nearly all statistics and learning was done for decades before, and still most kind of like senior lecturers at most universities in most areas have this background where they've learned the correct way to build a model is to like have as few parameters as possible, right? And so hopefully we've learned two things so far. One is we can build very accurate models even when they have lots and lots of parameters, like a random forest has a lot of parameters, and this here deep network has a lot of parameters, and they can be accurate, right? And we can do that by either using bagging or by using regularization. Okay, and regularization in neural nets means either weight decay, also known as kind of L2 regularization, or dropout, which we won't worry too much about here. So like it's a very different way of thinking about building useful models. And like I just wanted to kind of warn you that once you leave this classroom, like even possibly when you go to the next faculty member's talk, like there'll be people at USF as well who are entirely trained in the world of like models with small numbers of parameters. You know, your next boss is very likely to have been trained in the world of like models with small numbers of parameters. The idea that they are somehow more pure or easier or better or more interpretable or whatever. I am convinced that that is not true. Probably not ever true. Certainly very rarely true. And that actually models with lots of parameters can be extremely interpretable, as we learnt from our whole lesson of random forest interpretation. You can use most of the same techniques with neural nets, but with neural nets they're even easier, right? Remember how we did feature importance by randomizing a column to see how changes in that column would impact the output? Well, that's just like a kind of dumb way of calculating its gradient. How much does varying this input change the output? With a neural net, we can actually calculate its gradient. Right? So with PyTorch, you could actually say, what's the gradient of the output with respect to this column? Right? You can do the same kind of thing to do a partial dependence plot with a neural net. And, you know, I'll mention for those of you interested in making a real impact, nobody's written basically any of these things for neural nets. Right? So that whole area needs like libraries to be written, blog posts to be written, you know. Some papers have been written, but only in very narrow domains like computer vision. As far as I know, nobody's written the paper saying, here's how to do structured data, neural networks, you know, interpretation methods. So it's a really exciting, big area. So what we're going to do, though, is we're going to start with applying this with a simple linear model. And this is mildly terrifying for me because we're going to do NLP, and our NLP faculty expert is in the room. So David, just yell at me if I screw this up too badly. And so NLP refers to, you know, any kind of modeling where we're working with natural language text, right? And interestingly enough, we're going to look at a situation where a linear model is pretty close to the state of the art for solving a particular problem. It's actually something where I actually surpassed the state of the art in this using a recurrent neural network a few weeks ago. But this is actually going to show you pretty close to the state of art with a linear model. We're going to be working with the IMDb data set. So this is a data set of movie reviews. You can download it by following these steps. And once you download it, you'll see that you've got a train and a test directory. And in your train directory, you'll see there's a negative and a positive directory. And in your positive directory, you'll see there's a bunch of text files. And here's an example of a text file. So somehow we've managed to pick out a story of a man who has unnatural feelings for a pig as our first choice. That wasn't intentional, but it'll be fine. We're going to look at these movie reviews. And for each one, we're going to look to see whether they were positive or negative. So they've been put into one of these folders. They were downloaded from IMDb, the movie database and review site. The ones that were strongly positive went in positive, strongly negative went in negative, and the rest they didn't label at all. So these are only highly polarized reviews. So in this case, you know, we have an insane violent mob, which unfortunately is too absurd, too off-putting. Those in the area will be turned off. So the label for this was a 0, which is negative. Okay? So this is a negative review. So in the FastAI library, there's lots of little functions and classes to help with most kinds of domains that you do machine learning on. For NLP, one of the simple things we have is texts from folders. That's just going to go ahead and go through and find all of the folders in here with these names and create a labeled data set. And, you know, don't let these things ever stop you from understanding what's going on behind the scenes, right? We can grab its source code, and as you can see, it's tiny, you know, it's like 5 lines. Okay, so I don't like to write these things out in full, you know, but hide them behind little functions so you can reuse them. But basically, it's just going to go through each directory, and then within that, go through each directory, and then go through each file in that directory, and then stick that into this array of texts and figure out what folder it's in and stick that into the array of labels. Okay, so that's how we basically end up with something where we have an array of the reviews and an array of the labels. Okay, so that's our data. So our job will be to take that and to predict that. Okay, and the way we're going to do it is we're going to throw away like all of the interesting stuff about language, which is the order in which the words are in. Right? Now, this is very often not a good idea, but in this particular case, it's going to turn out to work like not too badly. So let me show you what I mean by like throwing away the order of the words. Like normally, the order of the words matters a lot. If you've got a not before something, then that not refers to that thing, right? So, but the thing is, when in this case we're trying to predict whether something's positive or negative, if you see the word absurd appear a lot, right, then maybe that's a sign that this isn't very good. So, you know, cryptic, maybe that's a sign that it's not very good. So the idea is that we're going to turn it into something called a term document matrix, where for each document, i.e. each review, we're just going to create a list of what words are in it, rather than what order they're in. So let me give an example. Can you see this okay? Okay. So here are 4 movie reviews that I made up. This movie is good, the movie is good. They're both positive. This movie is bad, the movie is bad. They're both negative, right? So I'm going to turn this into a term document matrix. So the first thing I need to do is create something called a vocabulary. A vocabulary is a list of all the unique words that appear. Okay? So here's my vocabulary. This movie is good, the bad. That's all the words. Okay? And so now I'm going to take each one of my movie reviews and turn it into a vector of which words appear and how often do they appear. Right? And in this case, none of my words appear twice. So this movie is good has those 4 words in it, whereas this movie is bad has those 4 words in it. Okay? So this is called a term document matrix. Right? And this representation we call a bag of words representation. Right? So this here is a bag of words representation of the review. It doesn't contain the order of the text anymore. It's just a bag of the words. What words are in it? It contains bad, is, movie, this. Okay? So that's the first thing we're going to do is we're going to turn it into a bag of words representation. And the reason that this is convenient for linear models is that this is a nice rectangular matrix that we can like do math on. Okay? And specifically, we can do a logistic regression. And that's what we're going to do, is we're going to get to a point where we do a logistic regression. Before we get there, though, we're going to do something else, which is called Naive Bayes. Okay. So sklearn has something which will create a term document matrix for us. It's called count vectorizer. Okay, so we'll just use it. Now, in NLP, you have to turn your text into a list of words, and that's called tokenization. Okay, and that's actually non-trivial, because like if this was actually this movie is good, dot, right? Or if it was this movie is good, like how do you deal with like that punctuation? Or perhaps more interestingly, what if it was this movie isn't good, right? So how you turn a piece of text into a list of tokens is called tokenization, right? And so a good tokenizer would turn this movie isn't good into this. This space, quote, movie space, is space and good space. Right, so you can see in this version here, if I now split this on spaces, every token is either a single piece of punctuation or like this suffix nt is considered like a word. Right, that's kind of like how we would probably want to tokenize that piece of text. Because you wouldn't want good full stop to be like an object, right? Because there's no concept of good full stop, right? Or double quote movie is not like an object, right? So tokenization is something we hand off to a tokenizer. FastAI has a tokenizer in it that we can use. So this is how we create our term document matrix with a tokenizer. sklearn has a pretty standard API, which is nice. I'm sure you've seen it a few times now before. So once we've built some kind of model, we can kind of think of this as a model, just-ish. This is just defining what it's going to do. We can call fit transform to do that, right? So in this case, fit transform is going to create the vocabulary, okay, and create the term document matrix based on the training set. Transform is a little bit different. That says use the previously fitted model, which in this case means use the previously created vocabulary. We wouldn't want the validation set and the training set to have, you know, the words in different orders in the matrices, right? Because then they'd like to have different meanings. So this is here saying use the same vocabulary to create a bag of words for the validation set. Could you pass that back, please?
What if the validation set has different set of words other than training set?
Yeah, that's a great question. So generally most of these kind of vocab creating approaches will have a special token for unknown. Sometimes you can, you'll also say like, hey, if a word appears less than 3 times, call it unknown. But otherwise it's like, yeah, if you see something you haven't seen before, call it unknown. So that would just become a column in the bag of words is unknown. Good question. All right, so when we create this term document matrix of the training set, we have 25,000 rows because there are 25,000 movie reviews. And there are 75,132 columns. What does that represent? What does that mean? There are 75,132. What? Can you pass that to Devesh? Just a moment. Can you pass that to Devesh?
All vocabulary?
Yeah, go on. What do you mean?
So, like the number of words, union of number of words?
The number of unique words, yeah, exactly. Good. Okay. Now, most documents don't have most of these 75,000 words, right? So we don't want to actually store that as a normal array in memory because it's going to be very wasteful. So instead we store it as a sparse matrix, right? And what a sparse matrix does is it just stores it as something that says whereabouts are the non-zeros, right? So it says like, okay, document number 1, word number 4 appears and it has 4 of them, you know. Document 1, term number 123 has that appears and it's a 1, right? And so forth. That's basically how it's stored. There's actually a number of different ways of storing, and if you do Rachel's computational linear algebra course, you'll learn about the different types and why you choose them and how to convert and so forth. But they're all kind of something like this, right? And you don't really, on the whole, have to worry about the details. The important thing to know is it's efficient, okay? And so we could grab the first review, right? And that gives us 75,000 long, sparse, one row long matrix, okay? With 93 stored elements. So in other words, 93 of those words are actually used in the first document, okay? We can have a look at the vocabulary by saying vectorizer.get feature names. That gives us the vocab. And so here's an example of a few of the elements of get feature names. I didn't intentionally pick the one that had Aussie, but, you know, that's the important words, obviously. I haven't used the tokenizer here. I'm just splitting on space, so this isn't quite the same as what the vectorizer did. But to simplify things, let's grab a set of all the lowercase words. By making it a set, we make them unique. So this is roughly the list of words that would appear, right? And that length is 91, which is pretty similar to 93, and just the difference will be that I didn't use a real tokenizer. Yeah, right? So that's basically all that's been done there. It's kind of created this unique list of words and mapped them. We could check by calling vectorizer.vocabulary underscore to find the ID of a particular word. So this is like the reverse map of this one, right? So this is like integer to word. Here is word to integer. And so we saw absurd appeared twice in the first document. So let's check train term doc 0, 1297. There it is as 2, right? Or else, unfortunately, Aussie didn't appear in the unnatural relationship with a pig movie. So 0, 5000 is 0. Okay? So that's our term document matrix. Yes.
So does it care about the relative relationship between the words?
As in the ordering of the words? No, we've thrown away the orderings. That's why it's a bag of words. Okay. And I'm not claiming that this is like necessarily a good idea. What I will say is that like the vast majority of NLP work that's been done over the last few decades generally uses this representation because we didn't really know much better. Nowadays, increasingly, we're using recurrent neural networks instead, which we'll learn about in our last deep learning lesson of part 1. But sometimes this representation works pretty well, and it's actually going to work pretty well in this case. Okay, so, and in fact, you know, most, like back when I was at Fastmail, my email company, a lot of the spam filtering we did used this next technique, Naive Bayes, which uses a bag of words approach, which is kind of like, you know, if you're getting a lot of email containing the word Viagra, and it's always been a spam, and you never get email from your friends talking about Viagra, then it's very likely something that says Viagra, regardless of the detail of the language, is probably from a spammer. All right? So that's the basic theory about like classification using a term document matrix. Okay, so let's talk about Naive Bayes. And here's the basic idea. We're going to start with our term document matrix, right? And these first two is our corpus of positive reviews. These next two is our corpus of negative reviews. And so here's our whole corpus of all reviews. Right. So what I could do is now to create a probability. I'm going to call these, as we tend to call these more generically, features rather than words, right? This is a feature. Movie is a feature. Is a feature, right? So it's kind of more now like machine learning language. A column is a feature. We often call those F in Naive Bayes. So we can basically say the probability that you would see the word this, given that the class is 1, given that it's a positive review, is just the average of how often do you see this in the positive reviews, right? Now, we've got to be a bit careful, though, because if you never ever see a particular word in a particular class, right? So if I've never received an email from a friend that said Viagra, right? That doesn't actually mean the probability of a friend sending me an email about Viagra is 0. It's not really 0, right? I hope I don't get an email, you know, from Terence tomorrow saying like, Jeremy, you probably could use this, you know, advertisement for Viagra, but you know, it could happen, and you know, I'm sure it'd be in my best interest. Yeah. So what we do is we say, actually, what we've seen so far is not the full sample of everything that could happen. It's like a sample of what's happened so far. So let's assume that the next email you get actually does mention Viagra and every other possible word, right? So basically, we're going to add a row of 1s. Okay? So that's like the email that contains every possible word. So that way, nothing's ever infinitely unlikely. Okay, so I take the average of all of the times that this appears in my positive corpus plus the ones. Okay, so that's like the probability that feature equals this appears in a document given that class equals 1. And so not surprisingly, here's the same thing for probability that this feature this appears given class equals 0. Right? Same calculation except for the 0 rows. And obviously these are the same because this appears twice in the positives, sorry, once in the positives and once in the negatives. Okay? Let's just put this back to what it was. All right. So we can do that for every feature, for every class. Right. So our trick now is to basically use Bayes' rule to kind of fill this in. So what we want is the probability that given that I've got this particular document, so somebody sent me this particular email or I have this particular IMDb review, what's the probability that its class is equal to, I don't know, positive, right? So for this particular movie review, what's the probability that its class is positive, right? And so we can say, well, that's equal to the probability that we got this particular movie review, given that its class is positive, multiplied by the probability that any movie review's class is positive, divided by the probability of getting this particular movie review. All right, that's just Bayes' rule. Okay, and so we can calculate all of those things, but actually what we really want to know is it more likely that this is class 0 or class 1, right? So what if we actually took probability that it's class 1 and divided by probability that it's class 0? What if we did that, right? And so then we could say, like, okay, if this number's bigger than 1, then it's more likely to be class 1. If it's smaller than 1, it's more likely to be class 0, right? So in that case, we could just divide this whole thing, right, by the same version for class 0, right, which is the same as multiplying it by the reciprocal. And so the nice thing is now that's going to put a probability D on top here, which we can get rid of, right, and a probability of getting the data given class 0 down here, and the probability of getting class 0 here, right? And so if we basically, what that means is we want to calculate the probability that we would get this particular document given that the class is 1 times the probability that the class is 1 divided by the probability of getting this particular document given the class is 0 times the probability that the class is 0. So the probability that the class is 1 is just equal to the average of the labels, right? Probability that the class is 0 is just 1 minus that, right? So so there are those two numbers, right? I've got an equal amount of both, so it's both 0.5. What is the probability of getting this document given that the class is 1? Can anybody tell me how I would calculate that? Can somebody pass that back, please? Thank you, Devesh.
Look at all the documents which have class equal to 1.
Uh-huh.
And 1 divided by that will give you...
So remember, though, it's going to be for a particular document. So, for example, we'd be saying, like, what's the probability that this review is positive? Right? So you're on the right track, but what we're going to have to do is we're going to have to say, let's just look at the words it has, and then multiply the probabilities together for class equals 1, right? So the probability that a class 1 review has this is 2/3, the probability it has movie is 1, is 1, and good is 1. So the probability it has all of them is all of those multiplied together. Kinda. And the kinda, Tyler, why is it not really? Can you pass that to Tyler? I'm so glad you look horrified and skeptical.
Word choice is not independent,
Thank
so
you.
that
Right.
doesn't hold.
So nobody can call Tyler naive, because the reason this is naive Bayes is because this is what happens if you take Bayes' theorems in a naive way, and Tyler is not naive. Anything but, right? So naive Bayes says, let's assume that if you have this movie is bloody stupid, I hate it, but the probability of hate is independent of the probability of bloody, is independent of the probability of stupid, right? Which is definitely not true, right? And so naive Bayes ain't actually very good, but I'm kind of teaching it to you because it's going to turn out to be a convenient piece for something we're about to learn later.
And it often works pretty well.
It's okay, right? I mean, I would never choose it. Like, I don't think it's better than any other technique that's equally fast and equally easy. But, you know, it's a thing you can do. And it's certainly going to be a useful foundation. So here is our calculation, right, of the probability that this document is, that we get this particular document, assuming it's a positive review. Here's the probability, given it's a negative, and here's the ratio, and this ratio is above 1, so we're going to say, I think that this is probably a positive review. Okay, so that's the Excel version. And so you can tell that I let Yannet touch this because it's got LaTeX in it. We've got actual math. So here is the same thing. The log count ratio for each feature F, for each word F. And so here it is written out as Python. Okay, so our independent variable is our term document matrix. Our dependent variable is just the labels of the Y. So using NumPy, this is going to grab the rows where the dependent variable is 1. Okay? And so then we can sum them over the rows to get the total word count for that feature across all the documents. Right? Plus 1. Right? Because that's the email. Terrence is totally going to send me something about Viagra today, I can tell. That's that.
Already done.
Yeah. Okay. So do the same thing for the negative reviews. Right? And then, of course, it's nicer to take the log, right? Because if we take the log, then we can add things together rather than multiply them together. And once you multiply enough of these things together, it's going to get kind of so close to 0 that you'll probably run out of floating point, right? So we take the log of the ratios, and then we can, as I say, we then multiply that, or in log we subtract that add that to the ratio of the class, the whole class probabilities. All right. So in order to say for each document, multiply the Bayes probabilities by the counts, we can just use matrix multiply. Okay. And then to add on the log of the class ratios, we can just use plus B. And so we end up with something that looks a lot like our logistic regression, right? But we're not learning anything, right? Not in kind of a SGD point of view. We're calculating it using this theoretical model, okay? And so, as I said, we can then compare that as to whether it's bigger or smaller than 0, not 1 anymore, because we're now in log space, right? And then we can compare that to the mean, and we say, okay, that's 80% accurate, 81% accurate, right? So naive Bayes, is not nothing. It gave us something. Okay. It turns out that this version, where we're actually looking at how often a word appears, like absurd appeared twice, it turns out, at least for this problem and quite often, it doesn't matter whether absurd appeared twice or once. All that matters is that it appeared. So what people tend to try doing is to say, take the term document matrix and go dot sign. Dot sign replaces anything positive with 1 and anything negative with -1. We don't have any negative counts, obviously. So this binarizes it. So it says, I don't care that you saw absurd twice. I just care that you saw it, right? So if we do exactly the same thing with the binarized version, then you get a better result, okay? Okay, now this is the difference between theory and practice, right? In theory, naive Bayes sounds okay, but it's naive, unlike Tyler, it's naive, right? So what Tyler would probably do would instead say, rather than assuming that I should use these coefficients R, why don't we learn them? Does that sound reasonable, Tyler? Yeah, okay. So let's learn them. So we can, we can totally learn them. So let's create a logistic regression, right? And let's fit some coefficients. And that's going to literally give us something with exactly the same functional form that we had before, but now rather than using a theoretical R and a theoretical B, we're going to calculate the two things based on logistic regression, and that's better. Okay? So, so it's kind of like, yeah, why do something based on some theoretical model? Because theoretical models are never going to be as accurate pretty much as a data-driven model, right? Because theoretical models, unless you're dealing with some, I don't know, like physics thing or something where you're like, okay, this is actually how the world works. There really is no, I don't know, we're working in a vacuum and this is the exact gravity and blah, 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 right? But in most of the real world, this is how things are. Like, it's better to learn your coefficients and calculate them. Yes, Yannette.
Jeremy, what's this dual equal true?
I was hoping you'd ignore and not notice, but you saw it. Basically, in this case, our term document matrix is much wider than it is tall. There is a reformulation, almost a mathematically equivalent reformulation of logistic regression that happens to be a lot faster when it's wider than it is tall. So the short answer is, if you don't put that here, anytime it's wider than it is tall, put dual equals true and it'll run. This runs in like 2 seconds. If you don't have it here, it'll take a few minutes. So like in math, there's this kind of concept of dual versions of problems, which are kind of like equivalent versions that sometimes work better for certain situations. Okay, here is the binarized version, right? And it's about the same, right? So you can see I've fitted it with the sign of the term doc matrix and predicted it with this, right? Now the thing is that this is going to be a coefficient for every term. There was about 75,000 terms in our vocabulary. And that seems like a lot of coefficients given that we've only got 25,000 reviews. So maybe we should try regularizing this. So we can use regularization built into sklearn's logistic regression class, which is C is the parameter that they use. This is slightly weird, a smaller parameter is more regularization, right? So that's why I used 1E8 to basically turn off regularization here. So if I turn on regularization, set it to 0.1, then now it's 88%. Okay, which makes sense. You know, you would think like 75,000 parameters for 25,000 documents, you know, is likely to overfit. Indeed, it did overfit. So this is adding L2 regularization to avoid overfitting. I mentioned earlier that as well as L2, which is looking at the weight squared, there's also L1, which is looking at just the absolute value of the weights, right? I was kind of pretty sloppy in my wording before. I said that L2 tries to make things zero. That's kind of true, but if you've got two things that are highly correlated, then L2 regularization will like move them both down together. It won't make one of them zero and one of them non-zero, right? So L1 regularization actually has the property that it'll try to make as many things zero as possible, whereas L2 regularization has a property that it tends to try to make kind of everything smaller. We actually don't care about that difference in really any modern machine learning because we very rarely try to directly interpret the coefficients. We try to understand our models through interrogation using the kind of techniques that we've learned. The reason that we would care about L1 versus L2 is simply like which one ends up with a better error on the validation set. Okay, and you can try both. With sklearn's logistic regression, L2 actually turns out to be a lot faster because you can't use dual equals true unless you have L2. So, you know, and L2 is the default. So I didn't really worry too much about that difference here. So you can see here if we use regularization and binarized, we actually do pretty well. Okay? So, yes, can you pass that back to Davi, please?
Before we learned about elastic net, right, like combining L1 and L2, can you do that?
Yeah, you can do that.
Is that?
But I mean, it's like, you know, with deeper models, yeah, I've never seen anybody find that useful. Okay, so the last thing I'll mention is that you can, when you do your count vectorizer, wherever that was, when you do your count vectorizer, you can also ask for n-grams, right? By default, we get unigrams, that is single words. But if we say n-gram range equals 1, 3, that's also going to give us bigrams and trigrams, by which I mean, if I now say, okay, let's go ahead and do the count vectorizer, get feature names, now my vocabulary includes a bigram, right, by vast, by vengeance, and a trigram, by vengeance, full stop, by Vera Miles, right? So this is now doing the same thing, but after tokenizing, it's not just grabbing each word and saying that's part of our vocabulary, but each 2 words next to each other and each 3 words next to each other. And this turns out to be like super helpful in like taking advantage of bag of word approaches, because we now can see like the difference between like, you know, not good versus not bad versus not terrible, right? Or even like double quote, good, double quote, which is probably going to be sarcastic, right? So using trigram features actually is going to turn out to make both naive Bayes and logistic regression quite a lot better. It really takes us quite a lot further and makes them quite useful.
I have a question about the tokenizers. So you are saying some max features. So how are these bigrams and trigrams selected?
Right. So since I'm using a linear model, I didn't want to create too many features. I mean, it actually worked fine even without max features. I think I had something like, I can't remember, 70 million coefficients. It still worked, right? But just, there's no need to have 70 million coefficients. So if you say max features equals 800,000, the count vectorizer will sort the vocabulary by how often everything appears, whether it be unigram, bigram, trigram, and it will cut it off after the first 800,000 most common n-grams. N-gram is just the generic word for unigram, bigram, and trigram. So that's why the train term doc.shape is now 25,000 by 800,000. And like, if you're not sure what number this should be, I just picked something that was really big and, you know, didn't worry about it too much, and it seemed to be fine. Like, it's not terribly sensitive. All right. Okay, well, that's we're out of time. So what we're going to see next week, and by the way, you know, we could have replaced this logistic regression with our PyTorch version, and next week we'll actually see something in the FastAI library that does exactly that. But also what we'll see tomorrow, is how to combine logistic regression and naive Bayes together to get something that's better than either. And then we'll learn how to move from there to create a deeper neural network to get a pretty much state-of-the-art result for structured learning. All right, so we'll see you then. So let's start by reviewing kind of what we've learned about optimizing multi-layer functions with SGD. And so the idea is that we've got some data, and then we do something to that data for example, we multiply it by a weight matrix. And then we do something to that. For example, we put it through a softmax or a sigmoid. And then we do something to that, such as do a cross-entropy loss or a root mean squared error loss. Okay, and that's going to like give us some scalar. Oh. So this is going to have no hidden layers. This has got a linear layer, a nonlinear activation being a softmax, and a loss function being a root mean squared error or a cross entropy. All right, and then we've got our input data. Input, linear, nonlinear, loss. So, for example, if this was sigmoid or softmax, and this was cross entropy, then that would be logistic regression. So it's still yeah. Cross entropy? Yeah, let's do that next. Sure. For now, think of it like, think of root mean squared error. Same thing, some loss function. Okay, for now. We'll look at cross entropy again in a moment. So how do we calculate the derivative of that with respect to our weights, right? So really, it would probably be better if we said x comma w here, because it's really a function of the weights as well. And so we want the derivative of this with respect to our weights. Oh, sorry, I put it in the wrong spot. G f of x comma w. I just screwed up, that's all. That's why that didn't make sense. All right. So to do that, we just basically we do the chain rule. So we just say that this is equal to h of u, and u equals u equals g of v, and v equals f of x. So we can just rewrite it like that, right? And then we can do the chain rule. So we can say that's equal to h dash, the derivative is h dash u by g dash v by f dash x. Happy with all that so far? Okay. So in order to take the derivative with respect to the weights, therefore, we just have to calculate that derivative with respect to w using that exact formula. So if we had in there, so d of all that, dw, would be that. Yeah. So then if we, went further here and had like another linear layer, right? Let's give us a bit more room. Another linear layer, I don't know, W2, right? So we now got another linear layer. There's no difference to now calculate the derivative with respect to all of the parameters. We can still use the exact same chain rule, right? So don't think of the multi-layer network as being like things that occur at different times. It's just a composition of functions. And so we just use the chain rule to calculate all the derivatives at once. They're just a set of parameters that happen to appear in different parts of the function, but the calculus is no different. So to calculate this with respect to W1 and W2, it's just, you just increase W, you can just now just call it W and say W1 is all of those weights. So the result, that's a great question. So what you're going to have then is a list of parameters, right? So here's W1, and like it's probably some kind of higher rank tensor, like if it's a convolutional layer, it'll be like a rank 3 tensor or whatever, but we can flatten it out, right? We'll just make it a list of parameters. There's W1. Here's W2, right? It's just another list of parameters, right? And here's our loss, which is a single number. So therefore, our derivative is just a vector of that same length, right? It's how much does changing that value of W affect the loss? How much does changing that value of W affect the loss, right? So you can basically think of it as a function like, y equals ax1 plus bx2 plus c, right? And say like, oh, what's the derivative of that with respect to a, b, and c? And you would have 3 numbers, the derivative with respect to a, and b, and c. And that's all this is, right? It's a derivative with respect to that weight, and 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 that weight. To get there, inside the chain rule, we had to calculate, and I'm not going to go into detail here, but we had to calculate like Jacobians. So like the derivative, when you take a matrix product, is you've now got something where you've got like a weight matrix, and you've got an input vector. These are the activations from the previous layer, right? And you've got some new output activations, right? And so now you've got to say like, okay, for this particular weight, how does changing this particular weight change this particular output? And how does changing this particular weight change this particular output? And so forth. So you kind of end up with these higher dimensional tensors showing like for every weight, how does it affect every output, right? But then by the time you get to the loss function is going to have like a mean or a sum or something. So they're all going to get added up in the end, And so this kind of thing, like, I don't know, it drives me a bit crazy to try and calculate it out by hand or even think of it step by step, because you tend to have like, you just have to remember for every input in a layer, for every output in the next layer, you're going to have to count for every weight, for every output, you're going to have a separate gradient. One good way to look at this is to learn to use PyTorch's like .grad attribute and .backward method manually, and like look up the PyTorch tutorials. And so you can actually start setting up some calculations with a vector input and a vector output, and then type .backward, and then say type .grad, and like look at it, right? And then do really small ones with just 2 or 3 items in the input and output vectors, and like make the operation like +2 or something, and like see what the shapes are, make sure it makes sense. Yeah, because it's kind of like this vector matrix calculus is not like introduces 0 new concepts to anything you learned in high school, like strictly speaking, but getting a feel for how these shapes move around, I find took a lot of practice. The good news is you almost never have to worry about it. Okay, so we were talking about then using this kind of logistic regression for NLP. And before we got to that point, we were talking about using Naive Bayes for NLP. And the basic idea was that we could take a document, right, a review, like this movie is good, and turn it into a bag of words representation consisting of the number of times each word appears, right? And we call this the vocabulary. This is the unique list of words. Okay, and we used the sklearn count vectorizer to automatically generate both the vocabulary, which in sklearn they call the features, and to create the bag of words representations, and the whole group of them then is called a term document matrix. Okay, and we kind of realized that we could calculate the probability that a positive review contains the word this by just averaging the number of times this appears in the positive reviews, and we could do the same for the negatives, right? And then we could take the ratio of them to get something which, if it's greater than 1, was a word that appeared more often in the positive reviews, or less than 1 was a word that appeared more often in the negative reviews. Okay, and then we realized, using Bayes' rule that and taking the logs, that we could basically end up with something where we could add up the logs of these plus the log of the ratio of the probabilities that things are in class 1 versus class 0, and end up with something we can compare to 0. If it's a bit greater than 0, then we can predict a document is positive, or if it's less than 0, we can predict the document is negative. And that was our Bayes rule, right? So we kind of did that from math first principles, and I think we agreed that the naive in Naive Bayes was a good description, because it assumes independence when it's definitely not true. But it was an interesting starting point, and I think it was interesting to observe when we actually got to the point where, like, okay, now we've calculated the ratio of the probabilities, and took the log, and now rather than multiplying them together, of course, we have to add them up. And when we actually wrote that down, we realized, like, oh, that is, just a standard weight matrix product plus a bias, right? And so then we kind of realized, like, oh, okay, so like if this is not very good accuracy, 80% accuracy, why not improve it by saying, hey, we know other ways to calculate a bunch of coefficients and a bunch of biases, which is to learn them in a logistic regression, right? So in other words, this is the formula we use for a logistic regression. And so why don't we just create a logistic regression and fit it? Okay, and it's going to give us the same thing, but rather than coefficients and biases which are theoretically correct based on, this assumption of independence and based on Bayes' rule, there'll be the coefficients and biases that are actually the best in this data. All right? So that was kind of where we got to. And so the kind of key insight here is, like, just about everything I find in machine learning ends up being either like a tree or, a bunch of matrix products and nonlinearities, right? Like everything seems to end up kind of coming down to the same thing, including, as it turns out, Bayes' rule, right? And then it turns out that nearly all of the time, then whatever the parameters are in that function, nearly all the time it turns out that they're better learnt than calculated based on theory, right? And indeed, that's what happened when we actually tried learning those coefficients. We got, 85%. Okay. So then we noticed that we could also, rather than take the whole term document matrix, we could instead just take the ones and zeros for presence or absence of a word. And, sometimes it was, this equally as good. But then we actually tried something else, which is we tried adding regularization. And with regularization, the binarized approach turned out to be a little better. Right? So then regularization was where we took the loss function. Right, and again, let's start with RMSE, and then we'll talk about cross-entropy. Loss function was our predictions minus our actuals, sum that up, take the average, plus a penalty. Okay, and so this specifically is the L2 penalty. If this instead was the absolute value of W, then that would be the L1 penalty. Okay. We also noted that we don't really care about the loss function per se. We only care about its derivative. That's actually the thing that updates the weights. So we can, because this is a sum, we can take the derivative of each part separately. And so the derivative of this part was just that, right? And so we kind of learnt that even though these are mathematically equivalent, they have different names. This version is called weight decay, and it's kind of what's used, that term is used in the neural net literature. Okay. So cross entropy, on the other hand, it's just another loss function like root mean squared error. But it's specifically designed for classification, right? And so here's an example of binary cross entropy. So let's say this is our, is it a cat or a dog? So let's just say, is cat 1 or a 0? So cat, cat, dog, dog, cat. And these are our predictions. This is the output of our final layer of our neural net or our logistic regression or whatever. All right. Then all we do is we say, okay, let's take the actual times the log of the prediction, and then we add to that 1 minus actual times the log of 1 minus the prediction, and then take the negative of that whole thing. All right? So I suggested to you all that you tried to kind of write the if statement version of this, so hopefully you've done that by now, otherwise I'm about to spoil it for you. So this was y times log y plus 1 minus y times log 1 minus y, right? And negative of that. Okay. So who wants to tell me how to write this as an if statement? All right, Chen-Shi, hit me.
I'll give it a try. So
yes, sir.
If y equal to 1, then return log y. Otherwise, else return log 1 minus y.
Good.
Because that's the thing in the brackets, and you take c minus something.
Good. So the key insight Chen-Shi is using is that y has two possibilities, 1 or 0. Okay? And so very often the math can hide the key insight, which I think happens here until you actually think about what the values it can take are, right? So that's all it's doing. It's saying either give me that or give me that, right? Could you pass that to the back, please, Chen-Shi?
Right, if I'm missing something, but do you not need two variables in that statement? Because you've got y. Shouldn't it be like a y hat and a y or something?
Oh, yeah. Thank you. As usual, it's me missing something. Okay. Okay, and so then the multi-category version is just the same thing, but you're saying, it for different, more than just y equals 1 or 0, but y equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, for instance. Okay. And so that, that loss function has well, you can figure it out yourself, and particularly simple derivative. And it also, another thing you could play with at home, if you like, is like thinking about how the derivative looks when you add a sigmoid or a softmax before it. It turns out it all turns out very nicely because you've got an XB thing going into a loggy thing, so you end up with, very well-behaved derivatives. The reason, I guess, there's lots of reasons that people use RMSE for regression and cross-entropy for classification, but most of it comes back to this statistical idea of a best linear unbiased estimator, and based on the likelihood function, it kind of turns out that these have some nice statistical properties. It turns out, however, in practice, root mean squared error in particular, the properties are perhaps more theoretical than actual, and actually nowadays using the absolute deviation rather than the sum of squareds deviation can often work better. So in practice, like everything in machine learning, I normally try both. For a particular data set, I'll try both loss functions and see which one works better. Unless, of course, it's a Kaggle competition, in which case you're told how Kaggle's going to judge it, and you should use the same loss function as Kaggle's evaluation metric. All right. So yeah, so this is really the key insight, is like, hey, let's not use theory, but instead learn things from the data, and we hope that we're going to get better results, particularly with regularization, we do. And then I think the key regularization insight here is, hey, let's not like try to reduce the number of parameters in our model, but instead like use lots of parameters and then use regularization to figure out which ones are actually useful. Right? And so then we took that a step further by saying, hey, given we can do that with regularization, let's create lots more features by adding bigrams and trigrams. Bigrams like by vast and by vengeance, and trigrams like by vengeance full stop and by 0 miles. Right? And, just to keep things a little faster, we limited it to 800,000 features, but, even with the full 70 million features, it works just as well, and it's not a hell of a lot slower. So we created a term document matrix, again, using the full set of n-grams for the training set, the validation set. And so now we can go ahead and say, okay, our labels is the training set labels as before. Our independent variables is the binarized term document matrix as before. And then let's fit a logistic regression to that. And do some predictions, and we get 90% accuracy. So this is looking pretty good. Okay. So the logistic regression, let's go back to our naive Bayes, right? In our naive Bayes, we have this term document matrix, and then for every feature we're calculating the probability of that feature occurring if it's class 1, that probability of that feature occurring if it's class 2, and then the ratio of those two, right? And in the paper that we're actually basing this off, they call this P, this Q, and this R, right? Maybe I should just fill that in. P, Q, maybe then we'll say probability to make it more obvious. Okay. And so then we kind of said, hey, let's not use these ratios as the coefficients in that matrix multiply, but let's instead like try and learn some coefficients, so maybe start out with some random numbers, and then try and use stochastic gradient descent to find slightly better ones. So you'll notice, some important features here. The R vector is a vector of rank 1, and its length is equal to the number of features. And of course, our logistic regression coefficient matrix is also of rank 1, and length equal to the number of features, right? And we're saying like there are kind of two ways of calculating the same kind of thing. Right? One based on theory, one based on data. So here is like some of the numbers in R, right? Remember it's using the log, so these numbers which are less than 0 represent things which are more likely to be negative, and these ones here are more likely, this one here is more likely to be positive. And so here's e to the power of that, and so these are the ones we can compare to 1 rather than to 0. So I'm going to do something that hopefully is going to seem weird. And so first of all, I'm going to say what we're going to do, and then I'm going to try and describe why it's weird, and then we'll talk about why it may not be as weird as we first thought. So here's what we're going to do. We're going to take our term document matrix, and we're going to multiply it by R. So what that means is we can do it here in Excel, right? So we're going to say, let's grab everything in our term document matrix and multiply it by the equivalent value in the vector of R. Right? So this is like a broadcasted element-wise multiplication, not a matrix multiplication. Okay? And that's what that does. Okay? So here is the value of the term document matrix times R. In other words, everywhere that a 0 appears there, a 0 appears here, and every time a 1 appears here, the equivalent value of R appears here. So we haven't really changed much, right? We've just kind of changed the ones into something else, into the R's from that feature, right? And so what we're now going to do is we're going to use this as our independent variables instead in our logistic regression. Okay, so here we are, multiply x NB, x naive Bayes version is x times R, and now let's do a logistic regression fitting using those independent variables. And let's then do that for the validation set, okay, and get the predictions, and lo and behold, we have a better number. Okay, so let me explain why this hopefully seems surprising. Given that we're just multiplying... Oh, I picked out the wrong ones. I should have said R, not coef. Okay, that's actually R. I got the wrong number. Okay, so that's our independent variables, right? And then the logistic regression has come up with some set of coefficients. Let's pretend for a moment that these are the coefficients that it happened to come up with, right? We could now say, well, let's not use this set of independent variables, but let's use the original binarized feature matrix, right? And then divide all of our coefficients by the values in R, and we're going to get exactly the same result mathematically. So, we've got our x naive Bayes version of the independent variables, and we've got some set of weights, some set of coefficients. I call it W, right? W1, let's say, where it's found like this is a good set of coefficients for making our predictions from, right? But x and b is simply equal to x times, as in element-wise, times R, right? So in other words, this is equal to x times R times the weights. And so, like, we could just change the weights to be that, right? And get the same number. So this ought to mean that the change that we made to the dependent variable shouldn't have made any difference, because we can calculate exactly the same thing without making that change. So there's the question. Why did it make a difference? So in order to answer this question, I'm going to try and get you all to try and think about this. In order to answer this question, you need to think about, like, okay, what are the things that aren't mathematically the same? Why is it not identical? What are the reasons? Like, come up with some hypotheses. What are some reasons that maybe we've actually ended up with a better answer. And to figure that out, we need to first of all start with like, well, why is it even a different answer? Why is that different to that? This is subtle. All right, what do you think?
I was just wondering if there was two different kinds of multiplications. You said that one is the element-wise multiplication.
No, they do end up mathematically being the same.
Okay.
Pretty much. There's a minor wrinkle, but it's not that. It's not some order operations thing. Worth a try. Kenchi? You are on a roll today, so let's see how you go.
I feel like the features are less correlated to each other.
I mean, I've made a claim that these are mathematically equivalent. So what are you saying really? You know, why are we getting different answers? It's good. Keep on coming up with hypotheses. We need lots of wrong answers before we start finding it's the right ones. It's like that, you know, warmer, hotter, colder, you know. Ernest, are you going to get us hotter?
Does it have anything to do with the regularization?
Yes.
And is it the fact that when you...
So let's start there, right? So Ernest's point here is like, okay, Jeremy, you've said they're equivalent, but they're equivalent outcomes, right? But you went through a process to get there, and that process included regularization, and they're not necessarily equivalent regularization. Like our loss function has a penalty. So yeah, help us think through, Ernest, how much that might impact things.
Well, this is me being kind of dumb, but I'm just noticing that the numbers are bigger in the ones that have been weighted by the naive Bayes R weights. And so
these are bigger. And some are smaller, some are bigger.
Right,
yeah.
but
there are some bigger ones.
Like the variance between the columns is much higher now.
The variance is bigger. Yeah. I think that's a very interesting insight.
Okay, that's all I got.
Okay. So build on that. Prince has been on a roll all month, so hit us.
Actually, I'm not sure, but
that's fine.
Is it also considering the dependency of different words? Is that why it is performing better, rather than all words independent of each other?
Not really. I mean, it's you know, again, theoretically, these are creating mathematically equivalent outputs. So they're not doing something different, except, as Ernest mentioned, they're getting impacted differently by regularization. So what's regularization, right? Regularization is we start out with our that was the weirdest thing. I forgot to go into screenwriting mode, and it just turns out that you can actually write in Excel, and I had no idea that was true. I still use screenwriting mode, so I don't kill up my spreadsheet. I never tried. So our loss was equal to like our cross entropy loss, you know, based on the predictions, or the predictions and the actuals, right, plus our penalty. So if your weights are large, right, then that piece gets bigger, right, and it drowns out that piece, right? But that's actually the piece we care about, right? We actually want it to be a good fit. So we want to have as little regularization going on as we can get away with. We want to have less weights. So here's the thing, right? Our value, yes, can you pass it over here?
When you say less weights, did you mean lesser weights?
I do, yeah. Yeah, and I kind of use the two words a little equivalently, which is not quite fair, I agree. But the idea is that weights that are pretty close to zero are kind of not there. Yeah. So here's the thing. Our values of R, you know, and I'm not a Bayesian weenie, but I'm still going to use the word prior, right? They're kind of like a prior. So like we think that the different levels of importance and positive or negative of these different features might be something like that, right? We think that like bad, you know, might be more correlated with negative than good, right? So our kind of implicit assumption before was that we have no priors. So in other words, when we said squared weights, we're saying a non-zero weight is something we don't want to have, right? But actually, I think what I really want to say is that differing from the naive Bayes expectation is something I don't want to do, right? Like only vary from the naive Bayes prior unless you have good reason to believe otherwise, right? And so that's actually what this ends up doing, right? We end up saying, you know what? We think this value is probably 3, right? And so if you're going to like make it a lot bigger or a lot smaller, right, that's going to create the kind of variation in weights that's going to cause that squared term to go up, right? So if you can, you know, just leave all these values about similar to where they are now, right? And so that's what the penalty term is now doing, right? The penalty term, when our inputs is already multiplied by r, is saying penalize things where we're varying it from our naive Bayes prior. Can you pass that there?
Why multiply only with a r, not constant like r square or something like that, when the variance would be much higher this time?
Because our prior comes from an actual theoretical model, right? So I said, like, I don't like to rely on theory, but if I have some theory, then, you know, maybe we should use that as our starting point rather than starting off by assuming everything's equal. So our prior said, hey, we've got this model called naive Bayes, and the naive Bayes model said, if the naive Bayes assumptions were correct, then R is the correct coefficient, right, in this specific formulation. That's why we picked that, because our prior is based on that theory. Okay, so this is a really interesting insight which I never really see covered, which is this idea is that we can use these, like, you know, traditional machine learning techniques, we can imbue them with this kind of Bayesian sense by starting out, you know, incorporating our theoretical expectations into the data that we give our model, right? And when we do so, that then means we don't have to regularize as much. And that's good, right? Because if we regularize a lot, like, let's try it. Let's go back to, you know, here's our, remember the way they do it in the sklearn logistic regression is this is the reciprocal of the amount of regularization penalty. So we'll kind of add lots of regularization by making it small. So that, like, really hurts. That really hurts our accuracy, because now it's trying really hard to get those weights down. The loss function is overwhelmed by the need to reduce the weights, and the need to make it predictive is kind of now seems totally unimportant, right? So, so by kind of starting out and saying, you know what, don't push the weights down so that you end up ignoring the terms, but instead push them down so that you try to get rid of, you know, ignore differences from our expectation based on the naive Bayes formulation. So that ends up giving us a very nice result, which actually was originally, this technique was originally presented, I think about 2012. Chris Manning, who's a terrific NLP researcher up at Stanford, and Cedar Wang, who I don't know, but I assume is awesome because his paper is awesome, they basically came up with this idea. And what they did was they compared it to a number of other approaches on a number of other data sets. So one of the things they tried is this one, is the IMDb data set, right? And so here's naive Bayes SVM on bigrams. And as you can see, this approach outperformed the other linear-based approaches that they looked at, and also some restricted Boltzmann machine kind of neural net-based approaches they looked at. Now, nowadays, there are better ways. There are better ways to do this. And in fact, in the deep learning course, we showed a new state-of-the-art result that we just developed at FastAI that gets well over 94%. But still, like particularly for a linear technique that's easy, fast, and intuitive, this is pretty good. And you'll notice when they did this, they only used bigrams, and I assume that's because I looked at their code and it was kind of pretty slow and ugly. I figured out a way to optimize it a lot more, as you saw, and so we were able to use trigrams, and so we get quite a lot better. So we got 91.8 versus their 91.2. But other than that, it's identical. Also, they used a support vector machine, which is almost identical to a logistic regression in this case. So there's some minor differences, right? So I think that's a pretty cool result. And, I will mention, what you get to see here in class is the result of like many weeks and often many months of research that I do. And so I don't want you to think like this stuff is obvious. It's not at all. Like reading this paper, there's no description in the paper of like why they use this model, how it's different, why they thought it works. It took me a week or two to even realize that it's kind of like mathematically equivalent to a normal logistic regression. And then a few more weeks to realize that the difference is actually in the regularization. Like this is kind of like machine learning, as I'm sure you've noticed from the Kaggle competitions you enter, like you come up with 1,000 good ideas, 999 of them, no matter how confident you are, they're going to be great. They always turn out to be shit, And then finally, after 4 weeks, one of them finally works and kind of gives you the enthusiasm to spend another 4 weeks of misery and frustration. This is the norm, right? And like, for sure, the best practitioners I know in machine learning all share one particular trait in common, which is they're very, very tenacious. Also known as stubborn and bloody-minded, right? Which is definitely a reputation I seem to have, probably fair. Along with another thing, which is that they're all very good coders. They're very good at turning their ideas into code. So this was like a really interesting experience for me working through this a few months ago to try and like figure out how to at least, how to explain why this at the time kind of state-of-the-art result exists. And so once I figured that out, I was actually able to build on top of it and make it quite a bit better. And I'll show you what I did. And this is where it was very, very handy to have PyTorch at my disposal, because I was able to kind of create something that was customized just the way that I want it to be, and also very fast by using the GPU. So here's the kind of FastAI version of the NB SVM. Actually, my friend Stephen Merity, who's a terrific researcher in NLP, has christened this the NB SVM++, which I thought was lovely. So here is even though there is no SVM, it's a logistic regression, but as I said, nearly exactly the same thing. So let me first of all show you like the code. So this is like, we try to like, once I figure out like, okay, this is like the best way I can come up with to do a linear bag of words model, I kind of embed it into FastAI so you can just write a couple of lines of code. So the code is basically, hey, I want to create a data class for text classification. I want to create it from a bag of words, right? Here is my bag of words. Here are my labels. Here is the same thing for the validation set, and use up to 2,000 unique words per review, right, which is plenty. So then from that model data, construct a learner, which is kind of the FastAI generalization of a model, which is based on a dot product of naive Bayes, and then fit that model, and then do a few epochs, and after 5 epochs, I was already up to 92.2, right? So this is now, like, you know, getting quite well above this linear baseline. So let me show you the code for that. So the code is like horrifyingly short. That's it, right? And it'll also look, on the whole, extremely familiar, right? There's a few tweaks here. Pretend this thing that says embedding, pretend it actually says linear. Okay, I'm going to show you embedding in a moment. Pretend it says linear. So we've got basically a linear layer where the number of features coming with the number of features as the rows. And remember, sklearn features means number of words, basically. And then for each row, we're going to create one weight, which makes sense, right? For like a logistic regression, so not for each row, for each word. Each word has one weight. And then we're going to be multiplying it by the R values. So for each word, we have one R value per class. So I actually made this so this can handle like not just positive versus negative, but maybe figuring out like which author created this work. There could be 5 or 6 authors, whatever, right? And basically, we kind of use those linear layers to get the value of the weight and the value of the R, and then we take the weight times the R and then sum it up, and so that's just a dot product, okay? So just a simple dot product, just as we would do for any logistic regression, and then do the softmax. So the very minor tweak that we add to get the better result is this. The main one really is this here, this plus something, right? And the thing I'm adding is, it's a parameter, but I pretty much always use this value, 0.4. So what does this do? So what this is doing is it's again kind of changing the prior, right? So if you think about it, even once we use this R times the term document matrix as their independent variables, you really want to start with the question, okay, the penalty terms are still pushing W down to 0, right? So what did it mean for W to be 0, right? So what would it mean if we had, you know, coefficient 0, 0, 0, 0, 0, right? So what that would do when we go, okay, this matrix times these coefficients, we still get 0, right? So a weight of 0 still ends up saying, I have no opinion on whether this thing is positive or negative. On the other hand, if they were all 1, right, then it basically says, my opinion is that the naive Bayes coefficients are exactly right. Okay? And so the idea is that I said 0 is almost certainly not the right prior, right? We shouldn't really be saying if there's no coefficient, it means ignore the naive Bayes coefficient. 1 is probably too high, right? Because we actually think that naive Bayes is only kind of part of the answer, right? And so I played around with a few different data sets where I basically said, take the weights and add to them some constant, right? And so 0 would become, in this case, 0.4, right? So in other words, the regularization penalty is pushing the weights not towards 0, but towards this value, right? And I found that across a number of data sets, 0.4 works pretty well, right? And it's pretty resilient, right? So again, this is the basic idea, is to kind of like get the best of both worlds. You know, we're learning from the data using a simple model, but we're incorporating, you know, our prior knowledge as best as we can. And so it turns out when you say, okay, let's tell it, you know, a weight matrix of zeros actually means that you should use about, you know, about half of the R values. That ends up working better than the prior, that the weights should all be zero. Yes.
Is the weights, the W, is it that the point for the amount of regularization required, the amount of so we have this term where we reduce the amount of error, the prediction error, RMSE, plus we have the regularization, and is the W the point for denote the amount of regularization required?
So W are the weights.
Okay.
Right? So this is calculating our activations. Okay, so we calculate our activations as being equal to the weights times the R sum. Right, so that's just our normal our normal linear function. Right. So the thing which is being penalized is my weight matrix. That's what gets penalized. So by saying, hey, you know what, don't just use W, use W plus 0.4. So that's not being penalized. It's not part of the weight matrix. Okay? So effectively, the weight matrix gets 0.4 for free.
Okay.
Yeah.
So by doing this, even after regularization, then every every feature is getting some form of weight, right? Some form of minimum weight or something like that?
Not necessarily, because it could end up choosing a coefficient of negative 0.4 for a feature. Oh. And so that would say, you know what, even though Naive Bayes says it's the R should be whatever for this feature, I think you should totally ignore it. Yeah. Great questions. Okay. We started at 20 past 2. Okay, let's take a break for about 8 minutes or so and start back about 25 to 4. Okay, so a couple of questions at the break. The first was just for a kind of reminder or a bit of a summary as to what's going on here, right? And so here we have W plus, I'm writing it out, yeah, plus adjusted weight, a weight adjustment, times R, right? So normally what we were doing, is saying, hey, logistic regression is basically WX, right? I'm going to ignore the bias, okay? And then we were changing it to be W dot R times X, right? And then we were kind of saying, let's do that bit first, right? Although in this particular case, actually, now I look at it, I'm doing it in this code. It doesn't matter, obviously. In this code, I'm actually doing this bit first. And so so this thing here actually, I called it W, which is probably pretty bad. It's actually W times X, right? So instead of W times X times R, I've got W times X plus a constant times R, right? So the key idea here is that regularization, can't draw in yellow, that's fair enough. Regularization wants the weights to be 0, right? Because it's trying to reduce that. Okay. And so what we're saying is like, okay, we want to push the weights towards 0 because we're saying like, that's our like default starting point expectation is the weights are 0. And so we want to be in a situation where if the weights are 0, then we have a model that like makes theoretical or intuitive sense to us, right? This model, if the weights are 0, doesn't make intuitive sense to us, right? Because it's saying, hey, multiply everything by 0, gets rid of all of that, and gets rid of that as well. And we were actually saying, no, we actually think R is useful. We actually want to keep that, right? So instead, we say, you know what? Let's take that piece here and add 0.4 to it, right? So now, if the regularizer is pushing the weights towards 0, then it's pushing the value of this sum towards 0.4, right? And so therefore it's pushing our whole model to 0.4 times R, right? So in other words, our kind of default starting point, if you've regularized all the weights out altogether, is to say, yeah, you know, let's use a bit of R. That's probably a good idea. Okay? So that's the idea, right? That's the idea, is basically, you know, what happens when that's 0, right? And you want that to, like, be something sensible. Because otherwise, regularizing the weights to move in that direction wouldn't be such a good idea. Okay. Second question was about n-grams. So the n in n-gram can be uni, bi, tri, whatever, 1, 2, 3, whatever grams. So for this movie is good, right? It has 4 unigrams. This movie is good. It has 3 bigrams. This movie is good. It has 2 trigrams. This movie is good. Okay? Can you pass that?
So, yeah, it's okay. Do you mind go back to the WADJ stuff, the 0.4 stuff? Yeah. So I was wondering if this adjustment will harm the predictability of the model. Because think of extreme case if it's not 0.4, if it's 4,000. And all coefficient will be like essentially.
So exactly. So our prior needs to make sense. And so our prior here, and you know, this is why it's called .prod NB, is our prior is that this is something where we think naive Bayes is a good prior, right? And so naive Bayes says that R equals P over, that's not how you write P. P over Q, I have not had much sleep. P over Q is a good prior. And not only do we think it's a good prior, but we think R times X plus B is a good model. That's the naive Bayes model. So in other words, we expect that, you know, a coefficient of 1 is a good coefficient, not 4,000. Right? So we think, specifically, we think 0 is probably not a good coefficient, right? But we also think that maybe the naive Bayes version is a little overconfident, so maybe 1's a little high. So we're pretty sure that the right number, assuming that our model, our naive Bayes model is appropriate, is between 0 and 1.
No, but what I was thinking is as long as it's not 0, you are pushing those coefficients that are supposed to be 0 to something not 0 and make the like high coefficients less distinctive from the low coefficients.
Well, but you see, they're not supposed to be 0. They're supposed to be R. Like, that's what they're supposed to be. They're supposed to be R, right? And so, and remember, this is inside our forward function, so this is part of what we're taking the gradient of, right? So it's basically saying, okay, we're still gonna, you know, you can still set self.w to anything you like, but just the regularizer wants it to be 0. And so all we're saying is, okay, if you want it to be 0, then I'll try to make 0 be, give a sensible answer. That's the basic idea. And nothing says 0.4 is perfect for every data set. I've tried a few different data sets and found various numbers between 0.3 and 0.6 that are optimal, but I've never found one where 0.4 is less good than 0, which is not surprising. And I've also never found one where 1 is better, right? So the idea is this is a reasonable default, but it's another parameter you can play with, which I kind of like, right? It's another thing you could use grid search or whatever to figure out for your data set what's best. And, really the key here being every model before this one, as far as I know, has implicitly assumed it should be 0, because they don't have this parameter, right? And, by the way, I've actually got a second parameter here as well, which is the same thing I do to R, is actually divide R by a parameter, which I'm not going to worry too much about it now, but again, it's another parameter you can use to kind of adjust what the nature of the regularization is. And I mean, in the end, I'm a empiricist, not a theoretician. I thought this seemed like a good idea. Nearly all of my things that seemed like a good idea turned out to be stupid. This particular one gave good results, on this data set and a few other ones as well. Okay, could you pass that? Oh, you want to start there? Yeah.
Okay, I'm still a little bit confused about the W plus W adjusted thing. So you mentioned that we do W plus W adjusted so that the coefficients don't get set to 0, that we place some importance on the priors. But you also said that the effect of learning can be that W gets set to a negative value, which effectively turns W plus W to 0. So if we are allowing the learning process to indeed set the priors to 0,
not the priors, the coefficients, yep.
Then why is that in any way different from just having W?
Great question. Because of regularization, because we're penalizing it by that. Right? So in other words, we're saying, you know what, if the best thing to do is to ignore the value of R, that'll cost you. You're going to have to set W to a negative number. Right? So only do that if that's clearly a good idea. Unless it's clearly a good idea, then you should leave it where it is. That's the only reason. All of this stuff we've done today is basically entirely about, maximizing the advantage we get from regularization and saying regularization pushes us towards some default assumption, and nearly all of the machine learning literature assumes that default assumption is everything's 0. And I'm saying, it turns out, it makes sense theoretically and turns out empirically that actually you should decide what your default assumption is, and that'll give you better results.
So would it be right to say that in a way you're putting an additional hurdle along the way towards getting all coefficients to 0? So it will be able to do that if it is really worth it.
Yeah, exactly. So I'd say the default hurdle without this is making a coefficient non-zero is the hurdle. And now I'm saying, no, the hurdle is making a coefficient not be equal to 0.4R. Yeah, that's our Prince.
So this is sum of W square into C.
Sum of
into some lambda or C penalty constant.
Times something.
So the weight decay should also depend on the value of C. If it is very less, if C is...
Sorry, by C do you mean this A?
Yeah, A.
Okay,
So if A is 0.1, then the weights might not go towards 0.
Yes.
Then we might not need weight decay. So
well, whatever this value, I mean, if the value of this is 0, then there is no regularization, right? But if this value is higher than 0, then there is some penalty, right? And presumably we've set it to non-zero because we're overfitting, so we want some penalty. And so if there is some penalty, then my assertion is that we should penalize things that are different to our prior, not that we should penalize things that are different to 0. right? And our prior is that things should be, you know, around about equal to R. Okay, let's move on. Thanks for the great questions. I want to talk about embedding. I said pretend it's linear. And indeed we can pretend it's linear. Let me show you how much we can pretend it's linear. As in nn.linear, create a linear layer. Here is our data matrix. Right? Here are our coefficients if we're doing the R version. Here are our coefficients R. Right? So if we were to put those into a column vector, like so, right? Then we could do a matrix multiply of that by that, right? And so we're going to end up with, so here's our matrix, here's our vector, right? So we're going to end up with 1 times 1 plus 1 times 1, 1 times 1, 1 times 3, right? 0 times 1, 0 times 0.3. Right? And then the next one, 0 times 1, 1 times 1, so forth. Okay? So like that, the matrix multiply, you know, of this independent variable matrix by this coefficient matrix is going to give us an answer. Okay? So that is just a matrix multiply. So the question is like, okay, well, why didn't Jeremy write nn.linear? Why did Jeremy write nn.embedding? And the reason is because, if you recall, we don't actually store it like this, because this is actually of width 800,000 and of height 25,000, right? So rather than storing it like this, we actually store it as 0, 1, 2, 3, right? 1, 2, 3, 4. 0, 1, 2, 5. 1, 2, 4, 5. Okay, I'll ignore the ones one. Oops. That's actually how we store it. Right? Is this bag of words contains which word indexes? Does that make sense? Okay, so that's like this is like a sparse way of storing it, right? It's just list out the indexes in each sentence. So given that, I want to now do that matrix multiply that I just showed you to create that same outcome, right? But I want to do it from this representation. So if you think about it, all this is actually doing is it's saying a one-hot, you know, this is basically one-hot encoded, right? It's kind of like a dummy matrix version. Does it have the word this? Does it have the word movie? Does it have the word is? And so forth. So if we took the simple version of like, does it have the word this? 1, 0, 0, 0, 0, 0, right? And we multiplied that by that, right? Then that's just going to return the first item. That makes sense? So in general, a one-hot encoded vector times a matrix is identical to looking up that matrix to find the nth row in it. Right? So this is identical to saying find the 0, 1st, 2nd, and 5th coefficients. Right? So they're the same, they're exactly the same thing. And like, it doesn't, like in this case, I only have one coefficient per feature, right? But actually the way I did this was to have one coefficient per feature for each class, right? So in this case it's both positive and negative, So I actually had kind of like an R positive and an R negative. So R negative would be just the opposite, right? Equals that divided by that, right? Now in the binary case, obviously it's redundant to have both, but what if it was like, what's the author of this text? Is it Jeremy or Savannah or Terence, right? Now we've got 3 categories. We want 3 values of R, right? So the nice thing is that in this sparse version, you know, you can just look up, you know, the 0th and the 1st and the 2nd and the 5th, right? And again, it's identical, mathematically identical to multiplying by a one-hot encoded matrix. But when you have sparse inputs, it's obviously much, much more efficient. So this computational trick, which is mathematically identical to, not conceptually analogous to, mathematically identical to multiplying by a one-hot encoded matrix, is called an embedding, right? So I'm sure you've all heard, or most of you probably heard about embeddings, like word embeddings, word to vec or glove or whatever. And people love to make them sound like there's some amazing new complex neural net thing, right? They're not. Embedding means make a multiplication by a one-hot encoded matrix faster by replacing it with a simple array lookup. Okay, so that's why I said you can think of this as if it said self.w equals nn.linear nf plus 1 by 1, right? Because it actually does the same thing, right? It actually is a matrix with those dimensions. This actually is a matrix with those dimensions, right? It's a linear layer. But it's expecting that the input we're going to give it is not actually a one-hot encoded matrix, but is actually a list of integers, right? The indexes for each word or for each item. So you can see that the forward function in FastAI automatically gets, for this learner, the feature indexes, right? So they come from the sparse matrix automatically. NumPy makes it very easy to just grab those indexes. Okay, so in other words there, we've got a list of each word index of the 800,000 that are in this document. And so then this here says look up each of those in our embedding matrix, which has got 800,000 rows, and return each thing that you find. Okay, so mathematically identical to multiplying by the one-hot encoded matrix. Does that make sense? So that's all an embedding is. And so what that means is we can now handle building any kind of model, like a, whatever kind of neural network, where we have potentially very high cardinality categorical variables as our inputs. We can then just turn them into a numeric code between 0 and the number of levels. And then we can learn a linear layer from that as if we had one-hot encoded it, without ever actually constructing the one-hot encoded version, and without ever actually doing that matrix multiply. Okay? Instead, we will just store the index version and simply do the array lookup. Okay? And so the gradients that are flowing back, basically in the one-hot encoded version, everything that was a 0 has no gradient. So the gradients flowing back is just going to update the particular row of the embedding matrix that we used. Okay? And so that's fundamentally important for NLP, just like here. I wanted to create a PyTorch model that would implement this ridiculously simple little equation, right? And to do it without this trick would have meant I was feeding in a 25,000 by 800,000 element array, which would have been kind of crazy, right? And so this trick allowed me to write, I just replaced the word linear with embedding, replaced the thing that feeds the one-hot encodings in with something that just feeds the indexes in, and that was it. That it kept working, and so this now trains, in about a minute per epoch. Okay. So what we can now do is we can now take this idea and apply it not just to language, but to anything, right? For example, predicting the sales of items at a grocery. Yes, can you pass that?
Just a quick question. So we are not actually looking up anything, right? We are just saying that now that array with the indices, that is the representation.
So so we are doing a lookup, right? The representation that's being stored for the bag of words is now not 111001, but 0125, right? And so then we actually have to do our matrix product, right? But rather than doing the matrix product, we look up the 0th thing, and the first thing, and the second thing, and the 5th thing.
So that means we are still retaining the one hot encoded matrix.
No, we didn't. There's no one hot encoded matrix used here. Here's the one hot encoded matrix, which is not currently highlighted. We've currently highlighted the list of indexes and the list of coefficients from the weight matrix. Does that make sense?
Yeah.
Great. Okay. So what we're going to do now is we're kind of going to go a step further and saying, like, let's not use a linear model at all. Let's use a multi-layer neural network, right? And let's have the input to that potentially include some categorical variables, right? And those categorical variables we will just have as numeric indexes. And so the first layer for those won't be a normal linear layer, they'll be an embedding layer, which we know behaves exactly like a linear layer mathematically. And so then our hope will be that we can now use this to create a neural network for any kind of data, right? And so there was a competition on Kaggle a few years ago called Rossmann, which is a German grocery chain, where they asked to predict the sales of items in their stores, right? And that included a mixture of categorical and continuous variables. And in this paper by Gore and Burkhan, they described their third place winning entry, which was much simpler than the first place winning entry, but nearly as good, but much, much simpler because they took advantage of this idea of what they call entity embeddings. In the paper, they thought, I think, that they had invented this. Actually, it had been written earlier by Yoshio Bengio and his co-authors in another Kaggle competition, which was predicting taxi destinations. Although I will say I feel like Gore went a lot further in describing how this can be used in many other ways. And so we'll talk about that as well. So this one is actually in the Deep Learning 1 repo. Okay, DL1 lesson 3. Okay, because we talk about some of the deep learning specific aspects in the deep learning course. Whereas in this course we're going to be talking mainly about the feature engineering, and we're also going to be talking about kind of this embedding idea. So let's start with the data, right? So the data was, store number 1 on the 31st of July 2015 was open. They had a promotion going on. It was a school holiday. It was not a state holiday. And they sold 5,263 items. So that's the key data they provided. And so the goal is obviously to predict sales in a test set that has the same information without sales. They also tell you that for each store, it's of some particular type. It sells some particular assortment of goods. Its nearest competitor is some distance away. The competitor opened in September 2008. And there's some more information about promos. I don't know the details of what that means. Like in many Kaggle competitions, they let you download external data sets if you wish, as long as you share them with other competitors. So people, they also told you what state each store is in. So people downloaded a list of the names of the different states of Germany. They downloaded a file for each state in Germany for each week, some kind of Google Trend data. I don't know what specific Google Trend they got, but there was that. For each state, they downloaded a whole bunch of temperature information. That's it. And then here's the test set. Okay. So, I mean, one interesting insight here is that there was probably a mistake in some ways for Rossmann to design this competition as being one where you could use external data, because in reality, you don't actually get to find out next week's weather or next week's Google Trends, you know. But, you know, when you're competing in Kaggle, you don't care about that. You just want to win, so you use whatever you can get. So let's talk first of all about data cleaning. You know, there wasn't really much feature engineering done in this third place winning entry. Particularly by Kaggle standards, where normally every last thing counts. This is a great example of how far you can get with a neural net. And it certainly reminds me of the claims prediction competition we talked about yesterday, where the winner did no feature engineering and entirely relied on deep learning. The laughter in the room, I guess, is from people who did a little bit more than no feature engineering in that competition. So, you know, I should mention, by the way, like, I find that bit where, like, you work hard at a competition and then it closes and you didn't win and the winner comes out and says, this is how I won. Like, that's the bit where you learn the most, right? Like, sometimes that's happened to me and it's been like, oh, I thought of that. I thought I tried that. And then I go back and I realize I, like, had a bug there. I didn't test properly. And I learn, like, oh, okay, like, I really need to learn to, like, test this thing in this different way. Sometimes it's like, oh, I thought of that, but I assumed it wouldn't work. I've really got to remember to check everything before I make any assumptions. And, you know, sometimes it's just like, oh, I did not think of that technique. Wow, now I know it's better than everything I just tried. Because, like, otherwise somebody says, like, hey, you know, here's a really good technique. You're like, okay, great. Right? But when you spent months trying to do something and, like, somebody else did it better by using that technique, that's pretty convincing. Right? And so, like, it's kind of hard, like, I'm standing up in front of you saying, here's a bunch of techniques that I've used, and I've won some Kaggle competitions, and I've got some state-of-the-art results, but it's like, that's kind of secondhand information by the time it hits you, right? So it's really great to, yeah, try things out. And also, like, it's been kind of nice to see, particularly I've noticed in the deep learning course, quite a few of my students have, you know, I've said, like, this technique works really well, and they've tried it, and they've got into the top 10 of a Kaggle competition the next day, and they're like, okay, that counts as working really well. So yeah, Kaggle competitions are helpful for lots and lots of reasons, but, you know, one of the best ways is what happens after it finishes. And so definitely, like, for the ones that are now finishing up, make sure you know, watch the forums, see what people are sharing in terms of their solutions. And, you know, if you want to learn more about them, like, feel free to ask the winners, like, hey, could you tell me more about this or that? People are normally pretty good about explaining. And then ideally, try and replicate it yourself, right? And that can turn into a great blog post, you know, or a great kernel, is to be able to say, okay, such and such said that they used this technique. Here's a really short explanation of what that technique is, and here's a little bit of code showing how it's implemented, and, you know, here's the result showing you can get the same result. That can be a really interesting write-up as well. Okay, so, you know, it's always nice to kind of have your data reflect, like, I don't know, be as kind of easy to understand as possible. So in this case, the data that came from Kaggle used various, integers for the holidays. We can just use a Boolean of like, was it a holiday or not? So like, just clean that up. We've got quite a few different tables. We need to join them all together, right? I have a standard way of joining things together with Pandas. I just use the Pandas merge function. And specifically, I always do a left join. So who wants to tell me what a left join is? Since it's there, why don't you go ahead?
So you retain all the rows in the left table, and so you have a key column, you match that with the key column in the right side table, and you just merge the rows that are also present in the right side table.
Yeah, that's a great explanation. Good job. I don't have much to add to that. The key reason that I always do a left join is that after I do the join, I always then check if there were things in the right-hand side that are now null, right? Because if so, it means that I missed some things. I haven't shown it here, but I also check that the number of rows hasn't varied before and after. If it has, that means that the right-hand side table wasn't unique. Okay, so even when I'm sure something's true, I always also assume that I've screwed it up. So I always check. So I can go ahead and merge the state names into the weather. I can also, if you look at the Google Trends table, it's got this week range, which I need to turn into a date in order to join it, right? And so the nice thing about doing this in Pandas is that Pandas gives us access to, all of Python, right? And so, for example, inside the series object is a .str attribute that gives you access to all the string processing functions. Right? Just like cat gives you access to the categorical functions, dt gives you access to the datetime functions. So I can now split everything in that column. And it's really important to try and use these Pandas functions because they're going to be vectorized, accelerated through, often through SIMD, at least through, C code. So that runs nice and quickly, right? And then, as per usual, let's add date metadata to our dates. In the end, we're basically denormalizing all these tables. So we're going to put them all into one table. So in the Google Trend table, there was also, they were mainly trends by state, but there was also trends for the whole of Germany. So we kind of put the Germany, the whole of Germany ones into a separate data frame so that we can join that. So we're going to have like Google Trend for this state and Google Trend for the whole of Germany. And so now we can go ahead and start joining, both for the training set and for the test set, and then for both check that we don't have zeros. My merge function, I set the suffix, if there are two columns that are the same, I set the suffix on the left to be nothing at all, so it doesn't screw around with the name, and the right-hand side to be _y. And in this case, I didn't want any of the duplicate ones, so I just went through and deleted them. Okay. And then we're going to, in a moment, we're going to try to create a competition. The main competitor for this store has been open since some date, right? And so you can just use pandas to date time, passing in the year, the month, and the day, right? And so that's going to give us an error unless they all have years and months. So we're going to fill in the missing ones with the 1900 and 01. Okay. And then what we really want to know is like how long has this store been open for at the time of this particular record. Right? So we can just do a date subtract. Okay. Now, if you think about it, sometimes the competition, opened later than this particular row. So sometimes it's going to be negative, and it doesn't probably make sense to have negatives, meaning like it's going to open in X days time. Now, having said that, I would never put in something like this without first of all running a model with it in and without it in, right? Because like our assumptions about the data very often turn out not to be true. Now in this case, I didn't invent any of these pre-processing steps. I wrote all the code, but it's all based on the third place winner's GitHub repo, right? So knowing what it takes to get third place in the Kaggle competition, I'm pretty sure they would have checked every one of these pre-processing steps and made sure it actually improved their validation set score. Okay. So what we're going to be doing is creating a neural network where some of the inputs to it are continuous and some of them are categorical. And so what that means in the neural net that, you know, we have, we're basically going to have, you know, this kind of initial weight matrix, right? And we're going to have this input feature vector, right? And so some of the inputs are just going to be plain continuous numbers, like, you know, what's the maximum temperature here, or what's the number of kilometers to the nearest store. And some of them are going to be one hot encoded effectively, right? But we're not actually going to store it as one hot encoded. We're actually going to store it as the index, right? And so the neural net model is going to need to know which of these columns should you basically create an embedding for, which ones should you treat, you know, as if they were kind of one hot encoded, and which ones should you just feed directly into the linear layer, right? And so we're going to tell the model when we get there which is which, but we actually need to think ahead of time about like which ones do we want to treat as categorical and which ones are as continuous. In particular, things that we're going to treat as categorical, we don't want to create more categories than we need, right? And so let me show you what I mean. The third place getters in this competition decided that the number of months that the competition was open was something that they were going to use as a categorical variable, right? And so in order to avoid having more categories than they needed, they truncated it at 24 months. They said anything more than 24 months, I'll truncate to 24. So here are the unique values of competition months open, and it's all the numbers from 0 to 24, right? So what that means is that there's going to be, you know, an embedding matrix that's going to have basically an embedding vector for things that aren't open yet, for things that are open a month, for things that are open 2 months, and so forth. Now, they absolutely could have done that as a continuous variable, right? They could have just had a number here, which is just a single number of how many months has it been open, and they could have treated it as continuous and fed it straight into the initial weight matrix. What I found, though, and obviously what these competitors found, is where possible, it's best to treat things as categorical variables, right? And the reason for that is that, like, when you feed something through an embedding matrix, you basically it means every level can be treated, like, totally differently, right? And so, for example, in this case, whether something's been open for 0 months or 1 month is, like, really different, right? And so if you fed that in as a continuous variable, it would be kind of difficult for the neural net to try and find a functional form that kind of has that big difference. It's possible, because neural nets can do anything, right? But you're not making it easy for it. Whereas if you used an embedding, treated it as categorical, then it'll have a totally different vector for 0 versus 1, right? So it seems like, particularly as long as you've got enough data, that treating columns as categorical variables where possible is a better idea. And so when I say where possible, that kind of basically means, like, where the cardinality is not too high. You know, so if this was like, you know, the sales ID number that was, like, uniquely different on every row, you can't treat that as a categorical variable, right? Because, you know, it would be a huge embedding matrix and everything only appears once. or ditto for like kilometers away from the nearest store to 2 decimal places, you wouldn't make a categorical variable, right? So that's kind of the rule of thumb that they both used in this competition. In fact, if we scroll down to their choices, here is how they did it, right? Their continuous variables were things that were genuinely continuous, like number of kilometers away to the competitor, the temperature stuff, right? The number, the specific number in the Google trend, right? Where else, everything else, basically, they treated as categorical. Okay. Okay, so that's it for today. So, yeah, next time we'll finish this off. We'll see how to turn this into a neural network, and yeah, kind of wrap things up. So, see you then. I thought what we might do today is to finish off where we were in this Rossmann notebook, looking at time series forecasting and structured data analysis. And then we might do a little mini review of everything we've learnt, because believe it or not, this is the end. There's nothing more to know about machine learning other than everything that you're going to learn next semester and for the rest of your life. But anyway, I got nothing else to teach. Yeah, so we'll do a little review, and then we'll cover the most important part of the course, which is thinking about how are ways to think about how to use this kind of technology appropriately, and effectively in a way that's hopefully a positive impact on society. So last time we got to the point where we talked a bit about this idea that when we were looking at building this competition months open derived variable, that we actually truncated it down to be no more than 24 months, and we talked about the reason why being that we actually wanted to use it as a categorical variable, because categorical variables, thanks to embeddings, have more flexibility in how the neural net can use them. And so that was kind of where we left off. So let's keep working through this, because what's happening in this notebook is stuff which is probably going to apply to most time series data sets that you work with, right? And as we talked about, although we use df.apply here, this is something where it's running a piece of Python code over every row, and that's horrifically slow, right? So we only do that if we can't find a vectorized pandas or numpy function that can do it to the whole column at once. But in this case, I couldn't find a way to convert a year and a week number into a date without using arbitrary Python. Also worth remembering this idea of a lambda function. Anytime you're trying to apply a function to every row of something or every element of a tensor or something like that, if there isn't a vectorized version already, you're going to have to call something like dataframe.apply, which will run a function you pass to every element. So this is something in a kind of, this is basically a map in functional programming. Since very often the function that you want to pass to it is something you're just going to use once and then throw it away, it's really common to use this lambda approach. So this lambda is creating a function just for the purpose of telling df.apply what to use, right? So we could also have written this in a different way, which would have been to say define create chromo 2 sense on some value, return And then we could put that in here. Okay, so that and that are the same thing. Okay, so one approach is to define the function and then pass it by name, or the other is to define the function in place using lambda. All right, and so if you're not comfortable creating and using lambdas, good thing to practice, and playing around with df.apply is a good way to practice it. Okay, so let's talk about this durations section, which may at first seem a little specific, but actually it turns out not to be. What we're going to do is we're going to look at 3 fields: promo, state holiday, and school holiday. And so basically what we have is a table of, for each store, for each date, does that store have a promo going on at that date? Is there a school holiday in that region of that store at that date? Is there a state holiday in that region for that store at that date? Okay, and so this kind of thing is, like they're events, and time series with events are like very, very common. Like if you're looking at oil and gas drilling data, you're trying to say like the flow through this pipe. Here's an event representing when it set off some alarm, or here's an event where the drill got stuck, or whatever, right? And so like most time series, at some level will tend to represent some events. So the fact that an event happened at a time is interesting itself, but very often a time series will also show something happening before and after the event. So for example, in this case, we're doing grocery sales prediction. If there's a holiday coming up, it's quite likely that sales will be higher before and after the holiday and lower during the holiday if this is a city-based store, right? Because you're going to stock up before you go away to bring things with you, and when you come back, you've got to refill the fridge, for instance, right? So it's, although like we don't necessarily have to do this kind of feature engineering to create features specifically about like this is before or after a holiday, the neural net, the more we can give the neural net like the kind of information it needs, the less it's going to have to learn it. The less that it's going to have to learn it, the more we can do with the data we already have, the more we can do with the size architecture we already have. So feature engineering, even with stuff like neural nets, is still important because it means that we'll be able to do get better results with whatever limited data we have, whatever limited computation we have. So the basic idea here, therefore, is when we have events in our time series, is we want to create 2 new columns for each event. How long is it going to be until the next time this event happens? And how long has it been since the last time that event happened? So in other words, how long until the next state holiday? How long since the previous state holiday? Okay? So that's not something which I'm aware of as existing as a library or anything like that. So I wrote it here by hand, right? And so importantly, I need to do this by store, right? So I want to say like, because, for this store, when was this store's last promo? So how long has it been since the last time it had a promo? How long it will be until the next time it has a promo, for instance. All right. So here's what I'm going to do. I'm going to create a little function that's going to take a field name, and I'm going to pass it each of promo and then state holiday and then school holiday. Right, so let's do school holiday, for example. So we'll say field equals school holiday, and then we'll say get elapsed school holiday, comma, after. So let me show you what that's going to do. So we've got to first of all sort by store and date. Right, so now when we loop through this, we're going to be looping through within a store, so store number 1, January the 1st, January the 2nd, January the 3rd, and so forth. And as we loop through each store, we're basically going to say, like, is this row a school holiday or not? And if it is a school holiday, then we'll keep track of this variable called last date, which says this is the last date where we saw a school holiday. Okay? And so then we're basically going to append to our result the number of days since the last school holiday. That's the kind of basic idea here. So there's a few interesting features. One is the use of zip. Right? So I could actually write this much more simply. Right? I could say, let's go through, well, we could basically go through, like, for row in df.iter rows, right? And then grab the fields we want from each row. It turns out this is 300 times slower than the version that I have. And basically, like, iterating through a data frame and extracting specific fields out of a row has a lot of overhead. What's much faster is to iterate through a NumPy array. So if you take a series like df.store and add .values after it, that grabs a NumPy array of that series. Okay, so here are 3 NumPy arrays. One is the store IDs. One is whatever field is, in this case, let's say school holiday. And one is the date. So now what I want to do is loop through the first one of each of those lists, and then the second one of each of those lists, and then the third one of each of those lists. And like, this is a really, really common pattern. I need to do something like this in basically every notebook I write. And the way to do it is with zip. Right? So zip means loop through each of these lists one at a time. And then this here is where we can grab that element out of the first list, the second list, and the third list. Okay? So if you haven't played around much with zip, that's a really important function to practice with. Like I say, I use it in pretty much every notebook I write all the time. You have to loop through, a bunch of lists at the same time. All right, so we're going to loop through every store, every school holiday, and every date. Yes.
So is it looping through like all the possible combinations of each of those, or just for 1, 1, 1?
Yeah, exactly. 1, 1, 2, 2, 2. Yeah.
Okay.
Yeah, exactly. Thanks for the question. So in this case, we basically want to say, let's grab the first store, the first school holiday, the first date. Right. So for store 1, January the 1st, school holiday was true or false. Right? And so if it is a school holiday, I'll keep track of that fact by saying the last time I saw a school holiday was that day. Okay? And then append how long has it been since the last school holiday. Right? And if the store ID is different to the last store ID I saw, then I've now got to a whole new store, in which case I have to basically reset everything. Okay. Could you pass that to Karen?
What will happen to the first points that we don't have a last holiday?
Yeah, so I just set, I basically set this to some arbitrary starting point. It's going to end up with like I can't remember, it's either largest or the smallest possible date.
Okay, thanks.
And you may need to replace this with a missing value afterwards, or some, with a 0 or whatever. The nice thing is, though, thanks to ReLUs, it's very easy for a neural net to kind of cut off extreme values. So in this case, I didn't do anything special with it. I ended up with these like negative a billion day time stamps, and it still worked fine. Okay, so we can go through, and so the next thing to note is there's a whole bunch of stuff that I need to do to both the training set and the test set, right? So in the previous section, I actually kind of added this little loop where I go, for each of the training data frame and the test data frame, do these things, right? So I kind of, each cell I did for each of the data frames. I've now got coming up a whole series of cells that I want to run, first of all, for the training set and then for the test set. So in this case, the way I did that was I had two different cells here. One which set df to be the training set, one which set to be the test set. And so the way I use this is I run just this cell, right? And then I run all the cells underneath, right? So it does it all to the training set. And then I come back and run just this cell and then run all the cells underneath, okay? So like this notebook is not designed to be just run from top to bottom, but it's designed to be run in this particular way. And I mentioned that because like this can be a handy trick to know. Like you could of course put all the stuff underneath in a function that you pass the data frame to and call it once with the test set and once with the training set. But I kind of like to experiment a bit more interactively, look at each step as I go. So this way is an easy way to kind of run something on two different data frames without turning it into a function. Okay, so this is going to, if I sort by store and by date, then this is keeping track of the last time something happened. And so this is therefore going to end up telling me how many days was it since the last school holiday. Right? So now if I sort date descending and call the exact same function, then it's going to say how long until the next school holiday. Right? So that's a kind of a nice little trick for adding these kind of event timers, arbitrary event timers into your time series models. Right? So if you're doing, for example, the Ecuadorian groceries competition right now, maybe this kind of approach would be useful for various events in that as well. Do it for state holiday, do it for promo. There we go. Okay. The next thing that we look at here is rolling functions. So rolling functions is how we, rolling in Pandas is how we create what we call windowing functions. So let's say I had some data, something like this, right? And this is like date, and I don't know, this is like sales or whatever. What I could do is I could say like, okay, let's create a window around this point of like 7 days, right? So it'd be like, okay, this is a 7-day window, say, right? And so then I could take the average sales in that 7-day window, right? And then I could like do the same thing, like, I don't know, over here, right? Take the average sales over that 7-day window, right? And so if we do that for every point and join up those averages, you're going to end up with a moving average. Okay, so the kind of the more generic version of the moving average is a window function, i.e. something where you apply some function to some window of data around each point. Now, very often the windows that I've shown here are not actually what you want. If you're trying to build a predictive model, you can't include the future as part of a moving average, right? So quite often you actually need a window that ends here. So that would be our window function, right? And so Pandas lets you create arbitrary window functions using this rolling here. This here says how many time steps do I want to apply the function to, right? This here says if I'm at the edge, so in other words, if I'm like out here, should you make that a missing value because I don't have 7 days to average over, or what's the minimum number of time periods to use, Right, so here I said 1. Okay, and then optionally you can also say, do you want to set the window at the start of a period, or the end of a period, or the middle of the period? Okay, so, and then within that you can then apply whatever function you like. Okay, so here I've got my weekly by store sums. Okay, so there's a nice easy way of getting kind of moving averages or whatever else. And I should mention in Pandas, if you go to the time series page on Pandas, there's literally, like, look at just the index here. Time series functionality is all of this, like, there's lots. Because, like, Wes McKinney, who created this, he was originally in hedge fund trading, I believe. And, his work was all about time series. And so I think, like, Pandas originally was very focused on time series, and still, it's perhaps the strongest part of Pandas. So if you're playing around with time series computations, you definitely owe it to yourself to try to learn this entire API. And like there's a lot of kind of conceptual pieces around like timestamps and date offsets and resampling and stuff like that to kind of get your head around, but it's totally worth it because otherwise you'll be writing this stuff as loops by hand. It's going to take you a lot longer than leveraging what Pandas already does. And of course Pandas will do it in highly optimized C code for you, vectorized C code, whereas your version is going to loop in Python. So definitely worth, if you're doing stuff in time series, learning the full Pandas time series API. Which is about as strong as any time series API out there. Okay, so at the end of all that, you can see here's those kind of starting point values I mentioned, slightly on the extreme side. And so you can see here the 17th of September, store 1 was 13 days after the last school holiday. The 16th was 12, 11, 10, so forth. Okay, we're currently in a promotion. Right here, this is 1 day before a promotion. Here we've got 9 days after the last promotion, and so forth. Okay, so that's how we can add kind of event counters to a time series, and probably always a good idea when you're doing work with time series. So now that we've done that, we've got lots of columns in our data set, and so we split them out into categorical versus continuous columns. We'll talk more about that in a moment in the review section. But so these are going to be all the things I'm going to create an embedding for. Okay, and these are all of the things that I'm going to feed directly into the model. So, for example, we've got like competition distance, so that's distance to the nearest competitor, maximum temperature, and here we've got day of week, right? So, so here we've got maximum temperature, maybe it's like 22.1 because they use centigrade in Germany. We've got distance to nearest competitor, might be 321 kilometers, 0.7. Right, and then we've got day of week, which might be, I don't know, maybe Saturday is a 6. Okay, so these numbers here are going to go straight into our vector, right? The vector that we're going to be feeding into our neural net. Right? 22.1, 321.7. Okay. We'll see in a moment. We'll normalize them, but more or less. But this categorical variable, we're not. We need to put it through an embedding, right? So we'll have some embedding matrix, right, of if there are 7 days by, I don't know, maybe dimension 4 embedding, okay? And so this will look up the 6th row, to get back the 4 items, right? And so this is going to turn into length 4 vector, which we'll then add here. Okay? So that's how our continuous and categorical variables are going to work. So then all of our categorical variables, we'll turn them into Pandas categorical variables in the same way that we've done before. And then we're going to apply the same mappings to the test set, right? So if Saturday is a 6 in the training set, this apply cats makes sure that Saturday is also a 6 in the test set. For the continuous variables, make sure they're all floats, because PyTorch expects everything to be a float. So then, this is another little trick that I use. Both of these cells define something called joined SAMP. One of them defines them as the whole training set. One of them defines them as a random subset. Right? And so the idea is that I do all of my work on the sample, make sure it all works well, play around with different hyperparameters and architectures, and then when I'm like, okay, I'm very happy with this, I then go back and run this line of code to say, okay, now make the whole data set be the sample, and then rerun it. Okay, so this is a good way, again, similar to what I showed you before. It lets you use the same cells in your notebook to run, first of all, on a sample, and then go back later and run it on the full data set. Okay, so now that we've got that joined SAMP, we can then pass it to procdf, as we've done before, to grab the dependent variable, to deal with missing values. And in this case, we pass one more thing, which is do_scale equals true. Do_scale equals true will subtract the mean and divide by the standard deviation. And so the reason for that is that if our first layer, it's just a matrix multiply, right? So here's our set of weights. And our input is like, I don't know, it's got something which is like 0.001. And then it's got something like, which is like 10 to the 6. Right? And then our weight matrix has been initialized to be like random numbers between 0 and 1. Right? So we've got like 0.6, 0.1, etc. Then basically this thing here is going to have gradients that are 9 orders of magnitude bigger than this thing here, which is not going to be good for optimization. Okay, so by normalizing everything to be mean of 0, standard deviation of 1 to start with, then that means that all of the gradients are going to be, on the same kind of scale. We didn't have to do that in random forests, right? Because in random forests, we only cared about the sort order. We didn't care about the values at all, right? But with linear models and things that are built out of layers of linear models, like i.e. neural nets, we care very much about the scale. Okay, so do_scale equals true normalizes our data for us. Now, since it normalizes our data for us, it returns one extra object, which is a mapper, which is an object that contains, for each continuous variable, what was the mean and standard deviation it was normalized with. The reason being that we're going to have to use the same mean and standard deviation on the test set, all right, because we need our test set and our training set to be scaled in the exact same way, otherwise they're going to have different meanings. Okay, and so these details about making sure that your test and training set have the same categorical codings, the same missing value replacement, and the same scaling normalization are really important to get right, because if you don't get it right, then your test set is, not going to work at all. Okay? But if you follow these steps, it'll work fine. We also take the log of the dependent variable, And that's because in this Kaggle competition, the evaluation metric was root mean squared % error. So root mean squared % error means we're being penalized based on the ratio between our answer and the correct answer. We don't have a loss function in PyTorch called root mean squared % error. We could write one, but easier is just to take the log of the dependent because the difference between logs is the same as the ratio. Okay, so by taking the log, we kind of get that for free. You'll notice like the vast majority of regression competitions on Kaggle use either root mean squared % error or root mean squared error of the log as their evaluation metric. And that's because in real world problems, most of the time we care more about ratios than about raw differences. Right? So if you're designing your own project, it's quite likely that you'll want to think about using log of your dependent variable. So then we create a validation set, and as we've learned before, most of the time if you've got a problem involving a time component, your validation set probably wants to be the most recent time period rather than a random subset. Okay, so that's what I do here. When I finished modeling and I found an architecture and a set of hyperparameters and a number of epochs and all that stuff that works really well, if I want to make my model as good as possible, I'll retrain on the whole thing, right, including the validation set. Right? Now currently, at least FastAI assumes that you do have a validation set, so my kind of hacky workaround is to set my validation set to just be one index, which is the first row, okay, and that way like all the code keeps working, but there's no real validation set. So obviously if you do this, you need to make sure that your final training is like the exact same hyperparameters, the exact same number of epochs, exactly the same as the thing that worked, because you don't actually have a proper validation set now to check against.
I have a question regarding getElapsed function, which we discussed before. So in getElapsed function, we are trying to find when is the next holiday, like when will the next holiday come?
How many days away is it?
So every year the holidays are more or less fixed. Like there will be a holiday on 4th of July, 25th of December, and there is hardly any change. So can't we just look from previous years and just get a list of all the holidays that are going to occur this year?
Maybe. I mean, in this case, I guess like that's not true of promo, right? And some holidays change, like Easter, you know. So like this way, I get to write one piece of code that works for all of them, you know, and it doesn't take very long to run. So yeah. So there might be ways if your data set was so big that this took too long, you could maybe do it on 1 year and then kind of somehow copy it. But yeah, in this case, there was no need to. And I always value my time over my computer's time. So I try to keep things as simple as I can. Okay. So now we can create our model. And so to create our model, we have to create a model data object, as we always do with FastAI. So a columnar model data object is just a model data object that represents a training set, a validation set, and an optional test set of standard columnar, structured data. Okay, and we just have to tell it which of the variables should we treat as categorical. Okay, and then pass in our data frames. So for each of our categorical variables, here is the number of categories it has. Okay? So for each of our embedding matrices, this tells us the number of rows in that embedding matrix. And so then we define what embedding dimensionality we want. If you're doing like natural language processing, then the number of dimensions you need to capture all the nuance of what a word means and how it's used has been found empirically to be about 600. it turns out that when you do NLP models with embedding matrices that are smaller than 600, you don't get as good a results as you do if there's the size 600. Beyond 600, it doesn't seem to improve much. I would say that human language is one of the most complex things that we model. So I wouldn't expect you to come across many, if any, categorical variables that need embedding matrices with more than 600 dimensions. At the other end, you know, some things may have pretty simple kind of causality, right? So, for example, let's have a look. State holiday, you know, maybe if something's a holiday, then it's just a case of like, okay, at stores that are in the city, there's some behavior, there's stores that are in the country, there's some other behavior, and that's about it. You know, like maybe it's a pretty simple relationship. So like ideally, when you decide what embedding size to use, you would kind of use your knowledge about the domain to decide like how complex is the relationship, and so how big embedding do I need, right? In practice, you almost never know that, right? Like you would only know that because maybe somebody else has previously done that research and figured it out, like in NLP. So in practice, you probably need to use some rule of thumb, okay? And then having tried your rule of thumb, you could then maybe try a little bit higher and a little bit lower and see what helps. So it's kind of experimental. So here's my rule of thumb. My rule of thumb is look at how many discrete values the category has, i.e. the number of rows in the embedding matrix, and make the dimensionality of the embedding half of that. Right? So for day of week, which is the second one, 8 rows and 4 columns. So here it is there, right? The number of categories divided by 2. But then I say, don't go more than 50, right? So here you can see for store, there's 1,000 stores, I only have a dimensionality of 50. Why 50? I don't know. It seems to have worked okay so far. Like, you may find you need something a little different. Actually, for the Ecuadorian groceries competition, you know, I haven't really tried playing with this, but I think we may need some larger embedding sizes. But it's something to fiddle with. Prince, can you pass that left?
So as your variables, the cardinality size becomes larger and larger, you're creating more and more, or like
bigger and bigger
wider embedding matrices. Yeah. Aren't you therefore massively risking overfitting because you're just introducing so many parameters that the model can never possibly capture all that variation unless your data is absolutely huge?
That's a great question. And so let me remind you about my kind of like golden rule of the difference between modern machine learning and old machine learning. In old machine learning, we control complexity by reducing the number of parameters. In modern machine learning, we control complexity by regularization. So the short answer is no. I'm not concerned about overfitting because the way I avoid overfitting is not by reducing the number of parameters, but by increasing my dropout or increasing my weight decay. Okay. Now, having said that, like, there's no point using more parameters for a particular embedding than I need, like, because regularization, like, is penalizing a model by giving it like more random data or by actually penalizing weights. So we'd rather not use more than we have to. But the kind of my general rule of thumb for designing an architecture is to, you know, be generous on the side of the number of parameters. But yeah, in this case, if after doing some work we kind of felt like, you know what, the store doesn't actually seem to be that important, then I might manually go and like change this to make it smaller, you know. Or if I was really finding there's not enough data here, I'm either overfitting or I'm using more regularization than I'm comfortable with, again, you know, then you might go back. But I would always start with like being generous with parameters. And yeah, in this case, this model turned out pretty good. Okay, so now we've got a list of tuples containing the number of rows and columns of each of our embedding matrices. And so when we call getLearner to create our neural net, that's the first thing we pass in, right, is how big is each of our embeddings. Okay? And then we tell it how many continuous variables we have. We tell it how many activations to create for each layer, and we tell it what dropout to use for each layer. Okay? And so then we can go ahead and call fit. Okay? So then we fit for a while, and we're kind of getting something around the 0.1 mark. All right. So I tried running this on the test set, and I submitted it to Kaggle during the week, actually last week. And here it is. Okay. Private score 107, public score 103. Okay. So let's have a look and see how that would go. So 107, private 103, public. So let's start on public, which is 103. Not there. Out of 3,000. Got to go back a long way. Here it is, 103. Okay, 340th. Ah, that's not good. So on the public leaderboard, 340th. Let's try the private leaderboard, which is 107. Oh, 5th. So, like, hopefully you're now thinking, oh, there are some Kaggle competitions finishing soon, which I entered, and I spent a lot of time trying to get good results on the public leaderboard. I wonder if that was a good idea. And the answer is no, it wasn't. Right? The Kaggle public leaderboard is not meant to be a replacement for your carefully developed validation set. Right? So, for example, if you're doing the iceberg competition, right, which ones are ships, which ones are icebergs, then they've actually put something like 4,000 synthetic images into the public leaderboard and none into the private leaderboard. Okay? So this is one of the really good kind of things that tests you out on Kaggle, is like, are you creating a good validation set and are you trusting it, right? Because if you're trusting your leaderboard feedback more than your validation feedback, then you may find yourself in 350th place when you thought you were in 5th, right? So in this case, we actually had a pretty good validation set, right? Because as you can see, it's saying like somewhere around 0.1, and we actually did get somewhere around 0.1. Okay, and so in this case, the validation set, the public leaderboard in this competition was entirely useless. Yep.
So,
can you use the box, please?
So in regards to that, how much does the top of the public leaderboard actually correspond to the top of the private leaderboard? Because in the churn prediction challenge, there's like 4 people who are just completely above everyone else.
It totally depends, you know, like if they randomly sampled the public and private leaderboard, then it should be extremely indicative, right? But it might not be, right? So in this case, no, Kaggle's crashed. Oh, here it comes. So in this case, the person who was second on the public leaderboard did end up winning. SDNT came 7th, right? So, in fact, you can see the little green thing here, right? Whereas this guy jumped 96 places. If we had entered with the neural net we just looked at, we would have jumped 350 places. So it just depends. And so often, like, you can figure out whether the public leaderboard, like sometimes they'll tell you the public leaderboard was randomly sampled, sometimes they'll tell you it's not. Generally, you have to figure it out by looking at the correlation between your validation set results and the public leaderboard results to see how well they're correlated. Sometimes if like 2 or 3 people are way ahead of everybody else, they may have found some kind of leakage or something like that. Like that's often a sign that there's some trick. Okay, so that's Rossmann, and that brings us to the end of all of our material. So let's come back after the break and do a quick review, and then we will talk about ethics and machine learning. So let's come back in 5 minutes. So we've learnt 2 ways to train a model. One is by building a tree, and one is with SGD. Okay, and so the SGD approach is a way we can train a model which is a linear model or a stack of linear layers with nonlinearities between them. Whereas tree building specifically will give us a tree. Right? And then tree building we can combine with bagging to create a random forest, or with boosting to create a GBM, or various other slight variations such as extremely randomized trees. So it's worth like reminding ourselves of like what these things do. So like let's look at some data. So if we've got some data like so, actually let's look specifically at categorical data, right? Okay, so categorical data, there's a couple of possibilities of what categorical data might look like. It could be like, okay, so let's say we've got zip code, like, so we've got line 4003 is our zip code, right? And then we've got like sales, right? And it's like 50, and like 94131, sales are 22, and so forth, right? So we've got some categorical variable. So there's a couple of ways we could represent that categorical variable. One would be just to use the number, right? And like maybe it wasn't a number to start, maybe it wasn't a number at all. Maybe our categorical variable is like San Francisco, New York, Mumbai, and Sydney, right? But we can turn it into a number just by like arbitrarily deciding to give them numbers, right? So like it ends up being a number. So we could just use that kind of arbitrary number. So if it turns out that zip codes that are numerically next to each other have somewhat similar behavior, then the zip code versus sales chart might look something like this, for example, right? Or alternatively, if the zip code versus sales, if the 2 zip codes next to each other didn't have in any way similar sales behavior, you would expect to see something that looked more like this. Like kind of just all over the place, right? Okay, so they're the kind of 2 possibilities. So what a random forest would do, if we had just encoded zip in this way, is it's going to say, all right, I need to find my single best split point. Okay, the split point that's going to make the 2 sides have as small a standard deviation as possible, or mathematically equivalently have the lowest root mean squared error. So in this case, it might pick here as our first split point, because on this side there's one average, and on the other side there's the other average. Okay, and then for its second split point, it's going to say, okay, how do I split this? And it's probably going to say, I would split here, right? Because now we've got this average versus this average, right? And then finally, it's going to say, okay, how do we split here? And it's going to say, okay, I'll split there, right? So now I've got that average and that average, okay? So you can see that it's able to kind of hone in on the set of splits it needs, even though it kind of does it greedily, top down, one at a time, right? The only reason it wouldn't be able to do this is if, like, it was just such bad luck that the two halves were kind of always exactly balanced, right? But even if that happens, it's not going to be the end of the world, because it'll split on something else, some other variable, and next time around, you know, it's very unlikely that it's still going to be exactly balanced in both parts of the tree, right? So in practice, this works just fine. In the second case, right, it can do exactly the same thing, right? It'll say, like, okay, which is my best first split, right? Even though there's no relationship between one zip code and its neighboring zip code numerically, we can still see here if it splits here, right? There's the average on one side, and the average on the other side is probably about here, right? And then where would it split next? Probably here, right? Because here's the average on one side, here's the average on the other side, right? So again, can do the same thing, right? It's going to need more splits because it's going to end up having to kind of narrow down on each individual large zip code and each individual small zip code, but it's still going to be fine, okay? So when we're dealing with building decision trees for random forests or GBMs or whatever, we tend to encode our variables just as ordinals, okay? On the other hand, if we were doing a neural network, or like the simplest version, like a linear regression or a logistic regression, the best it could do is that, right? Which is no good at all. And ditto with this one. It's going to be like that, okay? So an ordinal is not going to be a useful encoding for a linear model or something that stacks linear and nonlinear models together. So instead, what we do is we create a one-hot encoding, right? So we'll say, like, you know, here's 1, 0, 0, 0, here's 0, 1, 0, 0, here's 0, 0, 1, 0, 0, 0, 0, 1. Okay? And so with that encoding, it can effectively create like a little histogram, right? Where it's going to have a different coefficient for each level. Okay? And so that way it can do exactly what it needs to do. Can you pass that back, please?
At what point does that become like too tedious for your system? Or does it not?
Pretty much never.
Okay.
Yeah. Because remember, in real life, we don't actually have to create that matrix. Instead, we can just, you know, have the 4 coefficients, right, and just do an index lookup to grab the second one, which is mathematically equivalent to multiply by the one-hot encoding. Okay, so that's no problem. One thing to mention, you know, I know you guys have kind of been taught quite a bit of more like analytical solutions to things. And in analytical solutions to like a linear regression, you get, you can't solve something with this amount of collinearity. In other words, Sydney, you know something is Sydney if it's not Mumbai or New York or San Francisco. So in other words, there's 100% collinearity between the 4th of these classes versus the other 3. And so if you try to solve a linear regression analytically that way, the whole thing falls apart. Now note, with SGD we have no such problem. Okay, like SGD, why would it care, right? We're just taking one step along the derivative. It cares a little, right? Because like in the end, the main problem with collinearity is that there's an infinite number of equally good solutions, right? So in other words, we could increase all of these and decrease this, or decrease all of these and increase this, and they're going to balance out, right? And when there's an infinitely large number of good solutions, it means there's a lot of kind of flat spots in the loss surface, and it can be harder to optimize. right? So that's a really easy way to get rid of all of those flat spots, which is to add a little bit of regularization. So if we added a little bit of weight decay, like 1e neg 7 even, then that basically says these are not all equally good anymore. The one which is the best is the one where the parameters are the smallest and the most similar to each other, and so that'll again move it back to being a nice loss function. Yes?
Could you just clarify that point you made about why one hard coding wouldn't be that tedious?
Sure. If we have a one-hot encoded vector, right, and we are multiplying it by a set of coefficients, right, then that's exactly the same thing as simply saying, let's grab the thing where the 1 is, right? So in other words, if we had stored this as a 0, you know, and this one as a 1, and this one as a 2, right, then it's exactly the same as just saying, hey, look up that thing in the array. Okay. And so we call that version an embedding, right? So an embedding is a weight matrix you can multiply by a one-hot encoding, and it's just a computational shortcut. Okay, but it's mathematically the same. So there's a key difference. So the first, key difference is between like solving linear type models analytically versus with SGD. With SGD, we don't have to worry about collinearity and stuff, or at least not nearly to the same degree. And then the difference between solving a linear or single layer or multi-layer model with SGD versus a tree is going to be like, it's going to complain about less things, right? So in particular, you can just use ordinals as your categorical variables. And as we learned just before, we also don't have to worry about normalizing continuous variables for a tree, but we do have to worry about it for these SGD trained models. So then we also learned a lot about interpreting random forests in particular. And if you're interested, you may be interested in trying to use those same techniques to interpret neural nets. Right? So if you want to know which of my features are important in a neural net, you could try the same thing. Try shuffling each column in turn and see how much it changes your accuracy. Okay? And that's going to be your feature importance for your neural net. And then if you really want to have fun, recognize then that shuffling that column is just a way of calculating how sensitive the output is to that input, which in other words is the derivative of the output with respect to that input. And so therefore maybe you could just ask PyTorch to give you the derivatives with respect to the input directly and see if that gives you the same kind of answers, right? You could do the same kind of thing for a partial dependence plot. You could try, doing the exact same thing with your neural net, replace everything in a column with the same value, do it for 1960, 1961, 1962, plot that, right? I don't know of anybody who's done these things before, not because it's rocket science, but just because, I don't know, maybe no one thought of it, or it's not in a library, I don't know. But if somebody tried it, I think you should find it useful. It would make a great blog post, maybe even a paper if you wanted to take it a bit further. So there's a thought of something you could do. So most of those interpretation techniques are not particularly specific to random forests. Things like the tree interpreter certainly are, because they're all about like what's inside the tree. Can you pass it to Karen?
We're applying tree interpreter for neural nets. How are we going to make inference out of activations that the path follows, for example?
So,
how are we going to, like, in tree interpreter, we are like...
we're looking at the path.
We are looking at the paths and their contributions of the features.
Yeah.
In this case, it will be same with activations, I guess, the contributions of each activation and their path.
Yeah, maybe. I don't know. I haven't thought about it.
How can we make inference out of the activations?
So I'd be careful saying the word inference, because people normally use the word inference specifically to mean the same as like a test time prediction.
You
make some kind of interrogate the model.
Yes.
Yeah, no, sure. We should think about that.
Okay.
Actually, Hinton and one of his students just published a paper on how to approximate a neural net with a tree for this exact reason, which I haven't read the paper yet. Could you pass that?
So in linear regression and traditional statistics, like one of the things that we focused on was statistical significance of like the changes and things like that. And so when thinking about a tree interpreter or even like the waterfall chart, which I guess is just a visualization, I guess where does that fit in? Like, because we can see like, oh yeah, this looks important in the sense that it causes large changes, but how do we know that it's like traditionally statistically significant or anything of that sort?
So most of the time I don't care about the traditional statistical significance, and the reason why is that nowadays the main driver of statistical significance is data volume, not kind of practical importance. And nowadays most of the models you build will have so much data that like every tiny thing will be statistically significant, but most of them won't be practically significant. So my main focus therefore is practical significance, which is, does the size of this influence impact your business? You know, statistical significance only, you know, like it was much more important when we had a lot less data to work with. If you do need to know statistical significance because, for example, you have a very small data set because it's like really expensive to label or hard to collect or whatever, or it's a medical data set for a rare disease, you can always get statistical significance by bootstrapping, which is to say that you can randomly resample your data set a number of times, train your model a number of times, and you can then see the actual variation in predictions. Okay, so that's with bootstrapping, you can turn any model into something that gives you confidence intervals. There's a paper by Michael Jordan which has a technique called the bag of little bootstraps, which actually kind of takes this a little bit further, and well worth reading if you're interested. Can you pass it to Prince?
So you said we don't need one-hot encoding metrics if we are doing random forest or if we are doing any tree-based models. What will happen if we do that, and how bad can our model be?
If you do one-hot encoding?
For random forest.
Yeah, we actually did do it. Remember we had that like maximum category size, and we did create one-hot encodings. And the reason why we did it was that then our feature importance would tell us the importance of the individual levels, and our partial dependence plot, we could include the individual levels. So it doesn't necessarily make the model worse. It may make it better, but it probably won't change it much at all. In this case, it hardly changed it.
This is something that we have noticed on real data also, that if cardinality is higher, let's say 50 levels, and if we do one-hot encoding, the random forest performs very badly. And
yeah, that's right. If the cardinal, that's why we have that in. That's why in FastAI we have that like maximum categorical size. You know, because at some point your one-hot encoded variables become too sparse, right? So I generally like cut it off at 6 or 7. Also, because like when you get past that, it kind of becomes less useful because the feature importance, there's going to be too many levels to really look at.
So can it not just not look at those levels which are not important and just gives those significant features as important?
Yeah. Yeah, I mean, it'll be okay, you know. It's just like once the cardinality increases too high, you're just splitting your data up, you know, too much basically. And so in practice, your ordinal version is likely to be better.
Thanks.
Okay, so. Yeah, so there's no time to kind of review everything, but I think that's the kind of key concepts. And then, of course, remembering that, you know, the embedding matrix that we can use is likely to have more than just one coefficient. We'll actually have a dimensionality of a few coefficients, which isn't going to be useful for most linear models. But once you've got multi-layer models, that's now creating a representation of your category, which is kind of quite a lot richer, and you can do a lot more with it. Let's now talk about the most important bit. We started off early in this course talking about how actually a lot of machine learning is kind of misplaced. People focus on predictive accuracy, Like Amazon has a collaborative filtering algorithm for recommending books, and they end up recommending the book which it thinks you're most likely to rate highly. And so what they end up doing is probably recommending a book that you already have or that you already know about and would have bought anyway, right? Which isn't very valuable. What they should instead have done is to figure out, like, which book can I recommend that would cause you to change your behavior, right? And so that way we actually maximize our lift in sales due to recommendations. And so this idea of, like, the difference between optimizing influencing your actions versus just kind of improving predictive accuracy. Improving predictive accuracy is a really important distinction which is, like, very rarely discussed in academia or industry, kind of crazily enough. It's more discussed in industry. It's particularly ignored in most of academia. Right? So it's a really important idea, which is that in the end, the goal of your model, presumably, is to influence behavior. Okay? And remember I actually mentioned a whole paper I have about this, where I introduce this thing called the drivetrain approach, where I talk about, like, ways to think about how to incorporate machine learning into, like, how do we actually influence behavior. So, that's a starting point. But then the next question is, like, okay, if we're trying to influence behavior, what kind of behavior should we be influencing, and how, and what might it mean when we start influencing behavior, right? Because, like, nowadays, like, a lot of the companies that you're going to end up working at are big-ass companies, and you'll be building stuff that can influence millions of people, right? So what does that mean? I'm not going to tell you what it means, because, like, I don't know. All I'm going to try and do is make you aware of some of the issues, right? And make you believe two things about them. First, that you should care, right? And second, that they're big current issues, right? The main reason I want you to care is because I want you to want to be a good person and show you that, like, not thinking about these things will make you a bad person. But if you don't find that convincing, I will tell you this. Volkswagen were found to be cheating on their emissions tests. The person who was sent to jail for it was the programmer that implemented that piece of code. They did exactly what they were told to do, right? And so if you're coming in here thinking, hey, I'm just a techie, I'll just do what I'm told, right? That's my job, is to do what I'm told. I'm telling you, if you do that, you can be sent to jail for doing what you're told. Okay? So A, don't just do what you're told, because you can be a bad person, and B, you can go to jail. Okay? Second thing to realize is, in the heat of the moment, you're in a meeting with 20 people at work, and you're all talking about how you're going to implement, this new feature, and everybody's discussing it. And there's some, and everybody's like, we could do this, and here's a way of modeling it, and then we can implement it, and here's these constraints. And there's some part of you that's thinking, am I sure we should be doing this? Right? That's not the right time to be thinking about that, because it's really hard to, like, step up then and say, excuse me, I'm not sure this is a good idea. You actually need to think about how you would handle that situation ahead of time. Right? So I want you to, like, think about these issues now, right? And realize that by the time you're in the middle of it, right, you might not even realize it's happening. Like, it'll just be a meeting, like every other meeting, and a bunch of people will be talking about how to solve this technical question. Okay? And you need to be able to recognize, like, oh, this is actually something with ethical implications. So Rachel actually wrote all of these slides. I'm sorry she can't be here to present this, because, like, she's studied this in depth, and she's actually been in difficult environments herself where she's kind of seen these things happening. We know how hard it is, right? But let me give you a sense of, like, what happens, right? So engineers trying to solve engineering problems is, and causing problems is not a new thing, right? So in Nazi Germany, IBM, the group known as Hollerith, right? Hollerith was the original name of IBM, and it comes from the guy who actually invented the use of punch cards for tracking the US Census, the first mass, wide-scale use of punch cards for data collection in the world, right? And that turned into IBM. And so at this point, this unit at least was still called Hollerith. So Hollerith sold a punch card system to Nazi Germany. And so each punch card would like code, this is a Jew, 8, Gypsy, 12, general execution, 4, death by gas chamber, 6. And so here's one of these cards describing the right way to kill these various people, right? And so a Swiss judge ruled that IBM's technical assistance facilitated the tasks of the Nazis in commission of their crimes against humanity. This led to the death of something like 20 million civilians. So according to the Jewish Virtual Library, where I got these pictures and quotes from, their view is that the destruction of the Jewish people became even less important because of the invigorating nature of IBM's technical achievement, only heightened by the fantastical profits to be made. Right? So this was a long time ago, and hopefully you won't end up working at companies that facilitate genocide. Right? But perhaps you will, right? Because perhaps you'll go to Facebook who are facilitating genocide right now. Right? And I know people at Facebook who are doing this, and they had no idea they were doing this. Right? So right now in Facebook, the Rohingya are in the middle of a genocide, a Muslim population of Myanmar. Babies are being grabbed out of their mother's arms and thrown into fires. People are being killed, hundreds of thousands of refugees. When interviewed, the Myanmar generals doing this say, "We are so grateful to Facebook for letting us know about the Rohingya fake news," the words they use, the Rohingya fake news, that these people are actually not human, that they're actually animals. Right? Now, Facebook did not set out to enable the genocide of the Rohingya people in Myanmar. No. Instead, what happened is they wanted to maximize impressions and clicks. Right? And so it turns out that for the data scientists at Facebook, their algorithms kind of learned that if you take the kinds of stuff people are interested in and feed them slightly more extreme versions of that, you're actually going to get a lot more impressions. And the project managers are saying maximize these impressions, and people are clicking, and like it creates this thing, right? And so the potential implications are extraordinary and global, right? And this is something that is literally happening. This is October 2017. It's happening now. Okay, could you pass that back there?
So I just want to clarify what was happening here. So it was the facilitation of fake news or inaccurate media?
Yeah, so what happened was, let me go into it in more detail. So what happened was in mid-2016, Facebook fired its human editors. Right? And so it was humans that decided how to order things on your homepage. Those people got fired and replaced with machine learning algorithms. And so the machine learning algorithms written by data scientists like you, they had nice, clear metrics, and they were trying to maximize their predictive accuracy and be like, okay, we think if we put this thing higher up than this thing, we'll get more clicks. Okay. And so it turned out that these algorithms for putting things on the Facebook newsfeed had a tendency to say oh, human nature is that we tend to click on things which stimulate our views and are therefore more extreme versions of things we already see. Okay. So this was great for the kind of Facebook revenue model of maximizing engagement. It looked good on all of their KPIs. And so at the time, there was some negative press about I'm not sure that the stuff that Facebook's now putting on their trending section is actually that accurate. But from the point of view of the metrics that people were optimizing at Facebook, it looked terrific. Right? And so way back to October of 2016, people started noticing some serious problems. For example, it is illegal to target housing to people of certain races in America. That is illegal. And yet, a news organization discovered that Facebook was doing exactly that, right, in October 2016. Again, not because somebody in that data science team said, like, let's make sure black people can't live in nice neighborhoods, right? But instead, they found that their automatic clustering and segmentation algorithm found there was a cluster of people who didn't like African Americans, and that if you targeted them with these kinds of ads, then they would be more likely to select this kind of housing or whatever, right? But the interesting thing is that even after being told about this 3 times, Facebook still hasn't fixed it, right? And that is to say, these are not just technical issues, they're also economic issues, right? When you start saying, like, the thing that you get paid for, that is ads, you have to change the way that you structure those so that, you either use more people that cost money, or you are less aggressive on your algorithms to target people, based on minority group status or whatever, that can impact revenues. And so the reason I mention this is you will likely at some point in your career find yourself in a conversation where you're thinking, I'm not confident that this is morally okay. The person you're talking to is thinking in their head, this is going to make us a lot of money, right? And you don't quite ever manage to have a successful conversation because you're talking about different things, And so when you're talking to somebody who may be more experienced and more senior than you, and they may sound like they know what they're talking about, right? Just realize that their incentives are not necessarily going to be focused on how do I be a good person? They're not thinking, how do I be a bad person? But, the more time you spend in industry, in my experience, the more desensitized you kind of get to this stuff of okay, maybe getting promotions and making money isn't the most important thing, right? So, for example, I've got a lot of friends who are very good at computer vision, and some of them have gone on to create startups that seem like they're almost handmade to help authoritarian governments surveil their citizens. And when I ask my friends, have you thought about how this could be used in that way, they're generally kind of offended that I ask, But I'm asking you to think about this, wherever you end up working, if you end up creating a startup, tools can be used for good or for evil, right? And so I'm not saying don't create excellent object tracking and detection tools from computer vision, because you could go on and use that to create a much better surgical intervention robot toolkit, right? I'm just saying be aware of it, think about it, talk about it, So here's one I find fascinating, and there's this really cool thing actually that meetup.com did. This is from a meetup.com talk that's online. They think about this. They actually thought about this. They actually thought, you know what? If we built a collaborative filtering system like we learned about in class to help people decide what meetup to go to, it might notice that on the whole in San Francisco, a few more men than women tend to go to techie meetups. And so it might then start to decide to recommend techie meetups to more men than women. As a result of which, more men will go to techie meetups. As a result of which, when women go to techie meetups, they'll be like, oh, this is all men. I don't really want to go to techie meetups. As a result of which, the algorithm will get new data saying that men like techie meetups better, right? And so it continues, right? And so a little bit of kind of that initial push from the algorithm can create this runaway feedback loop, and you end up with almost all male techie meetups, for instance, right? And so this kind of feedback loop is a kind of subtle issue that you really want to think about when you're thinking about what is the behavior that I'm changing with this algorithm that I'm building. So another example, which is kind of terrifying, is in this paper, where the authors describe how a lot of departments in the US are now using predictive policing algorithms, right? So where can we go to find somebody who's about to commit a crime? And so you know that the algorithm simply feeds back to you basically the data that you've given it, right? So if your police department has engaged in racial profiling at all in the past, then it might suggest slightly more often, maybe you should go to the black neighborhoods to check for people committing crimes. Right? As a result of which, more of your police officers go to the black neighborhoods, as a result of which they arrest more black people, as a result of which the data says that the black neighborhoods are less safe, as a result of which the algorithm says to the policeman, maybe you should go to the black neighborhoods more often, and so forth. Right? And this is not like, vague possibilities of something that might happen in the future. This is like documented work from top academics who have carefully studied the data and the theory, right? This is like serious scholarly work. It's like, no, this is happening right now. And so, again, like, I'm sure the people that started creating this predictive policing algorithm didn't think like, how do we arrest more black people? Right? Hopefully they were actually thinking, gosh, I'd like my children to be safer on the streets. How do I create, a safer society? Right? But they didn't think about this nasty runaway feedback loop. So actually this one about social network algorithms is actually an article in the New York Times recently about one of my friends, Renee DeResta, and she did something that was kind of amazing. She set up a second Facebook account. Right, like a fake Facebook account. And she was very interested in the anti-vax movement at the time. So she started following a couple of anti-vaxxers and visited a couple of anti-vax links. And so suddenly her news feed starts getting full of anti-vaxxer news, along with other stuff like chemtrails and deep state conspiracy theories and all this stuff. And so she's like, starts clicking on those, right? And the more she clicked, the more hardcore, far-out conspiracy stuff Facebook recommended. So now when Renee goes to that Facebook account, the whole thing is just full of angry, crazy, far-out conspiracy stuff. Like, that's all she sees. And so if that was your world, right, then as far as you're concerned, it's just like this continuous reminder and proof of all this stuff, right? And so again, it's like this is, to answer your question, this is the kind of runaway feedback loop that ends up telling Myanmar generals, throughout their Facebook homepage that Rohingya are animals and fake news and whatever else, right? So, it's a lot of this comes also from bias, right? And so, like, let's talk about bias specifically. So bias in image software comes from bias in data. And so most of the folks I know at Google Brain building computer vision algorithms, very few of them are people of color. And so when they're training the algorithms with, photos of their families and friends, they are training them with very few people of color. And so when FaceApp then decided we're going to try looking at lots of Instagram photos to see which ones are upvoted the most, without them necessarily realizing it, the answer was light-colored faces. So then they built a generative model to make you more hot. And so this is the actual photo, and here is the hotter version, right? So the hotter version is like more white, less nostrils, more European looking, right? And so this did not go down well, to say the least. So so again, I don't think anybody at FaceApp said let's create something that makes people look more white, right? They just trained it on a bunch of images of the people that they had around them, okay? And this has kind of, serious commercial implications as well. They had to pull this feature, right? And they had a huge amount of negative pushback, like as they should, right? Here's another example. Google Photos created this photo classifier, airplanes, skyscrapers, cars, graduation, and gorillas, right? So, like, think about how this looks to, like, most people. Like, to most people, they look at this, they don't know about machine learning. They say, what the fuck? Somebody at Google wrote some code to take black people and call them gorillas. Like, that's what it looks like, right? Now, we know that's not what happened, right? We know what happened is, the team, of folks at Google computer vision experts who have none, or few people of color working in the team, built a classifier using all the photos they had available to them. And so when the system came across, a person with dark skin, it was like, oh, I've only mainly seen that before amongst gorillas, so I'll put it in that category, right? So again, it's the bias in the data creates a bias in the software. And again, the commercial implications were very significant. Like, Google really got a lot of bad PR from this, as they should. This was a photo that somebody put in their Twitter feed. They said, like, look what Google Photos just decided to do. You can imagine what happened with the first international beauty contest judged by artificial intelligence, right? Basically, it turns out all the beautiful people are white, again, right? So, like, you kind of see this bias in image software, thanks to bias in the data, thanks to lack of diversity in the teams building it. You see the same thing in natural language processing, right? So here is Turkish. O is the pronoun in Turkish, which has no gender, right? There is no he or versus she, right, Karim? No he versus she. But of course, in English, we don't really have a widely used ungendered singular pronoun. So Google Translate converts it to this. Okay. Now, there are plenty of people who saw this online and said, like, literally, so what? It is correctly feeding back the usual usage in English. Like, this is, I know how this is trained. This is like word-to-vec vectors. It was trained on Google News corpus, Google Books corpus. It's just telling us how things are. And, like, from a point of view, that's entirely true, right? Like, the biased data to create this biased algorithm is the actual data of how people have written books and newspaper articles for decades. But does that mean that this is the product that you want to create? Does this mean this is the product you have to create? Right? Just because the particular way you've trained the model means it ends up doing this, is this actually the design you want? And can you think of potential negative implications and feedback loops this could create? Right? And, if any of these things bother you, then now, lucky you have a new cool engineering problem to work on. Like, how do I create unbiased NLP solutions? And now there are some startups starting to do that and starting to make some money, right? So, like, these are opportunities for you. It's like, hey, here's some stuff where people are creating screwed up societal outcomes because of their shitty models. Like, okay, well, you can go and build something better, right? So, like, another example of the bias in word-to-vec word vectors is restaurant reviews rank Mexican restaurants worse because the Mexican words tend to be associated with criminal words in the US press and books more often. Again, this is like a real problem that is happening right now. Rachel actually did some interesting analysis of just the plain word-to-vec word vectors, where she basically pulled them out and, looked at these analogies based on some research that had been done elsewhere. And so you can see, like, word-to-vec, like the vector directions show that father is to doctor, is to mother, is to nurse, man is to computer programmer, as woman is to homemaker, and so forth, right? So, like, it's really easy to see what's in these word vectors. And, they're kind of fundamental to much of the NLP, or probably just about all of the NLP software we use today. So like here's a great example. So ProPublica has actually done a lot of good work in this area. Many judges now have access to sentencing guideline software. And so sentencing guideline software says to the judge, for this individual, we would recommend this kind of sentence. Right? And now, of course, the judge doesn't understand machine learning. So like they have two choices, which is either do what it says or ignore it entirely. Right? And some people fall into each category. Right? And so for the ones that fall into the like do what it says category, here's what happens. For those that were labeled higher risk, right, the subset of those that were labeled higher risk but actually turned out not to reoffend, right, was about a quarter of whites and about a half of African Americans. Right? So like nearly twice as often, right, people who didn't reoffend were marked as higher risk if they were African American. And vice versa. Amongst those that were labeled lower risk, but actually did reoffend, turned out to be about half of the whites and only 28% of the African Americans. So this is data which I would like to think nobody is setting out to create something that does this, right? But when you start with biased data, right, and, the data says that whites and blacks smoke marijuana at about the same rate, but blacks are jailed at, I think it's something like 5 times more often than whites. The nature of the justice system in America, at least at the moment, is that it's not equal, it's not fair. And therefore the data that's fed into the machine learning model is going to basically support that status quo. And then because of the negative feedback loop, it's just going to get worse and worse, right? I'll tell you something else interesting about this one, which a researcher called Abe Gong has pointed out, is here are some of the questions that are being asked, right? So let's take one. Was your father ever arrested? Right? So your answer to that question is going to decide whether you're locked up and for how long. Okay. Now, as a machine learning researcher, do you think that might improve the predictive accuracy of your algorithm and get you a better R-squared? It could well, right? I don't know. Maybe it does. You try it out, it's like, oh, I got a better R-squared. So does that mean you should use it? Well, there's another question. Do you think it's reasonable to lock somebody up for longer because of who their dad was? Right? And yet these are actually the examples of questions that we are asking right now to offenders and then putting into a machine learning system to decide what happens to them. Okay? So again, whoever designed this, presumably they were laser focused on technical excellence, getting the maximum area under the ROC curve, and I found these great predictors that give me another 0.02, right? And I guess didn't stop to think well, is that a reasonable way to decide who goes to jail for longer? So putting this together, you can kind of see how this can get, more and more scary. We take a company like Taser, right? And Tasers are these devices that kind of give you a big electric shock, basically. And Taser's managed to do a great job of creating strong relationships with some academic researchers who seem to say whatever they tell them to say. To the extent where now, if you look at the data, it turns out that there's a much higher there's a pretty high probability that if you get tased, that you will die. It happens, not unusually. And yet, the researchers who they've paid to look into this have consistently come back and said, oh no, it was nothing to do with the taser. The fact that they died immediately afterwards was totally unrelated. It was just a random, things happen. So this company now owns 80% of the market for body cameras. And they've started buying computer vision AI companies. And they're going to try and now use these police body camera videos to anticipate criminal activity. Right? And so, what does that mean? Right? So is that okay, I now have some augmented reality display saying tase this person because they're about to do something bad. You know, so it's kind of like a worrying direction, and so, you know, I'm sure nobody who's a data scientist at Taser or at the companies that they bought out is thinking like, you know, this is the world I want to help create. But they could find themselves in, you know, or you could find yourself in the middle of this kind of discussion where it's not explicitly about that topic, but there's part of you that says like, I wonder if this is how this could be used. Right? And you know, I don't know exactly what the right thing to do in that situation is, because like you can ask, and of course people are going to be like, no, 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 no. So it's like, you know, are you going to, you know, what could you do? You know, you could like ask for some kind of written promise. You could decide to leave. You could, you know, start doing some research into the legality of things to say like, oh, I want to at least protect my own, you know, legal situation. I don't know, like have a think about how you would respond to that. So these are some questions that Rachel created as being things to think about, right? So if you're looking at building a data product or, you know, using a model, like if you're building a machine learning model, it's for a reason, okay? You're trying to do something, right? So what bias may be in that data? Right? Because whatever bias is in that data ends up being a bias in your predictions, potentially then biases the actions that you're influencing, potentially then biases the data that you come back, and you may create a feedback loop. If the team that built it isn't diverse, you know, what might you be missing? Right? So for example, one senior executive at Twitter called the alarm about major Russian bot problems at Twitter way back, well before the election. That was the one black person in the exec team at Twitter, the one. And shortly afterwards, they lost their job, right? And so, like, definitely having a more diverse team means having a more diverse set of opinions and beliefs and ideas and things to look for and so forth. So non-diverse teams seem to make more of these bad mistakes. Can we audit the code? Is it open source? Check for the different error rates amongst different groups. Is there like a simple rule we could use instead that's like extremely interpretable and easy to communicate? And like, you know, if something goes wrong, do we have a good way to deal with it? Right? So when we've talked to people about this, and a lot of people like have come to Rachel and said like, I'm concerned about something my organization's doing. You know, what do I do? Or I'm just concerned about my toxic workplace. What do I do? And very often, you know, Rachel will say like, well, have you considered leaving? And they will say, oh, I don't want to lose my job. Right? But actually, if you can code, you're in like 0.3% of the population. If you can code and do machine learning, you're in probably like 0.01% of the population. You are massively, massively in demand. So like realistically, you know, obviously it's an organization does not want you to feel like you're somebody who could just leave and get another job. That's not in your interest, in their interest. But that is absolutely true. Right? And so one of the things I hope you leave this course with is enough self-confidence to recognize that you have the skills, you know, to get a job. And particularly once you've got your first job, your second job is an order of magnitude easier. Right? And so, you know, this is important not just so that you feel like you actually have the ability to act ethically, but it's also important to realize, like, if you find yourself in a toxic environment, right, which is pretty damn common, unfortunately. Like, there's a lot of shitty tech cultures, environments, particularly in the Bay Area, right? If you find yourself in one of those environments, the best thing to do is to get the hell out, right? And if you don't have the self-confidence to think you can get another job, you can get trapped. Right? So, you know, it's really important. It's really important to know that you are leaving this program with very in-demand skills And particularly after you have that first job, you're now somebody with in-demand skills and a track record of being employed in that area. Okay, great. So, yes?
Well, this is kind of just a broad question, but what are some things that you know of that people are doing to treat bias in data?
You know, it's kind of like a bit of a controversial subject at the moment, and there are like, some people are trying to use an algorithmic approach, you know, where they're basically trying to say, how can we identify the bias and kind of like subtract it out? But like the most effective ways I know of are ones that are trying to treat it at the data level. So like start with a more diverse team, particularly a team involved, you know, which includes people from the humanities, like sociologists, psychologists, economists, people that understand feedback loops and implications for human behavior. And they tend to be equipped with, you know, good tools for kind of identifying and tracking these kinds of problems. And then kind of trying to incorporate the solutions into the process itself. Let's say there isn't kind of like a, you know, some standard process I can point you to and say, here's how to solve it. You know, if there is such a thing, we haven't found it yet. You know, it requires a diverse team of smart people to be aware of the problems and work hard at them, is the short answer. Can you pass that back, please?
This is just kind of a general thing, I guess, for the whole class. If you're interested in this stuff, I read a pretty cool book. Jeremy, you've probably heard of it, Weapons of Math Destruction, by Kathy O'Neill. It covers a lot of the same stuff.
Yeah.
Just more on the topic. So
yeah, thanks for the recommendation. So Kathy's great. She's also got a TED Talk. I didn't manage to finish the book because it's so damn depressing. I was just like, yeah, no more. But yeah, it's it's very good. All right. Well, that's it. Thank you, everybody. You know, this has been really intense for me. You know, obviously this was meant to be something that I was sharing with Rachel. So I've, you know, ended up doing one of the hardest things in my life, which is to teach 2 people's worth of course on my own, and also look after a sick wife, and have a toddler, and also do a deep learning course, and also do all this with a new library that I just wrote. So I'm looking forward to getting some sleep. But it's been totally worth it, because you've been amazing. Like I'm thrilled with how you've, you know, reacted to the kind of, you know, the opportunities I've given you, and also to the feedback that I've given you. So congratulations.